right. Well, welcome everyone. I think this is our virtual climate variability and change working group. Thank you for talks today. And at the end, at about 3:15, we'll be having a kind of update on the working group and a discussion. So I hope you'll stick around for that. That's when we'll be talking about experiments that people like to see done and the nation particular. So if you have any thoughts, please stick around for that. All speakers, you have a 15-minute slot, and we'll give you a warning when you're at 12 minutes, the time to wrap up, to leave some questions. So I guess I'll hand it over to Sarah, who's going to chair the first session.
Hi, yeah. So we're all excited to be here. So I'm Sarah Larson, and just a reminder, as Isla said, so I'll let you know when the 12-minute mark hits, and then you'll have just a minute or so to wrap up, so we have time for questions. So our first speaker is Ruyan Chen, and the title of the talk is Mechanisms Behind the Springtime North Pacific Enso Teleconnection Bias and Climate Models.
Okay, thanks. Let me see how this works.
I can see your desktop. Oh, it was there for a second.
Okay. Does it work?
Yes.
Okay. Okay, sorry. Okay, good morning, everyone. I'm Ruyan. I'm now a postdoc at the South China Sea Institute of Oceanology. And my talk today will on the title of Mechanisms Behind the Springtime North Pacific Enso Teleconnection Bias in Climate Models. This work was actually inspired during my visiting time at UNCAR as a graduate student and collaborated with Ella and Clara. They offered really great help to this project. So at first, what's the North Pacific Enso teleconnection? It can be illustrated as here, accompany the evolution of positive SST anomalies over the eastern tropical Pacific during El Nino events. We can see an anomalous quasi-barotropic low pressure system occur over the North Pacific. And the signal usually intensifies from December to January and then decays from February. So how well of our present models can reproducing this kind of relationship? Let's check it first in one of the CESM simulations, the TOGA type simulation. And it is obvious to note that from February to April, the modeled North Pacific Enso teleconnection patterns are much stronger than observation. And that's how it triggers our first study to explore the robustness and the ubiquitousness of these bias. For more details, I think you can refer to this published paper, but now I'm gonna do a very quick review. So to ease the work, we first define a North Pacific index as the area averaged sea level pressure anomalies over this red box region, and calculated that for each Enso month in reanalysis data as shown by the red curves, and in different model configurations of CESM, as well as in different CMIP5 and CMIP6 models, as shown here by all these gray curves. So in the red panel, you can see that before January, CESM agrees well with the observation, but after that, when the observation shows rapid decay of the MPI amplitude, all these 9 CESM experiments actually remaining in their developing phase before February. So it's leaving an overly strong North Pacific circulation anomalies during the springtime of Enso. Similar features can also be found in the multimodal mean of CMIP models, and no significant improvement can be seen in CMIP6 compared to CMIP5. We also applied a bootstrapping technique to test the significance against sampling error, and it turns out that more than half of the CMIP models exhibit significant bias feature. So at this stage, we prove that the overly strong North-Pacific Enso teleconnection bias in climate models is both ubiquitous and significant. This slide shows the climate impact of these bias. The regression maps here suggest that the model's bias would forcibly prolong the influence of Enso into the spring season, especially over its downstream area, that is the North America. So then the question becomes why we have this kind of bias in our models. According to the stationary wave theory, the wave structure is determined by the initial forcing and its interaction with the background flow. So in order to isolate the role played by these two main components, one straightforward method is to use a simplified model. Here we use the stationary wave model. The stationary wave model is based on the primitive equations, and all the variables are described as a deviation from a zonal mean. So compared to a full GCM, there is no consideration of complicated feedback processes. So it is not only very cheaper to run, but also favors the attribution analysis. Before doing sensitivity experiment, we need to first make sure that the stationary wave model can reproduce the North Pacific Enso teleconnection bias. Therefore, we ran two separate experiments. One is the observation-based, that's the basic state and the forcing terms are all taken from the GRA55 reanalysis, as shown here by the by the black boxes. And another one is the model-based one, which means all the raw material needed by the model is taken from the CESM TOGA simulation. So to model the stationary wave response during the El Nino springtime, the basic state is set to the FM season's climatology, and the forcing terms are anomalies composited during the El Nino events. The simulated string function at 300 are shown here, and it is clear that the Pacific wave trend response is stronger in the model-based simulation. And the difference field further proves that the springtime North Pacific circulation bias can be well reproduced by the stationary wave model. And it is also true if we look at the lower level near the surface. The next step is then to disentangle the contribution from different components by running a bunch of sensitivity experiments. So we took the observation-based experiment as a baseline, and for each time we switch one single component from the op space to the model-based. Then we differ their modeling results so that the contribution from the perturbed component can be isolated. For example, if we replace the diabatic heating from GRA55 to TOGA, but remain other input fields unchanged, reduce the simulation and differ their modeling results, the stationary wave response caused by diabatic heating difference can be achieved as shown here. Similarly, we can perturb the transient forcing term to get the contribution of transient activity difference. Or we can perturb the basic state to get the contribution of climatological background difference. And so by comparing these three panels, we can tell that the difference in the modeled and observed diabatic heating is the main cause behind the North Pacific circulation bias. We also find that the tropical diabatic heating is more important than extropical, and further divided the whole tropical belt into three ocean basins: tropical Indian Ocean, Central Western Pacific, and the Central Eastern Pacific. And we can see that a negative, positive, and negative bias structure can be consistently detected when the ops is calculated from different reanalysis data. So based on the TOGA basic state and imposing the heating field over these three ocean basins separately, in turn, their relative importance can be clearly detected. And the result shows that the diabatic heating difference over the Indian Ocean and the Central Western Pacific jointly contributing to the bias circulation formation. In contrast, the Central Eastern Pacific heating difference negatively contributes to the forming of the bias circulation. So if the stationary wave modeling results give us the right answer about the origin of the bias, then it is worth to test it in a full GCM. Here we use CAM5, that is the same model as that used in TOGA. And we ran two simulations. One is the pre-industrial and one is El Nino acidic anomaly simulation. And each simulation has 20 members so that the El Nino force response can be extracted as their difference. So as displayed here on the right, the North Pacific Enso tiny connection bias is evident and even stronger than that in the Toga composites. Meanwhile, significant tropical diabatic heating bias feature can also be detected as that shown in Toga. So in order to verify the conclusion as shown by the stationary wave model, that the tropical diabatic heating bias is the main cause for the formation of the springtime circulation bias, we tried to add the diabatic heating bias into the integration process of the model's thermodynamic equation as a correction term. So the purpose is that we want to artificially correcting the tropical diabatic heating bias in the model and see how the model will respond accordingly. However, it is worth noting that when the origin primary and complete bias field is directly used as the correction term, the correction effect will be nonlinearly amplified due to the feedback in the GCM. So in order to partially offset this overreacting side effect, we use a scaling factor to proportionally scale down the absolute amplitude of this correction term. Also, due to this existence of model feedback, it is also difficult for us to estimate the optimal correction field at once. So an iterative modification strategy is adopted, which means the bias correction term is optimized iteratively according to the residual bias in each iteration step. So after applying that to strategy, the model's diabatic heating field can gradually approach to the observation field. And after 8 steps of iteration, significant bias is barely seen over the whole tropical area. So could the improvement in the heating field also lead to a more realistic North Pacific state? The answer is yes. It can be found that the intensity of the cyclonic circulation anomaly over the North Pacific is significantly weakened after removing the tropical diabatic heating bias. And at the same time, the center of the circulation anomaly also moves eastward a little bit, and that is more consistent with the observation. So the last question becomes, we try to answer is that why significant bias prefer to occur during the springtime. So as has been detected in our evaluation work, the FM biased circulation anomalies are not carried over from its early winter, which means that the significant bias feature only occurs during the FM's average, not DJ. Based on our findings about the bias origin, it is kind of natural to guess that this is because the tropical heating bias only occurs during the springtime. However, if we compare the tropical diabatic heating field in these 2 seasons, the fact is that similar biased heating fields already established during the DJ's average. Again, with the help of the stationary wave modeling method, we can explore a little more into this phenomenon. So by sticking to the same diabatic heating field, but switching the DJ and FM basic states, the simulation results suggest that the springtime basic state is more favorable for a stronger wave propagating into the North Pacific. However, if we
12 minutes.
Okay. If we keep using the same basic state, but imposing the DJ or FM heating bias, the wave response is actually stronger in the DJ's when the DJ's heating bias is imposed. So a short summary. First, we find that most of our present models tend to overestimate the springtime North Pacific Enso connection. And that is because the models has deficiencies in simulating the tropical diabatic heating field, especially over the tropical Indian Ocean and Central Western Pacific. And the last is that the tropical diabatic heating bias already established during the early winter time, but the FM background favors its wave propagation. Last point is that our all the previous analyses are all based on the TOGA simulation, but here we show that the underlying mechanism may be a common problem in many other models as well, because we can see that there is significant correlation relationship between the Indian Ocean and the Western Pacific bias and the North Pacific circulation bias across the CMIP models. Okay, so that's all. Thanks.
Thanks, Brianne. So if you have any questions, you can either, I guess, just type in the chat or raise your hand or unmute yourself. It's not too big of a group.
Yeah, I guess I had a quick question, maybe. It's
Yeah.
very interesting talk. I was just curious if you had a sense of whether the fact that you're seeing the bias more in this late winter, early spring period is due to the kind of nature seasonality or due to preferential mean state errors in the model itself.
Yeah, I think it's for the seasonality, I think it's for the stationary wave modeling results, it tells that the basic state is very important. So it may due to the model in simulating the climatological thing. But that's not and I'm not seeing this just because this the diabatic heating is also important. So I think it's a kind of mixture. So both this the climatology and the variability is important in forming that phenomenon.
We'll take one more quick question from Haiyan.
A very nice talk. And I just wonder, because you mentioned that the biases mainly came from the extratropical heating in the simple model, but in the GCM, you proved that it mainly caused by the tropical heating. And I wonder whether you have checked in your GCM simulation whether this simulation, not only the teleconnection, but also the extratropical heating's bias was also reduced.
We also tested that when we reduce the tropical diabatic heating bias, the heating bias in extratropical area also reduced. Yeah, we have that result, but didn't have time to show it here. Thanks.
All right, so we need to move on to the next speaker. Brianne, if you can unshare.
Okay.
Yeah, perfect. So our next speaker is Yaning Guo, and the title is Enso Diversities and its Impact on Interannual Variation of Terrestrial Water Storage to Sea Level.
Could you see my slide?
I see this slide, but it's not full screen yet.
Is it right now?
Yes, there you go.
Okay, cool. Thank you. Hi, my name is Yaning Guo, and I am now a first-year PhD student at Cornell University. I am working with Flavio Lehner. So today I'm gonna talk about how Enso diversity impacts the terrestrial water storage and link it to the sea level variation. This is the outline of my presentation today. So for the first part, I will talk about a paper that we published last year with the co-authors from National Taiwan University. And it is more about how the annual variation of terrestrial water storage from satellites, renaissance, and offline CLM5 simulations. And then in the second part, I will talk about the internal variability and hydroclimate in CSM2. And this is an ongoing project. And some of the results I show later is actually not very, we don't have a very great explanation for them. And this is the work I work with Flavio Lehner, and it is collaborating with Dr. Newman, and he is going to have a presentation later too. So let's move on to the first part. From the IPCC AR6 report last year, it shows that the sea level rise is accelerated, and this is very likely to be related to human activity. However, from the satellite observations, the satellite is launched from 1992, and we can see that although there's a very obvious rising trend, but the interannual variation of global mean sea level sometimes will obscure the observation in terms of the trend. The interannual variation of global mean sea level is actually dominated by El Nino Southern Oscillation. As we can see from the figure below, when there's a warm phase, which is El Nino, we will have a higher than normal global mean sea level anomaly. But when it is a cold phase, which is La Nina, the global mean sea level anomaly will drop. And my study published last year is actually comparing why the two strong El Nino in the observational records, why they have different global mean sea level. So you can see that in 1987 and 2015, both of El Ninos are extreme El Nino by the definition of their ocean Nino index strength. But the global mean sea level interannual variation differ from each other up to 5.28 millimeter. So why this is such a differences? So the sea level variation is actually could be separated into two contributions. The first one is direct sea level, which we can understand it as the density variation of sea level. It is related to ocean heat content and salinity variations. When the volume increase, which means that the temperature is higher, it get more ocean heat content, and then as a result, the sea level will rise. And the second contribution to sea level variation is parasitic sea level. You can consider it as the mass variation, which is the extra water mass into the ocean. So if we consider the Earth as a closed system, the ocean mass increase is actually from the land, which is terrestrial water storage. And how this water change through to reservoirs is actually from the hydrologic cycle. So I used the reanalysis data from ECHO and showed that in the two strong El Nino events, their global mean sea level variation can be decomposed into the two sea level variation. And the differences between the two events is actually because of the parasitic sea level is increasing more in 2015 events. But why the parasitic sea level, which is the ocean mass, increased more in 2015 El Nino? So this is a little bit recapping what I mentioned before. The sea level, the ocean mass increase can be approximated by the terrestrial water storage anomaly. And the terrestrial water storage anomaly is actually the precipitation minus evapotranspiration and minus runoff. If we integrate the equations, the second equation here, we can get the total water storage variation, which we can approximate it as the parasitic sea level variation. So I used the terrestrial water storage data from Aerosol land, which is a reanalysis data from ECMWF. And then I also use CL and offline simulations to get the terrestrial water storage variation. And in order to filter out the contribution from glacier, so I also include the RACMO 2.3 phase 2, which is the water balance model that to simulating the water storage variation in Greenland and Antarctica. So this is the time series of the global mean parasitic, which is the minus terrestrial water storage from 1993 to 2016. From this figure, we can see that in the two events, which is 1997 and 2015 El Ninos, and I made a shading here, we can see that both from ECHO or Aero5 land or even CLM5, we can see that the parasitic variation, parasitic sea level variation is very similar to terrestrial water storage variation. And we can also see that in Aero5 land and CLM5, they both demonstrate the higher negative terrestrial water storage in the December, January, and February in 2015 event. But why there was this larger anomalous terrestrial water storage in 2015 El Nino? So actually, El Nino can be separated into two different types of El Ninos. The first one is Central Pacific El Nino, and the second one is the Eastern Pacific El Nino. They differ from their maximum sea surface temperature anomaly in terms of their locations. So let's look into the Central Pacific Index and Eastern Pacific Index of the two events. We can see that in the 1997 event, this El Nino is actually an Eastern Pacific El Nino. But for 2015 El Nino, it is more like a mixture of Central Pacific and Eastern Pacific El Ninos. So the next step we did is to calculate the correlation coefficient and the regression slope of parasitic sea level to in terrestrial water storage to the two indexes. Our results shows that no matter the data is from the ocean reanalysis or land reanalysis or even the COM5 offline simulations, they all shows that the Central Pacific type Enso drives more interannual terrestrial water storage variations. And if we look into the spatial pattern of the terrestrial water storage on the two indexes from Era 5 land, it shows that in the box region with the dot means that those regions have a larger than 95% significance level of their change. We can see that in those regions, in the Central Pacific type regression map, we can see the box region have a more decreased terrestrial water storage. And from CLM5, we can also show a very similar pattern in terms of in Australia and in Amazon region. But actually their spatial distribution is different from each other, which means that in the future, probably the study about model uncertainties of terrestrial water storage predictability is very important. So let's move on to the next part, is the internal variability in hydroclimate in CSM2, which is my ongoing project right now. So we analyzed the terrestrial water storage chain in CSM2 large ensemble. And these three figures shows, the first figure is the signal, which is the ensemble mean chain over 1980 to 2014. And then the noise is the spread, the standard deviation, which means the spread of the chain across the ensemble members. So overall, we can see there is a drying tendency in North America, and with the and the chain across ensemble member spread in Eastern US. So why? So the next step we are curious about is what's the tropical sea surface temperature's contribution to such a drying chain in North America. So we start to analyze the TOGA simulations. And this is a brief introduction about TOGA. And there are three different ensembles. The first one is prescribed historical ERSST version 5 SST in the tropics. And the other two, LIM 66 and LIM 94, is actually the possible sea surface temperature evolution driven from a cyclostationary linear inverse model. So our results so far shows that from the three simulations, they all shows a drying trend in North America, but the drying trend is stronger compared to CSM2 large ensembles. And from the equation that I showed previously, the TWS flux is actually driven by the precipitation, which is TWS main forcing. We can see that the ERSST version 5 LIM 96 and LIM 66 all showed increasing sea surface pressure change over North Pacific, which is more like a negative PDO phase. And overall, layout shows a decreasing trend in precipitation, but the trend is different from what we can observe from CF2 large ensemble. So to sum up, we still have no very clear reason for such a patterns we showed in this slide, but it seems like the AMIP simulations and the fully coupled simulations still have a very different result. And this is what we will work on later. And if you have any questions or comments or suggestions, and feel free to tell us. And that's my presentation today. Thanks for your attention.
All right, thank you. Right on time. So we have time for maybe 1 or 2 questions. If you want to raise your hand in the in your participants. Yeah. Okay. Yeah, I have a question from Isla.
Yeah, I'm sorry if I missed this. Maybe you said it, but you focused on the model and longer term trends. But when you look at the Central and the Eastern Pacific events that you were focused on in the beginning, do you find a similar difference there in the coupled model?
Sorry. You say this figures?
This was offline CLM5.
Yeah, this is offline.
Yeah, I was
CLM5.
just guessing. I was meaning kind of more generally, if you look at the characteristics of the events in the coupled large ensemble, where you can get a big sample size of all different ones.
Yeah. Okay. Yeah. So, yeah, I think to use coupled model, I mean CSM2 large ensemble is actually my next step.
Okay.
That if I want to continue this study, but yeah. So
Okay, great.
probably I didn't connect both parts very smoothly. So in the second part, it is actually
good.
Yeah, but I appreciate your suggestions. That's
It's good, and it's nice to see that CLM5 is agreeing so well with the GRACE.
yes.
Yeah, thanks.
All right, I think we need to move on to the next speaker. So our next speaker is Tinghua Ding. The talk title is Comprehensive Representation of Tropical Extratropical Teleconnections Obstructed by Tropical Pacific Convection Biases and CMIP6.
Thank you. So I'm sure everybody can see my screen.
Yes, looks good.
Okay, thank you. Yeah, so it's good to talk this as the third one is a session. Since the first two talk gave a really good overview of this the tropical teleconnection and the importance of the diabatic heating. So today, this work is led by my student from China, Fujian University, Xiaofang Feng, and other like a group of colleagues from different school and institute. So the goal of this study is to understand how model in CMIP6 capture or replicate this observed teleconnection, or called the tropical extratropical interaction on this I think this internal time scale. So here is the first slide I want to show is the 2 leading mode in observation. One is a very well-known PNA pattern, Pacific and North American teleconnection. Another one is something recently identified by a number of studies that is called we call the park mode, just like the Pacific Arctic teleconnection. So if you look at the picture of this, the structure of the 2 mode, you can find that these 2 mode basically reflect the different the phases, the relationship between the tropical region and the polar area. For the PNA pattern, we know that is the same phase, the same phase between the tropical and like the Alaska. So it's the same phase, the warming warming Pacific corresponding to the warm phase of the over Alaska. But this second mode is we think the secondary mode is like a park. That is mainly reflect the out of phase, but still same phase between the cooling here over cooling here, but like the warm phase over the Greenland. So we think there's the 2 leading mode, and the goal is to see how CMIP6 model and the CSM model capture this. The main goal is that we still think the model, as I mentioned in the first two talk, Enso is the most important driver of this global climate on many variable and field. And this is a plot I just got from IRI. And you can see this is their like hindcast verification over years and in a multi-model ensemble. And the gray area means like the model has no scale currently. It seems like no matter which season and how many lead time a model start, it seems like models still have a really weak or like a no scale over its high latitude region. Like this over North America and a large part of this Eurasia. So it seems like the model we still have a long way to go to understand why model cannot capture or cannot provide a lot of useful information for this forecast, signal forecast on this year-to-year time scale or low frequency time scale. So just to make sure this mode is robust, we start from observation, which is using ERA5 data. So to do this, we're just using monthly data, remove trend, and remove annual cycle. So just to keep like the monthly anomaly data, no trend and no this annual cycle. And we do the MCA, that is the something people also call it like a SVD analysis. So we're using two field, we just try to do MCA between two fields. One is the northern hemisphere, entire northern hemisphere, jet pressure high 200 millibar. We call it Z200 here. Another one is a tropical SST within this domain. So after we put this two field into the master, we very objectively captures the two leading mode. One is this one is very famous, the PNA pattern. El Nino drives the PNA-like pattern, but look at this pattern, there's no signal over the polar region in the Arctic. The signal, just the wave train, just when the wave train reaches the Alaska and turn back, just a return over is before it's the critical latitude. A second mode is like a cooling here and have high pressure over Greenland. So this is a mode we call the park mode. This is their corresponding time series. You can see it's a highly correlated, and this many important peak of classical El Nino is captured by Enso is captured by this first mode. This is their seasonality, or like we can think like an amplitude of this time series, because we have monthly data, so we can only look at the absolute value and group into each month. We want to see how their seasonality look like. It seems like the black one is the Enso or PNA. The PNA is if you look at the Z200 is both like the reached maximum in the summer or winter time. But if you look at the ocean temperature mode, it seems like the Enso peak in the winter is well known. But the second mode associated with the park is something like the more dominant in the summertime or non-winter season, like the non-winter season. So there's some like competition between two modes. So we expect when I first saw this result, I thought probably due to the competition between two modes, Enso always a peak in winter, and during other time, maybe the secondary mode can come to play a role when Enso is a little bit weaker. So this is my understanding, my interpretation of this result. And because we have a monthly data, and we can reform by using monthly data, we can reform like annual mean index or signal mean index, and using this from this time series. Then we can using this time series to correlate it with like the seasonal mean or annual mean data, like a surface temperature. This plot just to show you how the two different modes influence or have like a teleconnection out of the tropics. You can see it's very different because PNA is a very dominant mode, but it's mainly influenced Alaska region, and over Eurasia is quite like the trivial, no signal. But like a park is mainly like Northeast America, Northeast Canada and Greenland, and a part of the interior of Eurasia, and also like Indian monsoon or like the Middle East region. So we know this two mode is important, both important, but the response for the climate anomaly over different area. So another thing I want to mention is that this park mode is important not only for year to year, but over long time scale. So this, when we do the calculation, we remove trend, right? But if you look at the raw trend over the same period, you can still find that this second mode shows pretty strong similarity to this long-term trend in Z200 and this SAT. So we think that the reason is that this mode is not only year to year, but also low frequency. So this mode imprint really strong signal over the like 40 years of variability. So that's why this a long-term trend over 40 years. So not only due to the anthropogenic forcing, but also have some signal from this park mode. This is the idea. And also try some longer data because ERA only, the older version of ERA only has like 40 years. We are trying like a ERA 20th century. So we have 110 years to, it's the same procedure to process data and do MCA. So we find the still two leading mode pop up. One is a PNA pattern. Another one is a park, similar mode as a park. So this park mode is featured by high pressure in over Greenland, close to Greenland, and another high pressure in the Central Pacific. Another one is over like Indian monsoon region, or like along the 30° over Eurasia, but corresponding to the cooling signal. So you can see there's a pretty strong like a decadal or multi-decadal variability, and this is really corresponding well with this another peak of like the over 1940. We still don't know why, but we think the model should capture this mode if we think we want to using model to do like the more like a multi-decadal prediction. Another thing I want to mention is that this mode is the really dominant, even in last year, it's a pretty simple idea, just like to do the annual mean Z200 over 2020 and 2021. We know over the last 2 years, La Nina just dominant over the Eastern Pacific, but the two La Nina is different. One La Nina 2020, just a simply annual mean minus like a 40 years average. And this La Nina is quite like a classical La Nina, and corresponding to this one, if you look at the Z200 anomaly in the same time, annual mean data, it's like the similar to PNA pattern. But this last year, like annual mean 12 months average, is like the Central Pacific one, and with this like a park mode. The difference between the 2021 and the 2020 is more like some, this La Nina, just the difference between the two La Nina is like a strong Central Pacific cooling signal, and just corresponding to some like a park variability. So this is the observation. We're pretty confident the mode is robust. So we try to check or is the 34 historical run from CVC, one member from each run, and all available Toga, Goga, and the pacemaker run in this is the working group, led by this working group. So the process is very simple. Just redo MCA, train the data, monthly variable, remove annual cycle, and do MCA, and then compare with observation. And here's the plot to show you the 34. So the dot here means like most of model agree over each grid point. And so you can see that most of model can capture PNA pretty well. So a lot of models just agree to the example average, but for second mode, model shows really diverse skill, cannot capture this really well, and this is observation for comparison. Then we do the ISOM, that is the self-organizing map, just to help us to do something like the really objective way to clustering some 34 pattern. So we give each MCA pattern, MCA1, MCA2 to the ISOM method, and the method will tell us how to classify this 34 model to like each group. So it seems like the compared with the observation, it seems like a model do really well to capture PNA pattern. And this is a spatial correlation between each node with the observation. So you can see this triangle means a nine node all capture pretty high correlation, no matter it's Z200 or SST. But for the second mode, for the MCA2, it seems like the model cannot capture that, and really diverse. Even for some model, capture the MCA2 like the PNA pattern. So it seems like a model has some necessary skill to capture this park mode, but we know the park mode is important on this low frequency time scale. So this is the same thing, show like a very diverse. Even some, so like a node 6 is the worst one. It's like very different from like observation, observed counterpart. And node 4 is pretty good, but it's only one model. One out of 34 model can capture this pattern. So we think this is probably related to this diabetic heating bias, like the emphasized in the first talk. We think this is probably due to related to this IPO, like a second mode, or like the Central Pacific Enso mode is too weak, model cannot capture. So like a tropical rainfall cannot capture well, or like a Ross wave source associated with the second mode is not well simulated in this the current CVC model. So this is the observation related to the like the Enso. And this is second mode. So you see this is a and because the sign also changed. But a model can capture this Enso related tropical precipitation, but cannot capture this precipitation related to the second mode. And the Rossby resource associated with the second mode are also weaker than observation. Another one is we think the mean state has a bias. For this, I want to be quick, just like because we know just show the mean flow, like a U200, we know the mean flow is the provided waveguide effect for wave train to generate and propagate. And here shows like the difference between the mean flow over this box with a observation. Just a difference between the two variable. We find over JJA or 34 model. This means a 34 model or model show large bias over this domain. In other words, like this observed Wesley duct is too strong in CVC in JJA. So that means that it's a Wesley dominant region. So Enso still can play a role in JJA type, but in observation in real world, in summertime, Enso is somehow just like the muted. Things over that place is a change to like a easily flow.
It's a 12 minutes.
Oh yeah, I want to stop here. Just like we also check the mean state, like the waveguide effect are also different. And we checked the longer run, Toga, Goga, and pacemaker, especially observability, doesn't show a very significant improvement. Yeah, so this is my main conclusion. Just we think that if we want to predict, we improve our decadal prediction, we really need to improve model scale to capture the second mode. Thank you.
Yeah, thank you. Oh, we have a question from Antonetta.
Oops. Hi, this was very interesting. Thank you very much. So I was wondering, I have a very quick question. So you showed the surface temperature pattern for these two modes just in the tropics. Did you look also if like your second mode in surface temperature has signature in the extratropics in the North Pacific?
So yeah, here we only focus on the MCA method for second mode. We haven't looked at it like you mean the actual tropical signal, right? Yeah, we haven't.
Right.
Yeah.
So if you look at the surface temperature pattern over the full tropics and North Pacific, do you see also signature in the North Pacific?
Yeah, I agree. Maybe extratropical ocean temperature may also important. Yes, I agree. Yeah, we will maybe try to enlarge our MCA domain. I mean, over the tropical SIT domain to see how this global SIT relate to this teleconnection. Yeah, thanks for the suggestion. Thank you.
All right, we have time for maybe one quick question, and then we need to move
may I have
on.
a question?
Okay.
Yeah, Qinghua, very nice talk. I just want the practicability of the park mode, the second mode. Look like the tropical forcing is very weak, ST anomaly very small. So this is my first question. Second one, look like the pattern of the both the SST, also from your long time series UF analysis show that recently this pattern have a upward trend. So I just want the practicability, the first. Second one is the connection with the global warming of the mole.
Yeah, very good question. I want to answer like short answer. Yes, I think because Enso is the dominant, so MCA just mainly reflect maybe the tropical Enso variability is dominant, but that doesn't mean the Z200 is not weak, explained by the park mode. Yeah, this is my understanding. Yeah, so for second question, I think you are right, because the park is a more moderate on low frequency time scale. So I think that still contribute to I mean, not global warming, but a part of the like a land warming over some place over the past 40 years. Yeah. So
thank you.
Yeah, thank you.
All right, we're going to move on to our next speaker, which is Matt Newman. The title of the talk is Removing the Effects of Tropical Dynamics from North Pacific Climate Variability.
Yeah. To share my screen, I think.
Yep,
Okay.
looks good.
Good. Okay, thanks. This is work that was done by Yingying Zhao when she was a postdoc at Georgia Tech. She's now in Qingdao, China, where I think it's about the middle of the night. So I'm giving the talk, so she doesn't have to get up. And this is a paper that's actually come out as well. So you don't need to hear this, you can just read the paper. What we're kind of focusing on is this question, which is kind of a common thing that comes up a lot, which is how do we identify and somehow remove the effects of Enso from the North Pacific? And there's a pretty standard way to do this. It's been in the literature for decades, I think. You basically just regress on Nino 3.4 or whatever your favorite Enso index may be. You subtract the portion of the regress portion from the North Pacific anomalies, and voila, you have removed Enso. That's it, pretty simple, right? This is what a regression on a Nino 3.4 looks like from observation. So in other words, you're taking this component out of every day's or every month's anomalies. But the problem is that Enso doesn't really evolve as a fixed pattern. It's really not one constant EOF pattern, either from event to event. So we know we have different types of Ensos, or even over its life cycle, it undergoes a lot of evolution in terms of the pattern. And its impact on the North Pacific is not really fixed either. And for this latter point, we can see this by just taking that regression and extending it for increasing lead. So this is the same pattern I showed before, the 0-month regression. But you can see as you do increasing lead times that in fact the peak of the North Pacific response, of course, is not simultaneous. It actually occurs after the peak of Enso. So you can see there's a maximum about 3 months later. And this pattern persists for quite a while, but as it persists, you can see there's changes in the tropics going on. And even in the North Pacific, you can see there's this eastward progression of the centers with lag. That progression actually increases as you get to 12 months and you start getting other processes that are important, but they're acting in different sorts of ways. So reemergence, for example, is bringing back the North Pacific anomaly at longer leads, but you can see that the equatorial Pacific has flipped sign at that point. So in other words, there's a sort of a relationship between a negative Enso event in that case and this positive kind of PDO-like pattern. So that is an issue, and we need a way to try to deal with that. And I think if you take a look at actually how this regression method works, you can see that there's also a fairly straightforward problem. So here on the left, I'm showing again the regression on Nino 3.4 at increasing lead time. So this is similar to what I showed before. I'm just looking in the North Pacific. And now here what I'm doing is I'm using two different approaches that try to remove the Enso effects. We'll regress on Nino 3.4 either simultaneously or with a 3-month lead time to account for that slight difference. And in either case, so here if you regress Nino 3.4 and then remove that, and now you take the residual and regress it on Nino 3.4 again, you get 0, which is what you'd expect. You've removed that regressed component. But as you look at increasing lead times, in fact, you have not removed a component that's related to Nino 3.4 at lead. In fact, by the time you get to a year lag, it's actually, if anything, slightly stronger signal. So you essentially have put in kind of a negative component, and you now have a stronger component that's related to Enso essentially a year prior than the actual observations have. And picking different leads doesn't help, picking different indices doesn't help. It's a fundamental problem that's basically related to the fact that we're trying to do this regression off of a single index. So what we're arguing then is that it's better not to regress on a single index, but rather to try to come up with a simple dynamical system that matches the observations and then decouple the tropics and the North Pacific. And that's what we're showing here. So we're going to write the Pacific monthly variability in this very simple linear stochastically forward system, where in this case it's x sub t is any tropical anomaly and the x sub n is any North Pacific anomaly. In our case, we're using detrended monthly anomalies of SST and SSH. And you can get this dynamical operator here and the statistics of the noise from a technique called a linear inverse model. I'm not going to explain that. If you haven't heard about it, I strongly urge you to look up papers and read about it. But it's a very good match to observations generally, and in fact, you can use it to forecast with the same level of accuracy as GCM. So it's a good representation of the system on these timescales. So this is our system. Now we want to focus on the North Pacific dynamical system part of that. So we're going to have essentially an internal dynamics in the North Pacific and a component where the tropics are forcing the North Pacific. And obviously this is the thing we would like to remove, to remove all the tropical effects, to see what the internal North Pacific dynamics would yield on their own. So in this case, it's pretty straightforward. We can just decouple our system by setting these off diagonal submatrices. They're not scalars, these are all matrices. Set them to 0. So this term in particular, we set to 0. And now we have what we would call a decoupled North Pacific dynamical system, which we were sometimes in the paper and in the figures here calling an MP only limb. So the idea here is that we can use this system to understand what variability we would have in the absence of the tropical Pacific, what variability in the North Pacific we would have in the absence of the tropical Pacific. And just to show how that this is working, I've repeated the calculation that I showed earlier, but now I've used this decoupled limb, this North Pacific only dynamical system, and rerun it, generating data that's consistent with that system. And then basically saying, okay, now if I take that and correlate or regress that North Pacific anomaly with Nino 3.4 at any lag, what do I get? The answer is I basically get nothing. So essentially I've now entirely removed the effects of Enso at all lags, not just simultaneous, not just at some lead, but at all lags from the North Pacific. So I've done a much better job than these simpler regression techniques. All right, so what does that mean in terms of the overall variability then? Well, here's the total North Pacific variance, again, from observations. And this is the result that I get from my NP only limb, from my North Pacific only dynamical system. And this is showing the proportional reduction. So basically what we're seeing is we're getting as high as 50%, more like 30 to 40 here, but up to about 50% reduction in variability in the eastern part of the basin and in this region, which basically is where the subtropical front lies, kind of northeast or northwest of Hawaii. And again, one can see that this is a much larger decrease than you would get from these simple univariate regression techniques. So these kind of techniques are really underestimating the tropical impact on the North Pacific. And that's because they're forcing that tropical impact to basically be coming from a single pattern and basically operating on a single time scale. And when we allow that impact to come from multiple patterns and multiple time scales, we see a much bigger tropical effect. Now, another nice thing we can do then is we can ask, what would the dominant mode of North Pacific variability be in the absence of Enso, right? So here's the leading EOF, the North Pacific, the shading representing the SST, the lines representing the SSH regressed onto the PC, the SST PC. And so this is this typical PDO pattern. However, when we decouple the system in this way and we remove all the tropical effects, what we're left with is something that's very much more reminiscent of a KOE kind of structure. So the Oyashio, Kurashio Oyashio extension coming out here, there's a very strong SST gradient in the ocean right here, the subarctic frontal zone. And basically what we're seeing then is that the main locus of variability would really be lying right along that frontal zone. You can see there's also almost a complete removal of this anomaly to the east. This looks very, very similar to what you get if you were to regress SST onto, say, the leading EOF of the position of this frontal zone here, which is work that is in papers by Young-Oh Kwon and Claude Frankenwald. And interestingly, also this EOF, this dominant pattern now actually is less persistent than this PDO pattern. So in other words, in the absence of the tropics, we're going from a PDO pattern to a KOE pattern, which is less persistent. And then maybe not entirely surprisingly, there is a lot less decadal variability. So in fact, the decadal variability is even more reduced than the overall seasonal variability. And again, we can see that that decadal variability in the absence of the tropical Pacific is lying really focused again in this KOE region right along the frontal zone. And again, that makes dynamical sense. It's going to be a region where oceanic Rossby waves, which are going to have a longer time scale, are going to play a particularly important role. Okay, that was observation. So how do the models do? First, we can look at how the models capture the PDO. So this is just a simple Taylor diagram, basically looking at individual CMIP6 models. In the diamonds here, the pink and orange are just different models. The pink are supposed to be better models compared to the observed PDO. And if one were curious, so how is this compared to CMIP3 and CMIP5? It's basically about the same. This kind of relationship really hasn't changed. The gray dots here are essentially generating synthetic samples from this dynamical system, this limb that I discussed earlier. So the dark gray dots are the top 90%, the 90% of samples that are closest to the observed, and the light gray dots are the remaining 10%. So this is basically a way of saying that we can say with at a 90% confidence interval that none of the models reproduce the observed PDO. And actually, if you get to the 95% level, then almost none of the models do. I think there's 2 here which do, and I don't know if they're 5% of the models, so that may not be significant either, but maybe they're just better models.
At the 12-minute.
Thanks. Anyway, so how are the models doing then in terms of the variance? They have way too much variance relative to observations. And you'll notice it's much more in this KOE region. When we do the same technique where we remove the tropical impact, we get very little change. We're really basically not seeing much of a tropical impact in any of the models, either in aggregate or for the most part individually. You can see there's no change in particular along the eastern part of the basin here. And if we look at the dominant mode of variability in the models, again, it's basically a KOE pattern with the tropics, and it's a KOE pattern without the tropics. And the effect of the tropics is basically to make this pattern somewhat more persistent. In other words, it's actually acting as a bit of a damping on what appears to be an overestimate of variability otherwise. All right, so just concluding, we're basically illustrating here that you need to do a multivariate approach if you want to identify and remove Enso impacts upon North Pacific or really anywhere. Enso has too much spatial and temporal variability, and it's a forcing of the North Pacific. So you need to be worrying about the lags, and those different time scales are also entering into it. It appears that the tropics then is important for a fairly large fraction of variance, particularly decadal variance. And without Enso forcing them, the dominant pattern of variability would really be more of a KOE pattern. But in CMIP6 models, the dominant pattern of the North Pacific variability already is a KOE pattern, which I would argue is being mistaken for the PDO. So if you're interested in this, you can read all about it here. Thanks.
Great, thank you. Any questions? Yeah, I see a question from Clara.
Hi, Matt. Thanks for such a superb investigation and talk. Just quick question. If I'm interested only in the simultaneous DJF Enso teleconnection on the North Pacific atmosphere, do I have to worry about doing this procedure?
Well, I think it's a timescale issue, right? The North Pacific is doing a lot of integration of the atmospheric bridge from the tropics into the North Pacific, right? So there's too many timescales that are involved there, and that makes this important. But I would basically argue you'd have to do something similar, just maybe on a faster timescale for the North Pacific atmospheric response. And in fact, we have a paper where we showed this to be the case for the NAO. And again, it comes down to the fact that the patterns are not really orthogonal. The real dynamical modes in the system because they're not orthogonal, you get similar patterns with very different time scales in terms of the dynamical linkage, say from the tropics into the North Pacific. And you can't just pick one, because other modes may be acting to interfere either constructively or destructively, and that's giving you a lot of that evolution. I think this is generally true. This is true for the PNA. Steph Henderson, Dan Weimann, and I did a paper kind of illustrating this, that there's an Enso component and an MJO component and an internal exotropical component. All have similar patterns, all have different timescales. Again, you have to be very careful about these simple univariate regressions.
Thanks.
So unfortunately, we need to move on, but any additional questions that you have for the speakers, feel free to add them to the chat so you can interact that way. So our next speaker is Kay McMonagle, and the talk title is Enso explains the link between Indian Ocean dipole and Meridianal ocean heat transport.
All right. Thank you, Sarah. Can you see my screen?
Yeah, looks good.
Okay, so this will tie in really nicely with the previous talk. This is work that I did with Sarah at NC State, and it's recently published in GRL. Okay, so we expect generally in the Indian Ocean that variability is going to be strongly related to Enso. But we also know that there are other modes of internal variability to the Indian Ocean that exist. So some of these are the Indian Ocean dipole, the Indian Ocean basin mode, subtropical Indian Ocean dipole, and the Ningaloo-Nino. And I'm mostly going to focus on Indian Ocean dipole, or IOD. And in a model, the positive phase of IOD looks something like this, where the colors are sea surface temperature and the arrows are the wind stress. So you have warm sea surface temperatures in the West Indian Ocean and cool sea surface temperatures in the East Indian Ocean. But if you look at the Pacific, you can also see that there's some sign of Enso in this. And so generally, it's hard to separate out these various modes of variability from Enso because Enso is so dominant. And in observations, this is difficult because they tend to be short. So we can do long model runs to try to get more years and look at the statistics. But we run to the problem of deciding what is Enso. So a little bit similar to the previous talk, how do you decide what is Enso and how do you remove it? So one thing you could do is a linear regression of something like the Nino 3-4 index, but I think the previous talk probably convinced you that's not enough. And we know there are nonlinearities in the system that won't be removed by some sort of linear regression, either at zero lag or at a longer lag of the Nino 3-4 index. You could also try some sort of timescale filtering, but we know that Enso can project onto lower frequencies. And then for these Indian Ocean modes, we also know that they occur in similar timescales as Enso. So you might end up removing some of what you're interested in. And so this is particularly relevant for the Indian Ocean because the 2019 Indian Ocean dipole was a really extreme positive Indian Ocean dipole event. And it occurred without an El Nino event. And in comparison, many of the IOD events in the historical record have occurred at the same time as an El Nino. And so if we take a look at what the 2019 IOD looked like, you can see similar to what I showed from the model, we have warm sea surface temperatures in the West Indian Ocean, cool sea surface temperatures in the East Indian Ocean, but now there's no Enso signal across the tropical Pacific. And so this brings up the question of whether we think that this IOD event and other IOD events that occur without Enso might have different impacts on the ocean than those IOD events that do occur at the same time as El Nino. And so one way we can quantify this is by looking at the ocean meridional heat transport and seeing what impact IOD has on that. And a previous paper looked at heat transport anomalies during IOD positive years and did a composite to argue that there are anomalous ocean heat transports driven by IOD. But looking at these various years they used, you can see that quite a few of those were El Nino years. And so it's difficult to separate out whether this is truly IOD or just Enso. And so what we did to take a look at this is we compared two models within CESM1 CAM4. So we had land, cryosphere, atmosphere, and ocean models with a nominal 1 degree ocean resolution and 60 vertical levels. And this was all done with pre-industrial forcing to focus on the natural variability. And the two models we're going to compare are the fully coupled model, which I'll call control. So in that we have all of the physics that's resolved by the model. And then we're going to compare that to a model where Enso has been dynamically removed, which I'll explain in just a minute. And I'll call that the no Enso model. And we have a little bit more than 300 years from each experiment. Okay, so what did we do to dynamically remove Enso? Within the coupler, we overwrote the time varying wind stress forcing with a climatology wind stress taken from the fully coupled run. And we do that across the tropical Pacific. So where this red is with a slight, little bit of a buffer zone to avoid anomalous wind stress curl signals. And so if you do that, it destroys the Bjerknes feedback because the ocean and the atmosphere are no longer coupled and Enso events cannot develop. And so this removes both the direct as well as any indirect effects of Enso. So you can imagine if Enso were to lead to some sea surface temperature anomaly, and then that feeds back onto the atmosphere, that's something that would also be removed through this process. And so for instance, in comparison to pacemaker experiments, this experimental setup is going to maintain thermodynamic coupling. And we also have anomalous heat transported by the Indonesian through flow. So if we're thinking about the Indian Ocean, we have the impacts of the atmospheric bridge, as well as kind of the ocean tunnel effect through the Indonesian through flow. And so first we can look at the spectrum of Nino 3.4 in the models to confirm that Enso has been removed. So in control, we have a really strong peak at about 4 years. Enso is a little bit too regular in this model. And then in the no Enso model, there's really strongly reduced power at all frequencies. There is still some variability in tropical Pacific sea surface temperature in the no Enso run, but it's thermally forced and it's much smaller than in the control. And we can also take a look at IOD in both models. So the top panel is that pattern of IOD in the control model, which I already showed. And then below is the pattern of IOD in the no Enso model. And there are some differences between them, which I'll come back to. But generally speaking, you can still see that there's warm sea surface temperatures in the west, cool sea surface temperatures in the east, but we no longer have the Enso signal across the Pacific. There are less IOD events after we remove Enso by about 20%. And so this suggests that some IOD events are Enso forced, but that most IOD events are not Enso forced. Sorry, my cat is being annoying. Okay, so then we calculate the ocean meridional heat transport as a function of latitude in each model. And we can first look at the time mean. So our two models are the black and the blue lines here. So latitude is on the y-axis, and then meridional heat transport in petawatts is on the x-axis. And the gray line and the black dots are the observational estimates we have. So there's kind of reasonable agreement to the fairly limited observations, but the more important part is that the mean state in each experiment is very similar, so we can compare the two experiments to see what impact removing Enso has. So now if we look at the meridional heat transport variance as a function of latitude, the black line here is the control model and the blue is no Enso. We can see that variance is reduced at all latitudes across the Indian Ocean. And on average across all latitudes, the variance reduction is about 33%. And the greatest variance reduction is near the latitudes of the Indonesian through flow, which makes sense because the Indonesian through flow is really strongly, the variability is strongly dominated by Enso. And so next what we can do is look at the relationship between the meridional heat transport and Enso as well as IOD. So if we start on the left side here, this is in the control model. As a function of latitude and lag in months, the correlation between Enso and meridional heat transport. And the stippling here is areas that are significant. So in control, there is a positive correlation with Enso leading by a couple of months, leading the meridional heat transport across the entire South Indian Ocean. Then we can do something similar, but looking at the correlation between meridional heat transport and IOD. And the correlations are a little bit weaker, but you still see this positive correlation with IOD leading by about 2 to 3 months. We can make the same calculation now of the correlation between meridional heat transport and IOD in the no Enso model. And although there are still a few areas where there are statistically significant correlations, there are much lower correlations, and most of the areas of significance are no longer significant. And that was all done over all months, but we know that IOD is mostly active in August, September, October, November. So we can calculate the zero lag correlation between the meridional heat transport and IOD as a function of month. So on the left, this is in the control model, and there are strong correlations between IOD and meridional heat transport from September all the way through to March, so the boreal winter months. And then if we do the same thing in the no Enso model, we can see that there are some areas that there's positive correlation between IOD and meridional heat transport between August and November, but it's much more latitudinally limited. So rather than being across the entire South Indian Ocean, we just see positive correlations between the equator and about 15 degrees south. And so this leads to the question of why do we see this relationship between meridional heat transport and IOD when Enso is present and not when Enso is removed? And that's because there's different wind stress patterns that are associated with the Enso forced IOD and the internal IOD. So going back to those IOD patterns in each model, now I've put the difference between the two at the bottom. And we can see there are some sea surface temperature differences, particularly off the coast of Australia. But the biggest difference between the IOD patterns in the two models is this anticyclonic wind stress anomaly over the South Indian Ocean. And in the paper, we calculate the geostrophic and Ekman temperature advections, and we can see that that explains the different relationship with meridional heat transport really well. And then lastly, that leads to the question of if this internal IOD is not causing heat transport variability, what is causing heat transport variability in the Indian Ocean besides Enso? And so to look at that, we calculated the EOF of the meridional heat transport as a function of latitude. And this is what the pattern looks like in control. The pattern ends up looking a lot like Enso, so I'm not going to show that. But in the no Enso model, we can then take our principal component time series and regress it onto sea level pressure and 500 millibar height, which is shown in this panel C, and then sea surface temperature and wind stress shown in panel D. And what we see is something that looks like barotropic internal atmospheric variability across the South Indian Ocean. And this principal component time series has a weak, although statistically significant correlation with the subtropical IOD and the Ningaloo Nino. So it's possible that those modes are playing some role, although neither of them seems to dominate. So in conclusion, we find that the internally driven IOD does not cause large-scale anomalies in Indian Ocean heat transport, but there is an apparent relationship if you look in something like composites, because Enso can force both IOD and the heat transport. And we also find that the Enso forced IOD and internally generated IOD have different wind stress patterns and therefore different impacts on the ocean. And specifically, we looked at heat transport, but I think that this might also be true for more of ecosystem kind of impacts for things like upwelling. It would be worth taking a look at. And if we think in terms of predictability, these Enso forced IOD events have higher predictability and also seem to have more impact on the ocean, while the internal IOD events that have lower predictability have more limited impact on ocean variability. So in terms of predictability, that's an ideal situation where the events that seem like they're mattering more are also the ones that are easier to predict. And I'll take any questions. There's more details in the paper, or feel free to send me an email. Thanks.
All right, thanks, Kay. Any questions? All right, one from Isla. I see one from Isla.
Yeah, I don't know if this is a question for you or for Matt, but I mean, presumably this could be used to kind of verify the more statistical methods that Matt was using. Yeah, have you looked at that?
I haven't looked at that, but yes, I think that's a very good idea.
Okay, great.
Was there another question?
Yeah, if I could figure out the hand thing, I would have done that. But I just have a real quick question. Did you look at the base state? Is the base state in the tropical Pacific or Indian Ocean for that matter, but the tropical Pacific, is it any different? I mean, you're removing Enso, so is Enso doing anything to maintain or balance or somehow alter the overall time mean basic state?
Sarah might have more detailed answers, but I think basically the basic state looks like a very weak La Nina state because it's not totally symmetric. But is that correct, Sarah?
Yeah, I had a grad student who looked at that last year, and the fully coupled runner case control is just a little bit warmer in the East Pacific because of the El Nino events being stronger than La Nina. We think that's projecting onto the mean state a little bit.
I have a question, if I can raise my hand, but maybe.
Yeah, Antoinette, if you have a quick question.
Yes, so in the IUD induced by Enso, is the influence mainly through the Indonesian through flow, just because you have changes in the winds along the equator that can affect the Indonesian through flow, or is it through the atmospheric teleconnections?
That's a good question. I don't know for sure. I didn't decompose it either way. I think that it's probably strongly related to the winds over the South Indian Ocean, but I didn't specifically look at what role the Indonesian through flow variability plays.
Okay, thank you.
All right, thanks. We need to move on to our last talk of this session from Melody Liu. The title of the talk is Mechanisms of Fast Walker Circulation Response to CO2 Forcing.
Okay, can you all hear me?
Yes.
And I can see the screen, right?
Yes, looks good.
Okay, so thank you, Sarah. I'm Melody Liu, and I'm a PhD student from Georgia Tech. Today, my topic will be mechanisms of fast Walker circulation in response to CO2 forcing. So to start with, we are wondering, as the global CO2 increases, are we going to have a weakening or a strengthening of the Walker circulation? So the Walker circulation response to CO2 forcing has been done for decades. And so most climate models all project a long-term weakening of the Walker circulation in response to CO2. So for example, in this very classic Helen and Stoughton paper in 2006, so they compare both the changes of the global mean column integrated water vapor, which is shown on the left, and compare that with the global mean precipitation changes, or like regress onto the global mean changes of surface temperature. So from the left, you can see from the Clausius-Clapeyron relationship, there will be about 7.5% per Kelvin increase of the water vapor. However, if you look at the precipitation, this increase will be much less. And in their paper, they explain with a weakening of the Walker circulation, which leads to this decrease of the precipitation. However, if we look at the observational data set, they will be a little bit different. For instance, in a recently published paper by Wu et al., they look at the SST and lower level wind, surface wind trends from the observational data set. And then you can see there's actually has a cooling trend in the equatorial Pacific and also a strengthening of the westerlies in the tropical Pacific. And then they explain this is because the strengthening trend of the Walker circulation might be contributed to by the internal variability. For instance, they regress the Walker circulation trend to the interdecadal Pacific Oscillation Index, and then they find a negative correlation here. Okay, so for most of the research, the response to CO2 forcing of Walker circulation can be decomposed to a slow and a fast components. So we do so is because different mechanisms drive the Walker circulation changes at different timescales. So for instance, if you give a perturbation to the atmosphere, so the atmosphere will start to react first, and the first thing will have a decrease of the direct radiative cooling. And then you will have a rapid lengthy thermal contrast and then related spatial pattern changes of SST. And as time goes by, these changes will influence the ocean. And then the ocean will slowly warm up, which might take about centuries or even like 1,000 years. And then as ocean become the dominant forcing, it starts to force atmosphere, which will increase precipitation. So how do we separate fast and slow components? There are like traditional, there are two ways. So the most universally used technique is use fixed asset experiment. Used technique is use fixed asset experiment. So where you have a atmospheric only experiment and you force with different forcing agent, like the warming of SST pattern, or like the mean state warming, or just by the changes of radiate forcing. Or there's another way you can use a fully coupled simulation with abrupt forcing. And then you take the first few years where you have mostly atmospheric changes and the rapid air-sea interaction changes in the beginning as the fast response. And then you take about the last year greater than your 100, or like the last 30 years of your total simulation as a slow response. So after we know the fast and then the slow components of the studies, so I first look at some of the fast changes in the SIMI-5 models. For instance, what is shown here is a changes in SST, which is a shading here, and the surface winds as vectors average over the first 2 years of abrupt forcing in the SIMI-5 models. So as you can see, there are some models, they present a very similar cooling pattern in the beginning when you abrupt forcing. And there are some other models, they don't have those features. So I started wondering what contributed to this intermodal discrepancy in the fast Walker circulation changes. And the second motivation is because most of the studies related to the fast and slow changes of Walker circulation, they use the decoupled models. So the interaction between the SST and then the atmospheric responses are really studied. So for the method, I take a look of both SIMI-5 models and CSM1 models. So for SIMI-5 models, I use all available 27 models from abrupt full-time CO2 experiments. And I separate these models into a co-group model, which I name as SIMI-5 CG, and a warm group model, which I name as SIMI-5 warm group WG. And I will come back to this separation in a minute. And I also have a large ensemble experiment in CSM1 with abrupt full-time forcing. So the way I design this experiment is like the following. So first I have a pre-industrial control run that are running for 160 years. And then I have a abrupt full-time CO2 simulations that branches off at different years or in the January. I try to separate them as much as possible so that I can collect as many internal variability signals as possible. And then I subtract the control from each individual full-time CO2 run, and I average the ensemble differences. In the end, I will have 120 ensemble members for the first 2 years after abrupt full-time CO2 forcing. So in this experiment, there are some notations here. So all the changes are defined as the experiment between the abrupt full-time CO2 experiments minus the pre-industrial control. And the total response is defined as the changes average over the last 30 years of the simulations. And the fast responses is defined as any changes happening within the first 2 years. And the slow responses is from the total response subtract the fast responses. So let's look at some of the results. Oh, so before looking at the results, there's how I separate the SIMI-5 co-group and the warm group. So the way I do it is I first calculated the SST changes in the Nino 3.4 region among all 27 models in the first 2 years, and then ranked them by their relative strength, relative magnitude. So I grouped the first half, the first lower half as SIMI co-group, and the second half as the SIMI warm group. And as you can see, the CSM1 or like similar model CSM4, they are belong to part of the co-group models. So let's look at the results. So for the fast response, in the first months when we abrupt full-time CO2, you can see there's pretty little changes in the ocean, but because of these like a very rapid lengthy thermal contrast, you will see a landward winds in the both maritime continent and also in the South American. And then this is happening across all 3 model groups. However, 6 months later, you can see that in the CSM1 large ensemble group and the SIMI-5 co-group models, you can see a very persistent Central Pacific cooling pattern and a very strong anomaly easterlies present. However, this thing does not happen in the SIMI-5 warm group. So now I'm starting to wondering, so what causes this fast response intermodal spread? And then the first guess is, well, is this discrepancy robust? In other words, is this due to the internal variability? So in order to do that, I perform a Monte Carlo method. So for instance, this plot shows the changes of the water circulation strength calculated within the 2 months evolution here. And the color bars are the strength. And this error bar is the internal variability obtained from the Monte Carlo method. If the color bar is bigger than the error bar, that means the response is robust. So as you can see, for both CSM1 large ensemble and co-group, the response is pretty robust, which means it's not contaminated by the internal variability. And so the second question will be, does the parent pre-industrial control simulations Enso state matter? So which means when I'm starting to do my abrupt full-time CO2 experiment, what if I abrupt my CO2 right in places where the Enso is happening? So in order to quantify these, I calculate all the initial Enso state where you started to abrupt full-time CO2. As shown in this table, the E events denote where the El Nino is happening when I quadrupling the CO2, and the L denotes there's a La Nina events happening when I quadrupling CO2. So you can see, so for all the models in CG or WG, it doesn't really matter if your pre-industrial control is having an Enso state when you start your abrupt full-time CO2 forcing, but you can see that the semi-5 co-group models, they do have a little bit more Enso events happening when you are doing your abrupt forcing experiment. So the answer is maybe no, but it needs a little bit more investigation in these assumptions. So and then the third hypothesis is the discrepancy due to the different lengthy thermal contrast among models. So which means if a co-group model has a stronger lengthy thermal contrast so that they can trigger more surface wind response in the beginning. So in order to test this, I plotted the surface wind responses the first 3 months and plotted against the lengthy thermal contrast within all the semi-5 models and also the CSM1 large ensemble. So from the plot, you can see the relationship, there's no relationship between the lengthy thermal contrast and the surface wind response. And the last hypothesis is maybe the model simulate different air-sea coupling strengths. So in order to test this, I quantify the model air-sea interaction strengths in their pre-industrial runs. And I developed a mathematical framework based on the SST tendency equation, which I will not go into details here, but you can read it in the paper. So from this framework, we can quantify the thermodynamic feedback index and the Bjerknes feedback index, and also the zonal advection feedback index. And then the total feedback index, which measures the total air-sea interaction strength, is the sum of these 3 index. So let's look at the air-sea coupling strengths from all different models. So from this plot, you can see co-group models in general has a much larger Bjerknes feedback index and a much larger zonal feedback index, which results in a higher total feedback index compared to the warm group, which means the co-group models in general simulate a stronger air-sea coupling. And also the Bjerknes feedback is easier to be triggered in the co-group models than in the warm group models. And interestingly, I also did a comparison between the CSM1 large ensemble and the CSM2 large ensemble. So I did a similar large ensemble experiment in the CSM2 as well. And I compared their fast response in the first 2 years. So interestingly, not as the CSM1 version, the CSM2 version does not have a very strong cooling pattern in the beginning, also does not have a strong westerly anomalous in the Western Pacific. And then I also calculate their air-sea coupling strengths. It turns out to be in the CSM1 version models, it has a larger air-sea coupling strength feedback compared to the CSM2. So moving from the fast to the slow responses, if we look at the semi-5 warm group, you can see the responses, the changes from the fast to the slow is pretty monotonic. They just like the sea surface keeps warming and it keeps warming. However, for the co-group models, there will be a little bit interesting thing happening. So in the beginning, in the first 2 years, when you have a very strong anomalous easterlies, it keeps piling up warm water in the Western Equatorial Pacific. And then as your background keeps warming, these easterlies started to weakening. And then this warm water was accumulated before they started to transport towards the east as a downwelling Kelvin wave. And these warm water bulges will gradually wash away these anomaly patterns. And eventually they will reach out in the same slow response pattern, which is shown here. So the slow responses generally features a weakening of the Walker circulation, and the pattern changes SST and the wind is kind of similar across the groups.
Here, 12 minutes.
Yeah. So the take-home message here can be summed up by this diagram. So the changes of the Walker circulation in the fast response period is different, but the slow response period was kind of similar. So in the fast response period, when you just give the impose the forcings, they will form a rapid lengthy warming contrast, and these will trigger a landward winds in all groups models. However, in the co-group models, because they have a stronger air-sea coupling feedback in their model structures, they tend to trigger Bjelknes feedback, then what tends to lead to a strengthening of Walker circulation. However, in some other models where you don't have a strong air-sea coupling feedback, then they won't trigger this Bjelknes feedback. Instead, they will just keep warming. And then as the background keeps warming, these strengthening of the Walker circulation will eventually be washed away. And then eventually the dominant forcing will just be the mean warming of the SST. Yeah, this is my talk. I'm happy to take any questions. Thank you.
Great, thanks. I saw the first hand from Zhang Zhen.
Very nice talk. I just have a comment about the fast response. Right now, I believe that a majority of CMAP5 model are able to capture the Enso frequency. So that probably a factor in addition to the pattern associated with the Enso. Also, the frequency may be a factor lead to the difference among different models. So just a comment.
So it's a really good comment. I actually looked at they're like Enso intensity and the frequencies in all the CMAP5 models, and I look at their both index in different group of models, and it turns out to be actually the co-group models tends to have a little bit more like realistic Enso frequencies than those like warm group models. So yeah, I think it has a little bit relationship, but I don't know if there is a true physical link between the Enso and this response. But yeah, this is a good comment. Thank you.
Thank you.
Yeah, Clara?
Yes, hi. What a wonderful talk and presentation.
Oh, thank you.
I learned so much. Just a quick question, maybe related to the previous one. Where do you think the observations lie in terms of the strength of their, Bjerknes feedback and other coupling strengths?
Yeah, good question. I also did a calculations regards so with the observational records and compared to the model results. I didn't put a plot here, but the answer is actually the observational. They have a much stronger air-sea coupling index compared to both groups. And then the curve group models tend to be a little bit more close to the observational data set. But not every single co-group models did a good job. So like just some will be a little bit closer to the observational results, but some are not. But if you take an average of all of them, it tends to be co-group simulate a little bit more realistic air-sea coupling strength in this scenario.
So in that regard, CSM2 would be more realistic than CSM1?
So the thing is CSM, This is the CS comparison CSM1 CSM2. So actually, I think CSM1 is a little bit more closer to the observational than CSM2.
Thank you.
Yeah.
All right, it's technically the break, so if anyone needs to go and stretch their legs, that's fine. But we can go ahead and take a final question. Matt, I see your hand is raised.
Yeah, thanks. Yeah, it's interesting to try to really stratify it that way. I really find that very valuable. I do have a question about how we apply it to the observations, because of course, have we been in a fast response for about the last, I don't know, 30 years? Or does it even make sense to compare these kind of experiments to the real world in that sense? I don't have a good sense of that time scale, I think.
Yeah,
it's been 30 years and nature hasn't caught up to where the models are in terms of the supposed weakening of the Walker circulation.
So I think for the observational data, like the biggest challenge is you're looking at both the responses to all the forcing agents and also the internal variability. So it's a little bit hard to disentangle these two components. So as like I previously showed from the paper by Yu et al., they found these like a strengthening trend of the Walker circulation are mostly contributed by the internal variability like IPO index. But I think it's like what we know is it's kind of like a tug of war between the internal variability and the force response. Because in my setup of experiment, I give a very strong forcing, which is like way overpowering the actual like observational data, right? But I think like from my setup of the experiment, you can at least like, get a sense of our current climate models and doing a consistent job in simulating the responses of atmospheric circulations. Yeah, but I do agree. I'm also like very puzzled by like these like model and observational discrepancies.
Yeah,
but I
mean,
yeah.
I mean, I think that it's always been striking to me that it's when the global temperature really started rocketing up that we started getting a strengthening of the Walker circulation.
Yeah.
So if that's all internal variability, yeah, it's an interesting coincidence. And if it's not internal variability, then what's the time scale of this fast response supposed to be then? So anyway, very interesting. Yeah.
Thank you.
Isla, do you want to make any announcements?
Yeah, just to say that we are going to have breakout rooms available during the break. So if anyone wants to go and have a chat with anyone about work or social, you can feel free to go into one of these breakout rooms. I guess otherwise we'll reconvene at 10:30, I believe, Mountain Time. So 20-minute break. Hi, Shu, are you there?
Yes.
Okay, did you get my message in the chat? That Youngo is going to.
Check.
Youngo
Okay, yeah, I just yeah.
Okay, so you're going to chair this session.
Okay. Oh, let me see. So that means that the first talk is not presented by the Jiarui Shi. Instead,
No,
it's Yang. Okay.
Youngo. So yeah, I think we should get started if you want to kick it off.
All right. Hello, everyone. Welcome back to the second session of Winter CVC WG Working Group Meeting. This session, we will have 6 presentations, and each talk will be 15 minutes, and hopefully you can finish it at 12 minutes. We can have a few minutes for questions. The first talk, it will be presented by Yang. The title is 2 distinct modes of climate response to anthropogenic aerosol forcing changes. Okay, Yang, please go ahead.
Thank you, Aishu. Can you see my slide?
Yes, but right now it's not in the presenter mode yet.
How about now?
Now it's not full screen, and because now it's showing 2 screens. One is for the audience, the other one is for yourself, I guess.
So it's not working yet.
That's right.
I think if you just
now
yeah,
it's fine.
okay.
Perfect.
It's perfect. Okay, thank you. Okay, so my name is Yang Kwon, and this work is led by Ray Shi, who's a postdoctoral scientist working with myself and Susan Riffle. And Ray was supposed to give this talk, but he had a last-minute emergency, so I am presenting his slide. So let me start with a just broad introduction. So anthropogenic aerosol forcing acts as a cooling agent, unlike the greenhouse gas forcing, which induces warming. And it's not just affecting the temperature, but also affecting the circulations. So on the right-hand side, we have a plot from Ray's PhD paper with Xiangping Si and Lintelli in 2018. I would like to draw your attention to 2 curves, that the red, which is greenhouse gas-induced AMOC change, and the light blue, which is anthropogenic aerosol-induced AMOC change, and they are opposite in sign, and the amplitude is more or less comparable. And one characteristic of the anthropogenic aerosol forcing is it's spatially heterogeneous and temporally non-monotonic. This characteristic has been emphasized by many previous studies, including Clara de Just 2020, as shown on the left side. And today we would like to use the same simulation that Clara used, but extend the study to 2018 to the end of the run. And I'd like to point out 2 particular aspects of the aerosol forcing evolution. So over the Europe and North America, the aerosol concentration increased until 1980, and then began to decline as the Clean Air Act became effective. And unlike that, for the Asia and tropics, the aerosol forcing peaks around 2020, and it's projected to decrease afterwards. So aerosol forcing is dependent on the regional concentration evolution. However, the effect of aerosol on climate has been mostly studied as overall one effect and compared to the effect of greenhouse gas forcing. So the question we want to address with this study is that is it possible to decompose the effect of anthropogenic aerosol on climate change into the multiple mode? And the answer is yes, because the key aspect is the spatial and temporal information, and we can use that to accomplish this goal. And we're going to focus on the anthropogenic aerosol effect for the rest of the talk against the background internal variability. And we're not going to touch anything about the greenhouse gas forcing. So the data we used, I already mentioned, it's same as Clara Deja's 2020 study. So we use CSM1 large ensemble 40 member and then CSM all but one forcing, the X aerosol forcing 20 members. And based on Clara's formulation, we can create aerosol single forcing ensemble. And we're going to use this 20 member aerosol single forcing ensemble for the rest of the study. So then we apply so-called signal to noise maximizing pattern filtering to this aerosol single forcing ensemble. And this method is used by Robert Wills et al. 2020 study, and it's very effective in isolating forced signal from internal variability signal. So to do that, the first step is concatenate all the 20 members, for example, for SST, into one single so-called ensemble data matrix X, and then perform EOF on that data matrix X. The right-hand side shows the result from that EOF, the top 3 EOF mode. The leading mode is Enso, of course, and it's dominated by internal variability as shown on the right-hand side time series. The gray are the time series from individual member, and the black is the ensemble mean of 20 time series. Then EOF 2 and 3 have more contribution from the forced signal, but the signal to noise ratio is still around 1 or less than 1, meaning the internal variability has substantial contribution as well. So the EOF alone is not effective in isolating forced signal from internal variability. So we need some additional steps. So we use the eigenvectors from these EOFs, A, and then scale it by sigma, which is its square root of its eigenvalue. And then we do linear combination of the n eigenvectors or EOF modes using the E vector, which is the coefficient vector for this linear combination, which is to be determined using the signal to noise maximizing method. And with U vector, we can project that onto the full data matrix and get the time series. And then we define the ratio between the forced signal and the total variance. And this becomes a maximization problem, and the eigenvector turns out to be E vector. So we can get the E, and then we can get the time series for each mode, and then we can get the pattern of each mode. And each mode is, we can calculate the signal to noise ratio, and if it's substantially above 1, that's forced mode. So if we apply this method to SST, we get these patterns. So the leading pattern has signal to noise ratio 14.9, and the second pattern has 6.0. So they are well above 1. So they are considered as a forced pattern. On the other hand, third and fourth mode have much smaller signal to noise ratio. So these are dominated by internal variabilities. So let's concentrate on the leading mode. So let me start with the time evolution. So the black curve is the ensemble mean time evolution extracted as the forced mode. And the red curve is the global mean, the aerosol optical depth, the simple average, and they are matching very well. Also, if we regress the AOD onto the black time series, we get the pattern with the almost every aerosol concentration center of action lighting up. So we call this first pattern as the global mean effect. if we look at the spatial pattern, the overall cooling pattern over the globe, mostly on the northern hemisphere, and very little signal over the Southern Ocean. And the largest cooling is on the North Pacific, related to the top of atmosphere radiation change and also the intensified ocean low. Over the North Atlantic side, we have warming over the South Polar Gyre, which is related to the strengthening of AMA due to the overall cooler climate. The second mode shows the time evolution of ramping up from 1980s to about 2020 and then became steady afterwards. The blue curve is now the AOD difference between the two areas, the Asia/tropical minus North America, Europe. And the regression of AOD pattern onto the black curve shows this pattern transition, the center of action from the North America, Europe to the Asia and tropics region. So we call this second pattern as aerosol transition effect. And the first pattern has more global pattern, including the cooling over the Southern Ocean. And we have zonal contrast between the warming over the North Atlantic and the cooling over the Indo-Pacific tropics and subtropics. Then we can look at the salinity response related to the SST forced pattern evolution. So these are the patterns of surface salinity regressed onto the SST forced pattern time series from mode 1 and 2. You can get almost identical pattern just by applying surface salinity directly for this signal to noise maximizing method. And the leading mode shows the overall shift of ITCG. So the color is the salinity. So more salty ocean in the northern tropics and fresher ocean in the southern tropics. And the contour is the E-P. So it shows the southward shift of the ITCG away from the cooler hemisphere. And this second mode shows the more zonal contrast of fresher Atlantic and the saltier Indo-Pacific, also consistent with this zonal contrast in the SST. Then with these two forced modes, we can linearly combine to get the full field of the forced anthropogenic aerosol forced pattern, the forced field. And if we do the northern hemisphere average, which is red, which shows the more or less of the mode 1 evolution, and the southern hemisphere average, which shows more or less mode 2 evolution. And then the difference 2 shows the hemispheric energy imbalance, kind of. And we can do the same thing for the precipitation, and this precipitation forced mode actually closely follows this interhemispheric difference in the temperature. And another interesting thing is we can just do simple ensemble mean like many studies do to get the forced signal, which is the SYN curve, and which is much more contaminated by internal variability. So you can see how effective this Wilson method is in extracting forced mode. One last figure I would like to share is that the mode 1, the global effect has been talked more in the literatures, but the transition mode has been less investigated. So, and one question is, when does this second mode become important? So we calculated the 41 running trend of 2 time series and asked when does the ratio become the maximized. And it's around 1987, the 41 trend around that, the trend maps are shown below for SST and surface salinity, which more or less reflect the 2 mode we saw before. So the conclusion is we use the signal to noise maximizing method to extract the anthropogenic aerosol forced mode we found two modes. One is global mean effect, and the other one shows the aerosol transition effect. And we hope to use this to find the fingerprint of aerosol effect in observation in the future work. Thank you.
Very nice talk. Any question?
Yes.
Yeah, I have just a small suggestion. Maybe you reverse the sign for the EF1 and PC1. That would be better for, look, just small comments, small suggestion for your, but very nice talk. Thank you.
Well, thank you for the suggestion. We chose, of course, the sign can be flipped. And we chose this to be consistent with the evolution of the AOD or aerosol concentration. So aerosol concentration is just simple area average or area average difference. So we chose that sign convention, but of course it can be flipped. Thank you.
Any other question? Okay, if not, thank you, Yango.
Thank you.
Very nice talk. And our next talk will be presented by Chen-Rui Diao. The title is Roles of Regional Aerosol Forcing on the Pacific Decadal Variability. Chen-Rui, go ahead.
Thank you. Can you see the slides now?
Yes.
Okay. Hi, everyone. I'm Chen-Rui Diao. I'm a PhD student from Texas A&M University. And today I'm going to talk about our ongoing research investigating the different roles of regional aerosol forcings on the Pacific decadal variations. And this study is collaborated with my advisor Yang Yang from Texas A&M, Aishui from NCA, and Zhi Li from Chinese Academy of Meteorological Sciences. Oops. Let me start with the motivation. Since the 1980s, the major aerosol emission shows a redistribution from the North America and Europe to the Asia region. Most previous studies only talks about the overall aerosol impact on the climate. However, the opposite emission trend between East and West after the 1980s may have competing roles on the global or regional climate, which may lead to an underestimate of the aerosol effect. On the other hand, in addition to the widely discussed zonal asymmetry, the redistribution process also shows a meridional redistribution with from the mid-latitude to the lower latitude. Both the zonal and meridional distribution of the aerosol forcing are shown to be important, but the meridional redistribution is rarely considered. Therefore, we aim to separate and compare the relative roles of East versus West aerosol forcings with both zonal and meridional distributions based on climate models. In addition, how aerosol forcings affect the North Atlantic warming and the multi-decadal variations is widely discussed recently, but the Pacific responses to the local and remote aerosol forcings is less discussed. Therefore, our current result mainly focuses on the Pacific responses in long-term trend. Our study relies on the CESM1 large ensemble and the CESM1 single forcing large ensemble projects. In addition to that, in order to separate the regional aerosol forcings, we did 2 additional regional single forcing large ensemble simulations, largely follows the setup of CESM1 single forcing large ensemble, but only fixed the fossil fuel related aerosol emission in the Eastern Hemisphere or the Western Hemisphere at 1920s level. We have 10 members for each experiment and had each individual simulation run for 40 years from 1980 to 2020. By subtracting the fixed aerosol emission from the all forcings result, we can obtain the climate responses driven by the regional or the combined aerosol forcings. More technical details about our simulation can be found in our published paper. Based on our simulation results, the surface and TOA shortwave radiation in response to the two regional aerosol forcings explains most of the response in the combined experiment, except for the signals from Africa and South America. Comparing the two regional results, we can see that the negative forcing from the Eastern Hemisphere are largely constrained in the tropics, while the warming forcing from the Western Hemisphere not only affects the tropical region, but also dominates the mid to high latitudes. This reveals the importance of meridional distribution of aerosol forcings. The first part of our result is focused on the tropical Pacific. In response to the East FF, the tropical Pacific shows a typical El Nino pattern with cooling in the emission domain and warming in the central and eastern Pacific. The easterly trade wind is also weakened by anomalous westerlies here. And the equatorial Indian Ocean also shows an anomalous easterly wind. In response to the West FF, the tropical Pacific shows a warming trend in the central Pacific, and a cooling trend in the equatorial eastern Pacific, which is similar to a central Pacific type El Nino pattern, but there is also a hemispheric asymmetry over the eastern Pacific with warming in the northern hemisphere and cooling in the southern hemisphere. Note that both East FF and the West FF induce warming of the central Pacific, but this warming signal is not captured by the combined case. This is possibly due to the aerosol forcings from other domains not included in our simulation, such as the South America or Africa, or it can also be related to the nonlinear effect between the East FF and West FF. Along with the SST response, the aerosol forcing also induce different worker circulation changes. Both East FF and West FF induces similar responses in the ascending branch of Pacific worker circulation, with strengthening of the ascending in the Western Pacific and weakening in the maritime continent, which are consistent with the local zonal SST gradient here. However, the zonal circulation changes in the descending branch of Pacific worker circulation shows different modes, but in smaller magnitude. In response to East FF, the Central and Eastern Pacific is characterized by anomalous ascending motion, which indicates a weakening of Pacific worker circulation. And it is also accompanied with an anomalous descending over the equatorial Atlantic. In response to the West FF, the Central and Eastern Pacific shows another anomalous cell, which strengthens the descending of Pacific worker circulation. In addition, the equatorial Atlantic worker does not show obvious trend. This suggests that the West FF-induced equatorial Pacific response is not originated from the equatorial Atlantic. Different from the tropical Pacific, the extratropical Pacific shows different patterns in response to two regional forcings. The East FF induces a typical warming phase PDO-like pattern with cooling in the western part of North Pacific. In contrast, the West FF induces a large-scale warming over the whole extratropical North Pacific. In the combined case, the East-West FF warming largely offsets the cooling due to the East FF. This is inconsistent with some previous studies. The interesting part here is that the North Pacific responses are significant in both cases, while the external forcings are located outside of the North Pacific basin. And we are particularly interested in how the East and West aerosol forcings remotely affect the extratropical North Pacific SST response. The right figures show the lower and upper level response to East FF based on the 200 millibar eddy geopotential height and the stream function. The remote forcing of East FF to the North Pacific largely follows the typical teleconnection pathway between the tropical and extratropical Pacifics. The local radiative cooling due to the aerosol forcing over the tropical Indian Ocean and the Western Pacific induces a redistribution of the Walker circulation, and the El Nino-like tropical SST pattern. This excites a wave trend from the tropics to the extratropics and generates upper level low in the western part of North Pacific. Since it is the barotropic system, the sea level pressure also shows an anomalous low in the North Pacific with cyclonic wind anomalies. The anomalous westerlies enhanced the climatological westerly wind in the extratropical region, and thus increased the surface heat flux. Thus, the western part of the North Pacific shows a cooling response here. The whole process here are similar to the teleconnections between Enso and the North Pacific patterns. In response to the West FF, the surface and upper level pattern in response is very different from that in response to East FF, where we cannot see obvious upper level wave activities occur in the tropics. Unlike the widely discussed equatorial teleconnection pathways between the Atlantic and the Pacific, the radiative warming due to the reduction of aerosol in the eastern hemisphere mid-latitude excites wave trends propagate at mid-latitude, while which induces upper level high in the extratropical North Pacific. This results in a high sea level pressure over the eastern part of North Pacific with anticyclonic anomalies here, which weakens the climatology westerly wind and decrease the surface heat flux. This explains the warming in the eastern part of North Pacific in response to the West FF. But while the western part of Northern Pacific shows strong warming cannot be fully explained. There may be some other mechanisms behind this, but it is still under investigation. And here is the brief summary of our current result. First, both zonal and meridional distribution of the aerosol forcings could be important in driving the climate response. The radiative cooling of aerosol forcing from Asia induced the El Nino-like SST pattern over the tropical Pacific in a multi-decadal timescale, and it also induced descending in the tropical Atlantic, but with a small magnitude. While the West FF induces a CP-like El Nino pattern and two-cell Pacific Walker circulation anomalies, and we cannot see an obvious zonal circulation occurs in the equatorial Atlantic Ocean. And the third one is the North Pacific is remotely driven by both East FF and West FF. but via different teleconnection pathways. The East FF induces the positive phase of PDO-like pattern via the wave trend from tropics to extratropics, while the West FF induces large-scale warming by the teleconnection between North Atlantic and North Pacific via the mid-latitude wave trend. Yeah, that's all we have right now. Yeah, thank you.
Okay. Thank you. And any question? If you have a question, you can unmute yourself or use your hand.
Yeah, quick question. I was just wondering if analogous to what Yano showed, if you've looked at to trying to exploit the different temporal evolution in the full aerosol forcing run to see if you pick up similar patterns to what you get in your experiments.
Yeah, we try to look at the combined East FF and West FF, the SSD pattern compared with the overall pattern here.
I was meaning more the fact that they evolve at different times. And so if you were to regress onto a time series of each location, sorry, maybe I misunderstood what you showed in the full run, and maybe that's already what you did.
Oh, thanks. Thanks for the suggestion. Actually, our simulation starts from 1980s to 2020, so it's like 40 years time series. And based on the zonal average result, the aerosol forcing is largely has a linear trend over both east and west.
Oh, okay. So it's hard to separate them out, but I guess you could do it over the full time period in the single forcing large ensemble runs.
Yeah, we can do that. Yeah, but yeah.
All right. Thanks.
Yeah, thank you.
Okay, thank you, Riri. And you can now unshare your screen, and we move to our next talk. Next one will give by Claire Desser. The title is Defining Internal Atlantic Multi-Decadal Variability in a Changing Climate.
Thanks.
Claire.
Thanks, Aishu. I think he's, let's see. I cannot share because the other participant is still sharing. Whoops.
Okay.
There we go. Just reading my message. Okay. All right. Well, thanks, everybody. We are going to change gears considerably. And I'll talk to you about some things we've stumbled on recently in, title here, Challenges in Defining the Internal Component of Atlantic Multi-Decadal Variability in a Changing Climate. And this is work that Adam and I have been doing together. So canonical definition of AMV, as I'm sure everyone knows, is the area average sea surface temperature anomaly over the North Atlantic from 0 to 60 north. I think this index dates back to Enfield et al. About 20 years ago. So here's the observed time series, annual SST anomalies for this region for the last 100 years. And typically one applies some kind of low pass filter to the data to emphasize the decadal and longer timescales. And so the problem is that there may be a global warming forced signal and other types of external forcing embedded in this index. So you have to, if you're interested in the internal component, you have to account for that in some way. So typically a very simple but powerful approach that's been used for many different topics, including AMV, is to simply take that time series and regress it on the global mean temperature record and remove that component. So that's a way of getting rid of the part that's congruent with the global mean temperature, which we consider to be mainly externally forced. So that's the red curve, and you can see we've gotten rid of that secular trend over this time period by applying this method. So, and then here is the spatial pattern that you would get, if you apply this residual method or regression on the global mean at each grid box, and then regress that purported internal variability onto the North Atlantic index. And this is the map that you get, and this was part of our paper published last year in GRL. So far, so good. Nothing looks odd, but does this procedure really isolate the internal component of AMV? So we can test this with model large ensembles where we know the true internal variability, or at least can estimate it very well if we have enough ensemble members. So that's what I want to talk about today. So it's a little bit complicated, so I wrote down a roadmap for us. So the aim here is to isolate the internal component of AMV. So step one, we have to find some empirical way to isolate the internal variability of the gridded sea surface temperature anomaly data at each time step. So we're going to use this regression on the global mean to do that and subtract that. So that's called the residual method. Step two, we now are in the world of internal SST anomalies if the method works well. So then we compute the AMV index, this North Atlantic average, and then we regress the data onto that index to get the associated spatial pattern. So that's in this residual method. Then we can test the accuracy of that method using model large ensembles where we know the true internal variability a priori. Okay, so just showing you in simple equation form what this residual method is. So it's simply, as I've been saying, you take the SST anomalies at each XY location and time, and you subtract from that the regression map that you form by regressing the data onto the global mean SST. And that's your estimated force component. Of course, this is not going to work if the global mean pattern, forced pattern associated with global mean SST changes its pattern with time due to, for example, aerosol forcings being different from greenhouse gas forcings, and also that there are regions of the global oceans that take longer to respond to greenhouse gas forcing, et cetera. But if you take this as a given, and we've tested it out for the time periods we've examined, that this actually does work quite well. So here is the heart of the matter, and that is something that we hadn't recognized before, and I think really has been overlooked in the literature. And that is that this global mean time series, temperature time series, contains forced and internal components. And further, that internal component has a piece that is linearly correlated or associated with the internal North Atlantic SST, so with the AMV itself, as we might expect. And then it also has a term, I'm calling it internal G star here, which is orthogonal just by construction here to the North Atlantic SST. And it's really this term that is causing the problem, as I will show you in a moment. Okay, so now we're moving to the model large ensemble world where we can really test things out, test the residual method against the truth. So here we're using 7 model large ensembles, and they're shown here. It's a mix of CMIP5 and CMIP6, and you can see the number of members for each model in parentheses. So in total, we have 430 ensemble members that are coming from these 7 models. So the procedure for each model, we're going to look at 2 different worlds here, the true internal variability and the estimated internal variability. So the true internal variability, just simply we subtract at each time step and location the ensemble mean, SST anomaly, from each member. And if we have enough ensemble members, that's a kind of a perfect way to isolate the true internal variability. If you don't have large ensembles, like in the real world, you can't use that method. So then we use this residual method, which is an estimate of the internal variability. So again, at each location and time step and ensemble member, you subtract the regressed SST onto the global mean temperature from each ensemble member. Then, as I said, we take that internal SST anomaly, we regress it onto our AMV index, the North Atlantic. We do this for each ensemble member separately. Then we average all the maps for each ensemble member in each model. And so then we have 7 ensemble mean maps, if you will. And then we average those 7 models, average regression maps. So we have lots and lots of samples here, and things are very statistically significant. You can take my word for it. Okay, so now I'm going to get to the heart of the result. So this is a map showing you using the time period of the historical portion of that overlaps with all of these models, 1950 to 2020. We've applied the 10-year Butterworth filter. And this is the estimated method, the residual method. So we're taking in this box the North Atlantic SST anomaly, and we're regressing SST in color and SLP in the contours onto that box. So this is what the map looks like, the very robust, because we have so many different models and ensemble members. So this is the regression onto the North Atlantic SST, but implicitly, we have also subtracted any global mean internal variability just because the method does that. And I think, just because the method does that. Okay, now we can simply compare to the truth, which is this truth method. So we don't have to which is this truth method. So we don't have to worry about the estimation at all. So this is the same thing where we regress now on this SST averaged over the North Atlantic minus the global mean, just to compare apples to apples. And indeed, the two maps look nearly identical. So the residual method is getting at the truth. So that's good. Now, in the truth world, we can why should we subtract the internal global mean? There's no reason to do that. So if you don't do that, if you just regress on the North Atlantic area average, that box, this is the map that you get. The Atlantic looks fairly similar, but the Pacific looks really different between these two maps. And if you take the difference between them, that's what it looks like. And some of us may recognize that as kind of an IPV, PDV kind of signal. And that difference map is big compared to the regression map on the North Atlantic index itself. So again, just reminding ourselves what's going on here. If you subtract the internal global mean from the internal North Atlantic SST, you can rewrite that global mean term as two parts. One is a part that's linearly correlated with the North Atlantic SST, and one is this G star term, which is uncorrelated. And then you regroup them into this red part, which is all related to the North Atlantic, and then this blue term, which is the orthogonal, the part of internal G that's orthogonal to the North Atlantic. And so these maps, that's what they are showing. Okay, so now let's see. So this residual method clearly needs some tweaking here. We've introduced here this modified residual method where instead of regressing for each ensemble member, we're regressing on its own time series of global mean temperature, which includes internal variability. We regress it on the ensemble mean global mean time series. So in that way, there is no internal G by definition. So that term is zeroed out. And you can see that, again, with comparing with the truth, this method does a great job in getting at the true association with the internal North Atlantic. And again, we can take that difference map and we can see once again that that pattern in the Pacific is really strong. And that's the part that's associated with this G star term, the part that is orthogonal to North Atlantic variability. So I'll have another slide after I go through my conclusions, but I just want to now hit the take-home messages. So here's the take-home. Estimating the force component with the global mean temperature regression method introduces a spurious connection between the Atlantic and Pacific in the definition of internal AMV in models. And I think you can see that by comparing the top maps and the middle row of maps. They are different, and that's because the top maps have included this internal G term that has nothing to do with the North Atlantic. It is by construction orthogonal. So secondly, take home, redefining the method to use the ensemble mean global mean temperature alleviates the problem. But you might say, well, if you have a large ensemble, you don't even need to use the estimated method. But of course, we want to use it for observation. So I think it's still a valid, a good thing to do. I haven't shown you, it would take way too long, but the results are robust across each model that we've examined and across different time periods, also looking out into the future. The relative magnitudes of this middle map and the lower map may differ in between models, but they all have this spurious connection between the Atlantic and the Pacific that is due to this G star term. I haven't shown it to you here, but we've also analyzed, the maps that go with IPV PDV by doing the usual EOF analysis, and these diff maps bear a very, very strong resemblance to the IPV PDV patterns in each model. So I think that really is the main contributor to this G star term. And then really what's left open here is how much of this North Atlantic maps, these middle maps, how much are they really due or associated with AMOC variability, and how much are they sort of a red noise response to white noise atmospheric forcing, i.e. The Clement et al. Slab ocean view, and that's still to be answered. We haven't done that here. And then the last point I want to make is that this has implications for precipitation. So here on the right-hand side, I'm showing you the precipitation regression maps just in the same format as the SST that you saw that's on the left-hand side. And, if we're interested, say, in North American precipitation, you can see that this spurious connection that's due to this G star term really affects Western North America. And you might think that AMV has a strong drying signal over California and the whole southern US. But in fact, that's due to this difference map, this G star term. And it really has nothing to do with the North Atlantic term. So I think this is an issue in models. So that's all I wanted to say here. I'm happy to take questions, and thanks for your time.
Thanks, Clara. Any questions for Clara?
Yango has his hand raised.
Yeah, I have a question about the. Hello.
Yes, go ahead.
Yeah, in the IG, look like the pattern. Yeah, the very beautiful result. I just want the IG term is the signal is strong in the tropical Pacific area. So is that associated with the interdecadal variation of Enso or?
Well, exactly. It's clearly related to, I would say, pan-Pacific variability and how much Enso, the tail of Enso, the low frequency tail of Enso contributes, how much, true decadal variability of PDV, as Matt has been showing us, how much that contributes. I really can't answer that from this analysis, but it's not surprising given what we know from the recent surface warming, global warming hiatus, that this PDV IPV pattern has an impact on internal global mean temperature variability, and that's what's being confounded in this definition of internal AMV if you're not careful.
Okay, thank you.
Yango, go ahead.
Thank you, Clara. Very nice talk. So it's very interesting that the IPV signal almost flips the sign when you take care of that IG star. But then there's pacemaker simulations that when you prescribe AMV, you get the cooling on the tropical Pacific. So any thoughts?
Yeah, I'm so glad you brought that up, and that's something I've been thinking about for a lot, how to reconcile this with these AMV pacemaker experiments that have been done, where you take the coupled model, you relax or restore the SST anomalies in this North Atlantic 0 to 60 North region to the, to the AMV pattern, and then you see an apparent negative IPV response. So I have, I guess, two comments. I think I'm still investigating, and it's a really important issue. One is that, yes, that's how the coupled model responds to AMV. It doesn't mean that that's the dominant direction of influence from Atlantic to Pacific. So if we look at the sign of the surface heat flux or total surface energy fluxes in the Atlantic, in positive IPV in the tropical North Atlantic, actually the atmosphere is driving the SST. It's not the other way around, which is what you're testing in the AMV pacemaker experiment. So I'm not sure that that setup is really giving you the dominant direction of interaction. And then the second part of my answer here is, let's see if I lost my train of thought. Oh yeah, that this warming that you saw in the Pacific, tropical Pacific associated with the North Atlantic, whether it's a warming or sort of a neutral tropical Pacific anomaly, that is model dependent, but it's not a negative IPV, that's for sure, in none of the models. Thanks for your question.
Thierry.
Yeah, Clara, nice talk. I was struck by the fact that when you look at the AMV, if you think the AMV is forcing the Pacific like you started out with, you get this opposite sign response to positive AMV, and you get this kind of negative PEV pattern in the tropical Pacific. But when you then remove that and you look at the response, say, from the Pacific to the Atlantic, if that's the way you look at it, you get kind of a same sign response in the tropical Atlantic that you have in the tropical Pacific. And that looks very much like when we do these pacemakers with idealized decadal SST patterns, just with the Atlantic only or the Pacific only. When you actually have the two effects are separated, you get those same kinds of patterns. And so that's really an interesting way to kind of confirm that these pacemaker experiments are getting the pieces of this interaction, but like you say, the direction, and we would argue it's kind of mutual. They're going back and forth and kind of interchanging their interactions. But I think it's an interesting kind of way to confirm the fact that the pacemakers are getting something that you're getting kind of from another direction.
Yeah, I think the bottleneck, if I may use that word, for this connection or lack of connection between AMV and PDV, that bottleneck or the nexus is really the tropical North Atlantic. And that's something, you know, I think it is so important to see how well do models simulate the response of SSTs in that region in response to AMOC or PDV, and what are the relative strengths of that. So I think that's the area I think we need to focus on next. Thank you.
Okay, thanks.
Thank you, Claire. Next talk will be given by Maria Molina. The title is Enso Characteristics During Different States of the Atlantic and the Pacific Meridian Overturning Circulations. Maria, go ahead.
Thanks, Aishu. I'll go ahead and share screen. And can you see the screen now?
Yes, everything looks fine.
Okay, great. Hello, everyone. So my name is Maria Molina. The work I'm sharing with you today is work that I conducted with Aishu and Jerry Meal. And to give a little bit of human background on how this project started or got going, when I first started my position within CGD, Aishu had these really interesting simulations. I asked if we had looked at Enso yet. Within them, the answer was no. And so I took a look, and the work that you're seeing today is the result of that. So we found some pretty interesting signals that I'll be sharing with you today, and I hope you find them interesting as well. So many of you are likely already familiar with AMOC, but this is relatively new to me, so I'll give you a brief overview. So AMOC is generally referred to as a thermohaline circulation. And so it's just this large-scale ocean circulation that redistributes heat into the subpolar North Atlantic from the tropics and the southern hemisphere, and its impacts are wide-ranging. So we see its imprint across North Atlantic sea surface temperatures. There's been a lot of past work done looking at the circulation, including some work from Axel Timmerman and others that have shown also an influence on Enso. And past abrupt climate change events have also been attributed to AMOC. And recently there was this publication, I believe last year, that was making the rounds across the media because they had, there's always tipping point concerns with AMOC. And so this brief communication piece published in Nature Geoscience, or just brief communication last year, provided some evidence that AMOC is actually slowing down. And that is also indicated by several climate model projections. And so a slowdown or a collapse of AMOC could really have widespread consequences to regional climates around the world. And that was really the motivation here for looking at more regional details, and also specifically at Enso, given Enso's teleconnections to regional climates around the world. Any influence on that would also influence regional climates. So AMOC transports warm saline waters of the upper ocean northward into the subpolar North Atlantic out here. And this water then cools and sinks and eventually upwells elsewhere around the world ocean. And as the climate continues to warm, AMOC may slow down due to increases in freshwater flux out here from ice sheets, ice caps, and glaciers across the North Atlantic. So the question that these simulations ask that I'm sharing with you today is, what would this schematic look like should we have an AMOC collapse? And so taking a look at the simulations with Aishu, we generated this follow-on schematic, which shows our hypothesis and what our simulations show, what would happen if there was no deep water formation across the North Atlantic. So we would see surface cooling out here across the North Atlantic Ocean, the lack of deep water formation there, and just some overall changes. The North Pacific would also see some changes, and that is because we have an open Bering Strait, which allows for water mass flux between the Arctic, North Atlantic, and the North Pacific. So some significant AMOC weakening could even trigger a reversal of water flow throughout the Bering Strait. And so that would allow comparatively fresher water to flow into the North Pacific, which would prevent any deep water formation across the North Pacific due to lower salinity. But then the question was, what about deep water formation across North Pacific? And we don't have deep water formation in North Pacific today, but there has been evidence that past climates did see this and that there was a Pacific Meridianal overturning circulation. There was a paper in 2004, Sainko et al., that showed that the extraction of fresh water from the North Pacific could result in the development of PMOC when the Bering Strait is closed. And that's because of that cutoff of that Arctic pathway and that cutoff of that freshwater flux across the North Pacific. But there's still a lot of uncertainty, right? So to what degree present day salinity profiles in both the Atlantic and Pacific basins are driven by oceanic fluxes like saline water advection versus atmospheric processes such as evaporation still remains an open question. And so we are curious about different states of AMOC and PMOC, and a series of simulations were generated. This was created by the group in Catalyst, along with Nan and Gary. And so essentially we have 4 schematics that we arrive at. And so here on the top left is our control simulation where we have present day conditions with deep water formation across the North Atlantic. Then we have simulations that we'll refer to as global, where we add fresh water to reduce salinity across certain areas. And essentially we arrive at a schematic where we have no deep water formation across the North Atlantic nor the North Pacific. Then we have experiments that we'll refer to as Pacific, where we do have deep water formation in the North Pacific, but no deep water formation in the North Atlantic. And finally, we arrive at Pacific Salt. This was a shorter simulation, but essentially we're looking at a time period where we would have deep water formation in both basins. And so we moved forward with this analysis first by looking at the mean state of sea surface temperatures and surface wind flux, just to look at what the global picture looks like with some of these experiments. And so when we consider the present day control run, these were created with CESM1, we arrive at this mean state across the globe. So these are sea surface temperatures and surface wind stress. And then if we consider a scenario where we don't have deep water formation across the Atlantic nor the Pacific, we have very cold sea surface temperature anomalies across the Northern Hemisphere and warmer anomalies across the Southern Hemisphere. So we really see this dichotomy between anomalies across hemispheres. When we take a look at a situation where we would not have deep water formation in the North Atlantic, but deep water formation in the Pacific, there is a change across the Pacific where our anomalies are not as cool across the North Pacific. And with stronger forcing, we actually arrive at warmer sea surface temperature anomalies across the North Pacific. There are also changes in surface wind stress. We see greater advection northward, so an intensification of the wind stress out there across basically the central Pacific and central equatorial Pacific up into the west coast of the US. And so this will have some implications on Enso that I'll share with you shortly. But then with the Pacific Salt experiment, where we have deep water formation across both the North Atlantic and the North Pacific, we actually see very little change in sea surface temperature anomalies across most areas with the exception of the North Pacific, where in this case, you would have a lot of warming occurring across the North Pacific. But there are differences in when these anomalies take place. So across the subtropics, whether you're looking at the Atlantic or Pacific or the Northern or Southern Hemisphere, the changes are pretty uniform year round. So this is a look at the annual cycle. You see that there is warming that occurs or cooling that occurs depending on the experiment and whether you have deep water formation occurring across either basin. But overall, the changes are pretty uniform year round. The stark difference is across the tropics. So across the tropics, we don't see this persistence of the annual cycle. And there's actually a reduction in the annual cycle across the tropical Pacific, whether you're considering a situation where you had no deep water formation in Atlantic or Pacific, or you did have deep water formation in the Pacific. And so that was really interesting. And it's really this change in the seasonal cycle across the tropical Pacific that results in some pretty substantial changes to Enso, of course, because Enso relies on the climate-based state. Across the tropical Atlantic, you also see a reduction in the seasonal cycle and in general warming that occurs during certain months of the year as we head into June through October. There are also influences from the ITCZ that result in some of those seasonal changes. And so then we went ahead and looked at we conducted a spectral analysis. So we were curious about whether these changes that we're seeing in the seasonal cycle also existed or persisted if we conducted a spectral analysis across these different regions. And when we consider the tropical Pacific, that's really where you see the most substantial change with this analysis. And so to give you a broader perspective, the tropical Pacific we refer to here is the entire band for the most part of the tropical Pacific. So we're not just looking at Nino 3.4 or a certain Nino region. We're talking about the full tropical Pacific region. And so for our control run or an observational product, the peak frequency here is the annual cycle. But for experiments where you're looking at global or Pacific, so again, a collapse of AMOC and potentially deep water formation in the Pacific or no deep water formation in the Pacific, you see that the Enso signal really gets amplified. So your peak frequency here is Enso. It's no longer the annual cycle across the full tropical Pacific region. And so we can also visualize this by plotting the dominant frequency. So here we're looking at this across a global map, and we're just plotting that peak frequency. And so this sort of purple pink shading is the annual cycle. And so you can see across most of the globe in our control run and our observational product, OISST, it is the annual cycle. But then the darker shade of purple is our Enso signal. And so we do have some differences between observations and what we're seeing in our CSM1 control, but nonetheless, that signal is there, especially across the Western Pacific. And so if we were to take the difference of our experiments with the control and look at that change in frequency, we see a big reduction in the dominant frequency. And so we're seeing a stronger Enso signal across this Nino 3.4 region, which is this black polygon, or you can see it across the broader tropical Pacific in most of these maps. Our Pacific salt experiment, where we have deep water formation in both basins, we don't see a substantial change in that dominant frequency signal across the Pacific. And so here we're looking at the full tropical Pacific region considered, and the black polygon is just the Nino 3.4 region. And so there's a lot going on here, but a signal that really stood out to us after looking at these maps for a while was that we do have stronger winds. And also we have this southwesterly component across the tropical Pacific for global experiments. So again, global experiments, we don't have deep water formation in either basin. But when we do have deep water formation across the Pacific, our surface wind stress is weaker across the Western Pacific Ocean. And so this actually allows or results in our model, it results in warm water moving farther east. So this influences our warm pool advection, which was quite interesting. And you can also see in some follow-up analysis that I'll be showing you. And so this is for Nino, and the bottom half is Nina. And overall, we just see an amplification of these anomalies. So Enso is stronger, whether you're looking at its warm phase, so Nino, or Nina. And this color bar doesn't really do Nina much justice, but again, it is amplified when you're looking at especially the Pacific experiments. And so here we're looking at mixed layer depth. So there are signals that show up also below the surface. And we can see that there is something really interesting that occurs when you're looking at these signals on a seasonal basis. So the top half is actually DJF, the bottom half is JJA. If we looked at mixed layer depth for the full year, so all 12 months, there really isn't a clear signal that emerges. But when we stratify our data by seasons, that's where we start to see a signal that emerges. And we see a reduction in our mixed layer depth during DJF months, and an increase in mixed layer depth during JJA. So this is just further evidence that this seasonal cycle signal, this reduction in the seasonal cycle, is occurring even below the surface. We also took a look at subtropical cells across the Pacific, and these were quite confusing. So if you look at the control run up here, this is DJF and JJA, we have asymmetry in the strength of the STCs, and this asymmetry just gets further amplified in our experiments. And so that was quite interesting. It made things a bit more difficult to analyze in terms of our STCs and their contribution to what that would mean for Enso. But overall, there is just, again, this amplification of this asymmetry, whereas if both the Northern Hemisphere and Southern Hemisphere STCs were to intensify or weaken, then that would have a more clear signal or imprint on Enso's intensity. But again, we see this asymmetry continuing and being amplified in the experiments. And so there are some key takeaways here. We just basically saw that Enso amplitude increases as a result of an AMOC shutdown. And it didn't matter whether PMOC developed or not. Enso amplification increased in all experiments where there was no AMOC or AMOC was significantly weakened. And this is, again, this caveat that this is within the CESM1 experiment. And that active overturning circulations in both basins did result in a reduction in that Enso amplitude. And then we also saw that there was an atmospheric component, some changes in trade winds that contributed to some of these changes. And also there were changes in the subsurface where we essentially see contributions to the reduction of the seasonal cycle. And as a result, that impacts Enso calculations. But overall, we also saw that during an AMOC collapse, there is an Enso extension into the Eastern Equatorial Pacific. So more Eastern Pacific Nino as well. And maybe I should have highlighted that here. But again, you can see that the anomalies for Nino extend farther east. So you're seeing, again, greater Eastern Pacific Nino occurring there. And so future work could address, how this persists into a changing climate, what roles do other modes of variability play, and also just more robust quantification of the physical mechanisms that are contributing to Enso changes, right? Right now it's a bit hand wavy. We're looking at maps and we're taking a look at subtropical cells and trade winds, but perhaps performing a causal inference analysis can lead to better quantification of the contributing factors to Enso changes. And so here is the paper. If you'd like to read more, it came out in January of this year and in Journal of Climate. And I look forward to answering any questions if you have them.
Thank you, Maria. Claire, you have a quick question?
Yes, hi. Thank you so much, Maria. What a really great results and super interesting. I wanted to see if I could reconcile it with what I was showing. So I think your AMOC shutdown simulations, you're seeing an effect, you're not seeing the opposite sign SST in the tropical Pacific as the Atlantic. I think it's It's more that, yeah, it's not the negative IPV when you have an AMOC-induced warm Atlantic. Is that correct, or do I have it wrong?
Let me show this to you, and I stopped sharing, right? Okay, let me share screen again.
I think it was one of your first slides.
This one?
No, the early slide where you showed the SST maps, the response.
Oh, okay. I think this is SST maps.
Yep, that's the one.
Exactly. Oh, okay. Yeah, and this is the full year. So we're not doing any seasonal stratification of the data. So I don't know if that may muddy things up a bit. But to be honest, yeah, I think that would be something to look into further based on these maps. I don't know. Yeah, so these are the global experiments here, B and C. So no deep water formation in either basin. And for Pacific, you do have deep water formation occurring across the Pacific. And so the main change is here in the Pacific. And your question was about, one more time?
Well, thank you. I won't take the time. I think we're behind, but thank you for showing me this again. I'll follow up separately. Thank you.
Okay, thanks, Clara. Thanks, Maria. Next talk will be given by Glenn Liu. The topic is understanding the drivers of Atlantic multi-decade variability using a stochastic model hierarchy. Okay, Glenn, go ahead.
Yeah. Can everyone see my screen?
Yes, perfect.
Okay, great. Hi, everyone. My name is Glenn. I'm a third-year student in the MIT Hui Joint Program, and I'm working with Youngo, Claude, and John. And today I'm going to talk about our work on understanding the drivers of Atlantic multi-decadal variability using a stochastic model hierarchy. And I want to start by defining AMV, but this has been defined pretty well by Clara already, so I'll just go quickly over this. Essentially, if you take the area weighted average of sea-surface temperature anomalies over the North Atlantic in this dashed white box, you'll see that as a whole, the North Atlantic basin fluctuates between states where it's anomalously cold or warm for multiple decades at a time. And while both ocean and atmospheric dynamics play a role in this phenomenon, one of the kind of interesting questions is there's not less consensus on the relative importance of both components. On one hand, some believe that AMV is primarily driven by intrinsic variability in the meridional overturning circulation, for example, while others argue that AMV is primarily driven through atmospheric processes such as the North Atlantic Oscillation. And one of the challenges of trying to understand AMV is that the observational record is simply too short, and it's difficult to make statistically robust statements about the behavior of this phenomenon. So one approach is to simplify one of the components. An example of this approach is the use of slab ocean simulations. So slab ocean simulations feature an atmospheric general circulation model that's coupled to a slab ocean that's has fixed thickness and time, but can vary in space depending on the model. And the key point here is that slab ocean simulations have no lateral or vertical communication between ocean grid cells. This effectively removes ocean dynamics from the picture and allows us to examine how SST varies in a world without ocean circulation. And oftentimes there is an additional climatological Q-flux correction to ensure that the SST is realistic. So this brings us to the motivation behind this work. Specifically, there's a paper in 2015 by Clement et al., which found that slab ocean simulations on the right were able to reproduce both the spatial and temporal characteristics of AMV that are comparable to observations on the left and fully coupled models in the center. And this raised the question of, is ocean circulation really necessary to generate AMV? More recently, there have been a few studies that found that slab ocean models tended to have higher SST variance compared to fully coupled models. And these studies suggested that this means ocean dynamics actually act to damp SST variability, particularly at low frequencies. And this kind of brings forth one of the challenges of using a slab ocean approach. So because of this wholesale entire removal of ocean dynamics, it makes it difficult to understand how individual processes might contribute to this difference in variance between slab and fully coupled models. So there's this sort of need for a flexible, transparent approach that allows us to understand how individual processes contribute to SST variability. In order to do that, we return to the classic stochastic climate model, and this was first proposed by Hasselmann in 1976. Basically, what this model is that it says the mixed layer temperature can be modeled in a simple equation with two terms. The forcing by the atmosphere via heat fluxes acts a much shorter time scale, so this can be parameterized as white noise. And a given SST anomaly is also damped to the atmosphere at a certain rate, and that strength of damping is determined by lambda A, which is a heat flux damping coefficient, and this can be statistically estimated. This particular model was pretty successful at capturing the spectral properties of SST in the exotropics, but one thing that hasn't been examined is the seasonal variation in these parameters. For example, slab simulations often feature a temporally fixed mixed layer depth, so the implications of adding seasonal variation in mixed layer depth have been less explored. And that's one of the goals of this work, is to explore how seasonal variation impacts SST variability, both down to lower frequencies. Additionally, when we add in variation in mixed layer depth, there are more additional phenomena to consider, such as entrainment and reemergence. Specifically, this concerns the fact that in the winter, anomalies are allowed to penetrate much deeper into the mixed layer. However, in the summer, we have the formation of a shallow seasonal thermocline, which effectively insulates these temperatures at depth from further damping to the atmosphere. The following fall and winter, the mixed layer depth deepens again and re-entrains these anomalies back to the surface, thereby affecting conditions the following year. This can be described in the stochastic model with the inclusion of an entrainment term. And note that this entrainment term has both damping and forcing components. And one of the questions of this work will be also to investigate how does the inclusion of this term impact SST variability? And does this provide a viable pathway for seasonal anomalies to persist onto longer timescales? So now we have the stochastic model with three terms, each of which are relatively physically interpretable. And actually, there are only really three input parameters: the amplitude of stochastic forcing, the heat flux feedback, and the mixed layer depth. And I won't go into detail in the interest of time, but feel free to ask me questions about how these are estimated. We estimate these parameters from the CSM1 pre-industrial control simulations, and we compare the stochastic model output SST with the SST from the CSM simulations to try to understand the interplay of these different processes. We've also developed a hierarchy of stochastic models that increase in complexity from bottom to top to systematically explore these processes. And it looks pretty complicated, but I want to break down how we answer our three key questions with this specific hierarchy. So first, we investigate the role of seasonal variation by successively adding in seasonal variation in damping, forcing, and both together, and finally mixed layer depth at level 4. We compare the non-entraining and entraining stochastic models to try to isolate the role of entrainment and how that impacts SST behavior. And finally, this kind of goes back to the Clement et al. Paper, but many works have focused on the temporal aspects of SST variability, and much less focus has been given on the spatial pattern. So if we apply a spatially coherent temporally random forcing to the stochastic model, can the stochastic model reproduce variability which resembles AMV in CSM1 full? To begin, we look at a case study in a very specific point in the subpolar gyre, and we've chosen this point for 3 reasons. It's the location of maximum AMV loading in CSM1 full, which allows us to investigate where the signal is the strongest. And it is also away from regions of mean advection, such as the western boundary currents. So this really allows us to focus on the interplay between these upper ocean processes. And finally, it has a very typical seasonal variation in parameters. So the most important takeaway from this slide is that these parameters tend to be stronger in the winter and weaker in the summer. So at this point, we integrate the stochastic model for about 10,000 years. And we're going to initially start by looking at the short-term SST persistence and move on to longer comparisons of the spectral estimates. So we begin by looking at the February SST lagged autocorrelation. So this is February SST anomalies correlated with March, April, and so on. And we begin at the classic stochastic model where all the inputs are temporally fixed. And for those who are familiar with this, there's a classic exponential decay, namely as you head further away in time from this particular point, because of the application of stochastic forcing, conditions are less and less similar. However, when you compare it to the autocorrelation of SST from the same point in CSL1 slab, you'll notice that there's this curious feature in the spring and summer where the decorrelation somewhat slows down. And the reason for this feature becomes clearer as we investigate levels 2 and 3 in the hierarchy. Specifically, the addition of stochastic seasonal variation in the amplitude of stochastic forcing begins to lead to this formation of a shoulder-like feature and slowdown in decorrelation. This suggests that in the summertime, we have weaker damping and forcing, but remember that in these levels of the hierarchy, the mixed layer depth is fixed, so the system has a constant heat capacity. As a result, anomalies that are formed in the winter are allowed to persist through the summer, leading to this unrealistic persistence that we see in slab-like configurations. And to bring this home, if we add in seasonal variation in mixed layer depth in magenta over here, you'll see that this shoulder-like feature is no longer present in the SST autocorrelation. If we now compare that model, but to the CSM1 full, which has a fully dynamic ocean, we see that adding in seasonal variation in mixed layer depths alone cannot capture the behavior of SST in a fully dynamic ocean model. Specifically, you see these rebounds in autocorrelation that are not captured. It is only with the addition of entrainment that the stochastic model actually does a pretty good job of replicating both the amplitude and the timing of these rebounds. And again, this is a simple term model with 3 terms, and it's doing a pretty good job of replicating the behavior in a fully dynamic ocean model, suggesting that at this particular point, processes, additional ocean dynamics beyond entrainment are less important for capturing SST variability on these seasonal to interannual timescales. But what about on longer timescales? So to examine this, we now look at the power spectral estimates of SST. So here we have the power spectral estimates from periods of 2 years to 100 years on the left. And what I want to emphasize with this slide is you'll notice that the power spectra for CSM1 full at the subpolar gyre point in white has much lower variance compared to CSM1 slab, as well as the non-entraining stochastic model with a fixed mixed layer depth. This again suggests that there's more variance at this in these slab-like configurations compared to the inclusion when ocean dynamics are included. However, this brings the question of if we add in seasonal variation in mixed layer depths, does this sort of fix this increased variance that we see in the stochastic model? And the answer is it doesn't quite fix it. Essentially, adding in seasonal variation in mixed layer depth slightly damps the SST variance, but it doesn't alter the spectrum shape. Only the addition of the entrainment mechanism really allows for a better match with the SST spectra in CSM1 full, specifically with the increased damping at interannual to decadal timescales. However, you might notice that at lower frequencies, there still is a slight underestimate of power compared to CSM1 full. So compare the orange and the white lines. And this suggests that additional dynamics beyond entrainment that are missing from the stochastic model might be responsible for reconciling these differences. And finally, we've been doing all this analysis at a single point, but we can do the same integration at all other points in the North Atlantic Basin and compute the resultant A and B pattern. So I've done that on the left over here, and this is a comparison of the A and B pattern in the entraining model with CSM1 full. And what we see here is that the stochastic model does a pretty good job of capturing the major features of the canonical horseshoe pattern, including the maximum warming in the subpolar region. And this suggests that ocean dynamics might be less important for capturing the large-scale features of the A and B pattern. However, we see that overall, the stochastic model still underestimates the amplitude. And this is where potentially there's a role for ocean circulation or other dynamics that are missing from the stochastic model. So I just want to quickly go over the takeaways of this talk. And we saw that seasonal variation in the upper ocean parameters are quite important for capturing SST variability at our subpolar point. And because of the lack of mixed layer depth variation, slab oceans have this unrealistic summertime persistence. We saw that entrainment damped SST across most timescales, but there still is an underestimate at low frequencies. And finally, that applying the spatially coherent but temporally stochastic forcing produces the A and B pattern, but the amplitude remains underestimated, suggesting that ocean dynamics might be responsible for reconciling these differences. Thank you for listening, and I'm happy to take any questions.
Thank you. Any question? Okay, Ella, go ahead.
I had one comment and one question. I guess the comment is just that the CSM1 underestimates the low frequency variability in the North Atlantic, and it might be interesting to look at the decadal prediction large ensemble and the balances that are happening there. But my question was, it looked like when you didn't have the seasonal variation mixed layer depth, you had that extra persistence in the summer, but then it fell off more rapidly the next winter. Do you understand why that happened? So that kind of by the time you're in the next winter, it looked like they had similar kind of autocorrelation.
Right. So the reasons behind that sort of rapid drop off in towards the second winter.
Yeah.
And right. So in that case, in thinking of the seasonal cycle of the stochastic forcing, this strengthens again in the fall and winter. So that would lead to stronger influence of the stochastic forcing term, which would lead to larger decorrelation during that particular period.
Oh, okay.
If that makes sense. Oh, thanks for the suggestion too.
Okay,
Glenn, I'm curious about what kind of stochastic forcing you used. Did you try both red and white noise, and have you tried different red noise forcing? Because I'm curious that you're attributing that lack of persistence in the AMV to lack of ocean transport. You're emphasizing the ocean transport. I'm just curious about the forcing, the stochastic forcing.
Right. So the stochastic forcing, I haven't tried any, we haven't tried any red noise type stochastic forcings. We only use white noise stochastic forcings. And to estimate the monthly amplitudes of this forcing, we essentially do an EOF analysis on net heat flux within the corresponding CSM model. And we replace the PCs with the corresponding of a white noise time series. So basically we get the amplitude from the EOF coefficients, and we replace the time series with a white noise time series of unit variance.
Amy, you have a quick question?
Yeah, sorry, just to follow up on this. Great talk, Glenn. One, can you, is there a paper you can share on this? And second question is following up on Hyan's question about the atmospheric forcing. What if you were to include anthropogenic forcing, or even potentially there's some evidence that anthropogenic forcing causes changes in the NAO, which then, so your stochastic forcing, atmospheric forcing may actually have some more low frequency variability in it.
Yeah, thanks for the questions. So on the first one, I'm still working on a paper for this, so I don't have any published work so far, but it's going to come out soon after I submit it. And regarding your second question, I actually haven't really thought about exploring the role of external forcing so far, but I think I agree that would be really interesting to try to investigate how that impacts these results. And primarily, we've been focused on the pre-industrial control simulations to kind of focus on the internal variability of AMV, but I think it would be really interesting to add in external forcing as well and examine the impacts.
Okay, thanks, Glenn. Our next and the last talk for this session is Yan and Duan. The topic is a revised interpretation of the signal-to-noise paradox. Yan, please go ahead. Yan, right now we cannot hear you.
Hello, everyone. My research topic is revised interpretation of the signal-to-noise paradox in the long-term climate simulation. Can you see my screen?
Right now, yeah, we can see your screen, but we cannot see the presentation.
Okay. Can you see it now?
Yes.
Okay.
Not in screen. Okay. Yeah, that's good.
Okay. I'm sorry.
No
my research topic is revised interpretation of the signal-to-noise paradox in the long-term climate simulation. With thanks to the USD NIFA grant for supporting of our research and the CSM2 large ensemble group for sharing data with us. My presentation is divided into 3 sections. The first one is the ratio of predictable component definition and the RPC global distribution in the global continent region and the RPC trend with increasing of ensemble size. The second section is about the signal to noise paradox reason and the revised interpretation of the paradox. The last section is about the paradox interpretation application for the model accuracy and for the long-term temperature trend analysis. The data we use is CRUTS, surface temperature, and also the CSM2 large ensemble with 19 ensemble members and the SEMIP6 model with 220 ensemble members from the 23 climate models. The ratio of predictable component is the main metric we use to test the paradox, and the data time period is from 1901 to 2014. We also use model selection method by the ratio of predictable signals. The method is from Smith et al. 2020. The RPC is the main metrics we use to test the signal to noise paradox. It is the comparison between the model ability to predict observation and the ability to predict itself. The signal to noise paradox definition and some introduction is from the Adam and Smith 2018, this paper. And for this purpose, so the RPC will be the comparison between the correlation of the ensemble mean and observation with the signal to total ratio in the model prediction. So we expect the RPC to be around 1, so it is perfect situation. If the RPC is much greater than 1, it means the signal to noise paradox occur. By that means model can better predict observation than the model itself. And beside RPC, we also want to test the model ability to capture observation. By that means we replace the observation from the RPC in the numerator with randomly selected ensemble member and see if the RPC based on observation is much more significant different compared with the RPC based on the model ensemble. So we randomly select the ensemble member and calculate RPC and repeat the process 1,000 times. And if the RPC based on observation is outside of the RPC based on model with 95% range, and then we reject non-hypothesis. By that means if the rejection area is much greater than the other model, so we think this model forecast accuracy is much lower compared with others. The detailed introduction of this method can be found in this paper, in the JIR paper. So here is the result we have. This graded figure is the RPC distribution in the global continent region for the 1901 to 2014. And also the hatching area is the region where we reject the non-hypothesis testing. So if the RPC is greater than 1, that means the signal to noise paradox occur. We find that the RPC greater than 1 is concentrated on the India continent. So it triggered 2 problems. One is the key contribution for the paradox, and other is how to solve it. And also the hatching area in the CMIP6 is 10%. So we want to see if is the hatching area depends on model or does it depends on ensemble size. And the less hatching means no paradox. So the more hatching means we need to investigate the model predictability much further. In order to discuss the second section, the rejection rate with the ensemble size and also depends on the model, we plot these figures. We find we want to plot the figure about the fraction of the land area where non-hypothesis is rejected with the increasing of the ensemble size. We find that this branch is the CESM2 large ensemble. It appears to have small spread or large rejection rate than other large ensemble in the CMIP6 climate model and also the CMIP6 itself. These 2 ensemble models are the top 2 large ensemble models in the CMIP6. So we get the conclusion that the rejection rate will reach balance after 30 or 14 ensemble members in the in both of the forecasters, and also it also depends on the model categories. To solve the first section problem, is the RPC. What is the reason for the signal to noise paradox? We plot the trend, the increasing trend for the RPC, the numerator and the denominator individually with increasing of the ensemble size. We find that the RPC, the greater than 1 RPC should be caused by the very small signal of the climate ensemble member, because you see the numerator part is much smaller, so it should not be the main cause to lead to the greater RPC. So this one is much smaller, so the new denominator is much smaller, is the main problem. So we want to reduce the total variance of the ensemble members of the ensemble models and see if it works for improving the paradox situation. So here is a method we use to improving the paradox situation. Because the signal to noise ratio paradox suggests a muted climate signals in the ensemble member, that means it can be improved through the model selection. We use this method to the CMIP6 plus ASM2 large ensemble cluster, because we combine these two models together. So we have 310 ensemble members together, and we select the top 31 ensemble member with the highest correlation of the adjusted ensemble mean and ensemble member. So the adjusted ensemble mean means we use ensemble mean to times RPS. The RPS is the signal variance of observation and the signal variance of the forecast. By that way, the signals strengthened by almost 100% using the model selection. The right-hand side figure is RPC calculation for the same period after selection and before the selection. We find that the RPC decreased from 2.02 to 1.13, so that is a big much improvement. The ensemble selection method is from Smith et al. 2020. In order to make the specific application for the selection method, we divided the 1901 to 2014 into 2 periods. One period is used for the climate selection, another period is used to apply the selected result from past climate to the projected period. Because in the model selection, we use the observation, so we only use the observation in the past climate, and we will not use observation in the projected period. So this application will have some real world meaning. After, also we follow the same method in the previous slides. After selection, here is the 310 all ensemble member temperature trend distribution. And this box plot is the temperature trend distribution for only 31 ensemble member we selected. We find that after selection, the temperature trend reduced RMSE to 0.32 degree from the 0.41 degree in the all ensemble members. So, and also in that figure, the blind star is the observation. So after selection, the trend concentrated around the observation, and the performance much better than the unselected distribution. And the summary of this presentation is that the signal to noise paradox, by that means RPC greater than 1, exists in agreement with previous studies, and the paradox was widely spread in the ensemble climate models. The non-hypothesis, we want to test if the model can capture the observation very well. The observation is among the several model ensembles. So this hypothesis cannot be rejected with much confidence. It is new finding and means the climate model we use works well in some part. We find the reason for the signal to noise paradox, and it can be attributed to smaller signal in the model ensemble. The region climate projection can be improved through model selection if the RPC is much greater than 1. The further study, we need to maybe discuss more about the ensemble selection by a process-based investigation. So that's all.
Thank you.
Thank
Any
you.
question? Ella.
Yeah, I might not completely, but I'm wondering what the justification is for choosing the members. Are you saying that if you do choose the members that resemble the observations in the earlier part of the record, they also resemble the observations in the later period too? Is that?
I beg your pardon? Do you mean the before and after selection if the ensemble cluster contains the observation variance or something like this?
Yeah, I guess just more generally, I'm just wondering what the justification is for choosing the members that resemble the observations well. Like, for example, if you did it within the large ensemble, there's no reason to trust one member more than the other. So, what you're showing is that if you do choose the members based on the historical period, you also find that they do better after 1950. But this is for all different models. So I guess what it could be is that models that have a bigger forced response resemble the observations better for the full time period. Is that the conclusion?
Yeah, that is just experiment setting, because in the Doc Smith 2020 in their paper, they select the ensemble member from the initial states and see if the future projection on the model forecast works better. Well, for our experiments, we divided the historical period into 2 periods. And select the ensemble member and see if the ensemble member improves the trend calculation. And I think, yeah, I think this 2 time series find that after selection, the ensemble member, we only select 31, it will be distributed around the observation. And before selection, it will contain too much noise, maybe the uncertainty, model uncertainty. So that is the case. So that is the reason we want to investigate more for the process-based for the ensemble selection, not only the statistics.
Okay, thanks.
Thank you.
Thank you. And if there's no other question, let's thank all the speakers in the morning session one more time. And we're going to conclude this session and reconvene at 1 o'clock, Ella?
Yep, that's right. Sorry for this shorter lunch break.
Yeah. Okay, see everyone at 1 o'clock Mountain Time.
Hi, Isla. This is Bonnie. You're still muted.
Yeah, sorry, I was on another window. Hi.
So Elizabeth is not back yet, and I have another meeting that I'm also moderating and being part of. So I will, start the recording, but I may have to turn the sound down on your meeting and not monitor it so closely, if that's okay.
Yeah, that's fine. I think.
Okay. Okay, I just wanted to give you a heads up.
Okay, yeah, no problem. Elizabeth is there, but so she's like
she's still on her computer, but she isn't at home.
Oh, okay.
If that makes sense.
Yeah.
Okay, great.
Okay, no problem. All right, well, welcome back. Thanks for coming back after the lunch break. I'm sure people will be streaming in as we get going. But since it's 1 o'clock, we'll get started. So again, just a reminder for the speakers that I'll give you a shout at 12 minutes in, just that'll be your signal to try to wrap up. So we're gonna start, we have a bunch of talks about kind of regional aspects of climate variability, atmospheric rivers and things. And we're gonna start with Naomi Goldenson, who's gonna talk about finding a subset of CSM2 large ensemble members to maximize variance for downscaling.
Thanks, Isla. Can everyone see my screen properly? And you can hear me?
It's good.
Okay. Great. So, yeah, to start here, I'm gonna motivate the way that, and the reason that I'm looking at this problem. So first of all, there's some ongoing dynamical downscaling in the group that I'm a part of at UCLA, and we've been focusing on a Western US domain that looks like this with an even higher 3-kilometer resolution domain over California, using the weather research and forecasting model for downscaling. Now, there's a number of different reasons that we use regional climate models in this way to better study regional scale processes, to evaluate and improve the simulations, and also because people engaged in climate planning want data for impacts assessments. And it's usually that last one when people come looking for data. So being cognizant of that, and trying to build an ensemble of dynamically downscaled simulations, we want to span the range of possibility the best we possibly can. And when it comes to choosing among GCMs, that's a whole nother talk, which actually I gave at AGU about different kind of process-based measures for deciding among GCMs. But here we're going to focus on the internal variance axis here. If you're going to have multiple ensemble members from the same GCM that you want to downscale, can we do better than selecting them randomly? And the reasons that we might want to try to do that, there's a couple. First, we want to make sure to include some really extreme extremes, because one of the ways in which downscaled simulations can be used is as essentially scenarios that some stakeholders might want to use to stress test their systems. So you want to have some closer to worst case, plausible time series in there. Another is that it's really nice when you can tie these storylines to something physically meaningful. So instead of being like, the rest is internal variance, you know, it's just random and waving our hands, it's nice if we can say, yeah, it's internal variance, it's tied to some mode of variability that we can give a name to, and that explains why you might end up with, you know, one kind of outcome or another. So can we do that? So the goal of this little exercise, laid out in the most generic possible way, is to choose the n large ensemble members that span the range of trends and variance for your region in question and include some extreme extremes. And the way that I'm doing that is to cluster all, in this case, 100 CESM2 large ensemble members across a number of different metrics chosen based on physical reasoning. And I want to find all the sets of n, however many I can downscale, where all n of them are in a different cluster from each other for all of the things that I care about, if that is possible to do. And we're also going to be limited to the members that are downscalable dynamically, which for CESM2, 10 of the 100, these extra variables were saved in 3 dimensions on model levels at higher temporal resolution, which is better for driving a regional climate model. So then that will also limit our subset. And the final step will be to add constraints for more extreme extremes until there's one set left. So that's the plan here. Because I'm focused on California and there's just enormous uncertainties in California winter precipitation, most of which relates to internal variance, I'm focusing on some metrics related to Enso variability because we have some reason to believe that that might have some explanatory power. Going back to a paper by Longenbrunner and Newman, they kind of identified these 2 modes in North Pacific variability in the change pattern of a jet shift and a jet extension. And in this paper I'm showing here, they've focused on how this jet extension mode is the most correlated with California precipitation changes. And that mode in turn is across models, you know, how much that jet extension mode strengthens is related to how much does the model become more El Nino-like in that tropical SST. So, okay, so there's some reasons to think that this might be a fruitful thing to include if we want to have stuff that we can give an explanation to. So these are the measures that I'm going to use here. Looking at some decadally smooth Enso variability phasing, a trend in El Nino-like pattern, and local temperature and precipitation trends. And then, as I alluded to before, I'll just use the selection of extreme extremes to narrow it down until I only have one set left. And I'm trying to come up with a set of 3, which if you start from 100, there's many, many, many possible groups of 3. If you start from 10, there's still quite a few. So, all right, starting with the Enso related metrics, I have done it in the following way. I've defined an ensemble EOF by stacking all 100 ensemble members in the time dimension, and then calculating an EOF over this mask of the Pacific SST. So that should be one stable pattern, consistent loading pattern that then I can use to look at all of the other, to look at every single ensemble member with respect to the same loading pattern now separately, look at the principal component time series. And I've purposefully left the trend in there so that we'll see that in the time series that we're clustering across for the future period. So this first version of that, which has this trend in it towards being more El Nino-like, illustrates how the clustering here designed to just choose the, just separate the ensemble members that just happen to have more El Nino-like years at the beginning of the period. These blue ones a little bit closer to mid-century, and these green ones just happen to have more El Nino years, kind of mid-late century. So that's random, and it's still a really helpful thing if you're trying to have different scenarios for stakeholders to be able to explain, well, if you just happen to have more El Nino years early in the century or later in the century, what difference that might make. And because there's this trend to a more El Nino-like world, they're kind of all more El Nino-like by the time you get to the very end of the century there. So that's the first set of criteria for which I have these 3 clusters. I've also clustered these in a different way based on how strong of a trend they have towards a more El Nino-like future. And the interesting thing there is that for the this kind of blue set of ensemble members that have less strong of a trend towards a more El Nino-like future, just because of the random phasing of decadal variability, none of the 10 downscalable out of the 100 large ensemble members happens to be in that blue cluster with the less strong trends. So I'll circle back to discussing that a bit more, but that just means that for this criterion, I've relaxed it so that at least one of my group I'm selecting have to be from each of the other 2 clusters. I also looked at local temperature and precipitation trends and decided to focus more on the precipitation trend, which is why this scatter plot really just stratifies the precipitation trends and ignores temperature. But this is for basically an average over this box that's shown here. And so we want some of the ensemble members that are wetter and some that are less wetter than before. Okay, the last thing that I mentioned I would be doing is to further limit the possible combinations by ensuring that they all have happen to sample some particularly extreme extremes that might not be captured in the things we've looked at so far. So these are the ones that I happen to use. So at least 4 wet winters that are at least as wet as the 99th percentile historical 90-day running maximum. So it doesn't have to be DJF, it could fall wherever, but I mean, it's definitely going to overlap with the winter season. And 27 of our 100 satisfy that. The kind of parallel thing, jumping down to C, is at least 4 instances of a 10-year rolling mean below the first historical percentile water year total. So this is our dry period, and 10-year rolling mean so that it's like a longer dry period. And you want at least 4 instances that would have been 1% thing historically. So 47 of the 100 have that in them. And then the last thing here was at least 2 single annual maximum hot days that exceed the historical 99th percentile. So that's another 23. And these are overlapping, right? So these aren't mutually exclusive, but they overlap. So, okay, we could tighten any of these constraints. Sorry, have I gone on too long already?
Oh, no, you're at 12 now.
So. Okay, great. Yeah. So we can tighten any of these until we ended up with only 3 left. But with that set, we could come up with 3 ensemble members to choose. So I just wanted to, then circle back and show you them highlighted against some of these earlier plots. And the yellow ones were all of the downscalable ones. So we do seem to be sampling some different variability in what we have selected, the goal being they're different from each other. It's less great for the precipitation, but you can see we were never going to get a whole lot more precipitation given the black outlined ones, which are the downscalable ones. But I want to circle back to that weaker trend in El Nino like SST pattern. I've outlined those ones in this light blue. It doesn't seem to yield any particular regional response, and that's kind of interesting because I might have expected it to. Even if I just look at DJF and just look at California, again, those ones with the weaker trend towards a more El Nino-like state are kind of spread all around here in our regional response. And I would have hoped, at least looking at DJF in California, that might help because there's an expected sharpening of the seasonal cycle where you might otherwise see some canceling from the shoulder seasons in the winter. But that didn't do it. And also because in another large ensemble, we see a relationship between the California precipitation change and El Nino-like warming. And that paper, by the way, has this really neat little thing where they look at, in that large ensemble, how if you happen to have a positive to negative IPO phase transition in the recent historical period, you can match the California precipitation trends in a way that you don't in the larger ensemble as a whole. But nonetheless, this didn't really work out. It's possible that there's some significantly less likely chance of being way up here in the most, in the greatest increases in precipitation. But even so, I would argue it's probably not meaningful for interpretation, which is the goal here. That sort of second goal for trying to do better than random, where we would like to be able to explain to a stakeholder, yes, this range of possibility relates to something we can give a name to. So I guess just to summarize, we do have an objective method here for choosing a subset of members to downscale dynamically. You could substitute different criteria. The downscalable subset for CSM2 does not adequately span the tropical trends that are present in the larger ensemble. But including those kind of large scale factors, it might not have the expected influence on our regions like the Western US, probably because of some things we heard earlier this morning about how the teleconnections are not properly represented. Though I'm curious what you all think there. And perhaps it would be more helpful if a different region were being downscaled. So yeah, I'll stop.
Thank you. So we're at time, but if there's one quick question, maybe it could be asked while we switch over to Christine. Or you can put them in the chat. I guess I had one. Oh, okay. Flavio, go for it.
Oh, it's super short. Maybe I missed it. So you are going to downscale it? Parts of the large ensemble?
Oh, yeah, that is a great question. So we're talking about doing several, which was the original motivation for this, over this Western US domain. Although more recently, some of my colleagues secured a large allocation request through University of Wyoming, with which they're planning to downscale all 10 anyway, across CONUS at 6 kilometer. So that also makes it.
Good to know. Yeah, just want to avoid duplication of efforts.
Yeah.
Okay, thanks. So Christine, do you want to share your slides?
Okay.
So Christine's going to be talking about climate change impacts on upper ocean processes and atmospheric rivers.
Does everything look okay, Isla?
Yep, looks good.
Okay, great. So thank you for listening to this presentation. So yeah, as Isla said, I'm going to be looking at upper ocean processes on atmospheric rivers and feedbacks using the high resolution CESM. And this work is in collaboration with Hui Li, Nan Rosenblum, and Sasha Glanville, and we are all Catalyst people at NCAR. So I think everyone here knows what atmospheric rivers are, but I had to throw in the obligatory beautiful atmospheric river shot. So atmospheric rivers are these vehicles of moisture transport. And so what I'm showing you here is some satellite images that are strung together from a NASA series of satellites. And you see this beautiful long atmospheric river extending across the North Pacific, attached to this extratropical cyclone, which is about to make landfall here in the Western North America. So this is sort of the beast we're talking about and how these things sort of interact with the upper ocean. Okay, so how are we going to do this? We will do this using, as I said, the high resolution CSM. This is CSM 1.3. This is the IHESP version. It has a 1/4 degree atmosphere and land and a 10th degree ocean and ice. And in this version, you can resolve eddies, which is a great feature. We are initially, we're looking at the high res MIP simulations. And so we follow these simulations follow the protocol for that control and transient, which means the control was 155 years. The transient went from 1950 to 2050 and used the RCP 8.5 scenario. There was a little bit of drift in the control, which I will address in a couple of slides. We focus on the Eastern Pacific and landfalling atmospheric rivers for the Western North America. And we are using the ARDT, the Atmospheric River Detection Tool that I developed with Jeff Keel a number of years ago. This was designed for high resolution climate data. It is a relative time independent method, meaning it does not depend on temporal anomalies. It's a spatial anomaly, moisture threshold, and is designed to detect the strongest atmospheric rivers. And for those of you who are aware of ArtMIP, the Atmospheric River Tracking Method in our comparison project, it is rather restrictive compared to the ArtMIP mean in a lot of those algorithms. Okay, so I thought I would throw this slide in to sort of show you exactly what we're doing because I think it's meaningful for when we're talking about the drift. Here I'm showing you 4 slides of different flavors of Pineapple Express that this method detects. It uses spatial anomalies, so it's like there's periods where it's the atmospheric rivers are high relative to a low moisture background. And then there are times where it picks up atmospheric rivers where it's relative to a high moisture background. This is the relationship that we use. It's an empirical formula that we grabbed straight out of Jules Newell in the 1998 foundational paper there. So this is sort of how we are essentially, how we're detecting the moisture piece of these atmospheric rivers. So I also wanted to throw in some pretty movies because what's a high resolution atmospheric river talk without looking at these beautiful high resolution atmospheric rivers? So this is precipitable water. This is 1950. We're just sort of cycling through October through December. So cool season atmospheric rivers. And the one on beneath is the examples from the year 2050. You can see the much higher moisture background in the 2050 period. Okay. All right, so on to how we're handling the high-res MIP drift and how this impacts AR statistics. So what we did here is we took a look at the drift by just computing the end control versus the beginning of the control, and I'm sort of mapping that out. I've sort of circled this area here where we see some small amount of cooling drift in the SST in the region that we're sort of interested in here. We're detecting atmospheric rivers in this band. If we look at these, the SSTs sort of as a time average, there really isn't a big drift for the SSTs, nor is there for the full ocean. IVT, we did the same thing. It's a little different. We actually do see a little bit of a drift and the magnitude of the IVT, which is plotted here in this bottom time series plot with the slope out there outlined. Here are the plots for the beginning of the period versus the end of the period. And what you can see is that the drift is mostly in the magnitude and not necessarily in the position of the drift. And I think this is relevant, especially for the ARDT we use, because it's not really dependent on the temporal climatology. It's dependent on the relative background, for each time slice. So this minimizes the impact on the AR statistics for this piece. Okay. So on to the cold season climatology. This is October through March cold season. And this is just the full climatology. We're looking at these are some of the variables that we're going to be looking at in the upper ocean, sea surface temperatures, sea surface height, and mixed layer depth. We can see that, and this is what we're looking at is at the end of the period, the 2031 to 2050 minus the beginning of the period, 1950 to 1969. And no surprise, of course, the SSTs increase, the sea surface height increases with the sort of exception around land areas. And then we have a shallower mixed layer depth. And the vectors you see are the wind stress coming out of the ocean. Okay, so let's move this so I can see. So this is, so now we're going to start talking about composites of ARs. And I looked at so different regions around Western North America, and I'm going to sort of focus for most of this talk on Southern California, just to show you examples. I'll draw your attention to this upper right-hand corner. To start, this is actually the composite AR events for making landfall over Southern California. So you can, and this the color contour is the precipitable water. So you can sort of have an idea of where the atmospheric rivers are falling and what we're looking at here for these composites. The colors are going to be the anomalies from the climatology. However, the vectors show you the composite AR wind stress coming from the ocean. Okay, so this is the beginning of the period versus the end of the period. And this first slide here is sea surface temperature. And you can see that you see, essentially, for the most of the domain behind where the ARs are falling, you have a reduction in sea surface temperature, and this is sort of amplified as you move into the future. And then you do see this piece ahead of where the fronts are falling, where it's warmer SSTs. So sort of related to sea surface temperatures, we're now looking at surface heat flux. And this is, you have sort of this dipole pattern behind the front and before the front. And then you see this this essentially amplified as we are moving into the future. And another thing to note, all these vectors that we're looking at, as I said, are the composite AR surface stress, and you see general northwesterly flow in the beginning of the period, which shifts more zonally as you move into the future. So that's also something that is relevant here. Okay, so now on to mixed layer depth. We see mixed layer depth here, essentially larger behind where the atmospheric rivers are making landfall, and then you see this dipole pattern emerge as we go into the future. So this is, essentially makes sense compared, when it's the opposite of what you see with sea surface temperatures. And then sea surface height is this other field that we're looking at, which is I feel is an interesting quantity to look at. You have the pattern between the beginning of the period versus the end of the period just sort of amplifies and intensifies as you move into the future. And you see these, behind the front, this decrease in sea surface height in the North Pacific. However, as the winds sort of shift to a more zonal pattern, you see an increase in sea surface height along the coastal boundaries. So that water is being pushed into the coastal boundaries, and this is potentially amplified once you move into a warmer world, which of course would have implications for things like water resources or water planning for Western North America. Okay, so I also quickly wanted to just sort of show you other regions that we looked at. I'm just showing you sea surface height now, and two of the other regions that we looked at were California and Pacific Northwest, and I have these little postage stamp mini plots plotted near them. So for California, this is sort of where the composite ARs are making landfall. And then for the Pacific Northwest, the composites are sort of falling up here in the upper part of the Pacific Northwest. And so for the sea surface height, the California pattern is very similar to the Southern California pattern. However, the Pacific Northwest pattern is a little bit different. And this probably has to do with a couple different things. I think it might be having to do with where these landfall, the atmospheric rivers, the geometry and where they're making landfall, and it could also have implications on, maybe just how we're detecting them here. So there's more work to be done to sort of understand what's going on with the Pacific Northwest. All right, so I'll summarize now key points and next steps. So for the first key point, feedbacks between atmospheric rivers and the upper oceans are detected and noted in the high resolution CSM. And we're specifically looking at this Pineapple Express and the North Pacific in this study here. Decreases in sea surface temperature and surface heat flux, little postage stamp over here to sort of remind you, and then that goes along with the increase in mixed layer depth are found in the waters behind the atmospheric rivers. Under climate change, this relationship will strengthen, intensify, and then for Southern Californians, we have a shallower and warmer waters ahead of where the front is the composite fronts are occurring. And then finally, sea surface heights respond to air wind flow by pushing the water towards the coast. Under climate change, this relationship is strengthened for California. We need to sort of figure out what's going on with the Pacific Northwest. And then our next steps will be to repeat this analysis for the historical and RCP.5 simulations as a part of the IHESP suite, and those are will be used as equilibrium control, so we won't have to really worry about this drift issue for that. And then we would like to expand the different AR regions, in particular looking at atmospheric rivers in the North Atlantic and various different flavors. So I will stop there. Take questions.
Thanks. Any questions for Christine? Haya?
Nice talk, Christine. Maybe you already mentioned, but I didn't get it. Like, what is the special feature for the high resolutions that we didn't, or you haven't found in the medium resolution, our standard like CSM2 simulations before?
Oh, well,
and how ocean eddies contribute to those differences.
Well, the reason why we use the high resolution is mostly for the impacts. Actually, the precipitation is much better defined with a high resolution, or simulated with a high resolution. But one feature that we see in the 10th degree ocean is you can sort of see this in the eddies that occur in the ocean reflected within these precipitable water movies. And when you look at the quarter degree coupled to the 1 degree ocean, you don't see such fine eddy features in the precipitable water. Now, I actually have not really chased this down yet, even though I've wanted to for a while now. I just haven't really been able to check that off my list yet. But is that a real feature? Are these observed in nature? It's hard to sort of figure that out because the satellite, we don't have that resolution with either temporal resolution with a satellite to be able to determine that. But that's one thing I think that could be, it's just and then it's essentially just the fact that the eddy resolving, what the implications of having the eddy resolving features in the ocean, and how that impacts the atmospheric rivers. I hope that answered your question. A little babbly, sorry.
That's great. If you have any more questions for Christine, maybe you can add them in the chat. And we'll move on to the next speaker, who unfortunately had a family emergency, so couldn't join, but he has recorded his talk and put it on YouTube. So if this is not clear, someone shout at me if it's not coming across properly. So this is from Pengfei Zhang, and I'm going to share. And
I'm Pengfei.
Okay.
I'm an assistant research professor at Penn State University. Today, my topic is about the climate change in the Arctic atmospheric rivers and its role in the sea ice decline in recent decades. This work is in collaboration with Gang in UCLA, Minfang in Columbia University, Robbie in PNAL, Bin in UCLA. Before my presentation, I would like to say thanks to Dr. Adam Phillips at NCAR for detailed information on the model approach used in this study. As shown on the left, atmospheric rivers are long, narrow, intense moisture transport in the mid-latitude. This is a case 5 years ago. It shows that the AR can extend from the North Atlantic into the deep Arctic. As one of the most visible evidence of the ongoing global climate change, the Arctic sea ice has rapidly declined in the past several decades, including in the wintertime, when the temperature below the freezing point. In the figures on the right, we can see that the negative sea ice concentration anomaly were observed more frequent along with the time. Previous studies attributed the winter sea ice decline to the downward long-wave radiation from moisture transport. The Arctic moisture import is by transient. However, previous studies about the downward long-wave radiation in sea ice decline as the seasonal mean moisture transport or the events like moisture intrusion that only account for a small portion of the total transport into the Arctic. In contrast, the atmospheric rivers account for a large portion of the total moisture transport. So there is an emergent need to quantify the role of ARs in recent Arctic sea ice loss. The melting effect of ARs has been highlighted by a couple of recent studies on the ice sheet melt in Greenland and Western Antarctic, polar events in the Weddell Sea, and the recorded low Arctic sea ice in the winter of 2016 to 17. The physical processes in melting effects includes the extensive greenhouse effect of the water vapor, cloud radiative effect in downward long-wave radiation, condensational heating released in the atmosphere, surface turbulent heat flux into the ice and the liquid rainfall induce the surface melt energy increase. For the melting effect of ARs in the Arctic, here we analyze the ARs in the early winter, November, December, January, during the 4 decades. The first figure shows a CS concentration anomaly associated with ARs. It shows that significant negative anomaly are observed in the marginal seas around the Arctic Ocean. The red line and the green line are the climatological positions of the ice age at the end of the October and the end of January. So the red line and the green line denote the ice growth in the 3 months. And the sea ice between the red line and the green line can be regarded as a newborn sea ice. If we present the negative anomaly in the percentage of its climatological value, we can see that more than half of the newborn sea ice melt when an AR approaches the ice cover. The third column shows the composite temporal evolution when ARs make landfall on the ice cover. Along with massive water vapor transport, the sea ice area in the black box shrinks about 0.35 million square kilometers in the following 3 days. During those several days, the downward radiation enhanced by the cloud radiative effect and the liquid rainfall are the most important factors in the melting effect. The surface heat flux only works on the day of landfalling. The melting effect is partly offset by the snowfall. We first calculated the correlation between the AR frequency and the sea ice area in the black box, shown in the bars. The different color denotes the 4 segments in the 4 decades. We can see that the correlation is significant and robust throughout the 40 years. So especially in the early winter. So hereafter, we only focus on the early winter, which is the ice growing season. In the following section, we are going to reply those 2 questions. The first, if there is a change in Arctic ARs on the global warming. If yes, can AR changes affect the sea ice loss? The first figure shows a long-term trend in the AR frequency in ERA 5. There is a significant trend in the region of interest. And this increase is robust in 3 United States data, coinciding with the sea ice area decline in the region of interest. To explore the drivers of the AR increase in the Arctic, we employed 3 model example experiments obtained from CVC WG at Enso. Those model experiments is conducted using CSM2. The first one is GOGA, AGCM run, which is forced by the historical SST and the sea ice and the historical radiative forcings. It is clear that the AGCM run will capture the AR increase in the Arctic and the spatial pattern, except the too strong increasing in the Pacific side. In the light example run, which is a coupled run only forced by the historical radiative forcing, we indeed obtained sea ice Arctic ARs increase. The spatial pattern of the is failed simulated in the light example run. It indicates the role of the natural variability in the observation. To explore the impact of the natural variability, we examine the changes in the pacemaker experiment. Pacemaker experiment is the same as light example simulations, but the tropical Pacific SAT variabilities are nudged to that in the observations. It means that at least part of the natural variability in the observation are involved in the pacemaker run. we can see that the spatial pattern of the AR increase are much better than that in the large sample simulations. Because of the model experimental design, the contribution of the natural variability can be obtained by makes a difference between the pacemaker run and the large sample run, as shown in this figure. It shows that the natural variability indeed contributed to the Arctic AR increase, especially in the deep Arctic. By comparing the three example experiments, we can conclude that both the natural variability and the anthropogenic forcing contributed to the observed AR increase in the Arctic in the observation. Next, we are going to discuss if the AR changes could affect the CS trend in past several decades. Let's recall that in the melting effect of ARs, the long wave radiation and the liquid rainfall are the most important factors. So here we check the long-term trend in those two factors associated with ARs. And we do find a significant trend in those two variables in the region of interest. And those results can be confirmed by the pacemaker experiment. To explicitly measure the contribution of ARs to the CS changes, we examine another variable, CS error growth in early winter. The CS error growth is calculated based on the daily tendency normally of the CS error in the early winter, as shown in the green color lines. It suggests a positive trend. That means the CS error growth becomes faster in a warming climate. That's because although the temperature is warming in the Arctic, the surface temperature is still below the freezing point in winter. So the warmer in summer, the faster CS growth in winter. Let's see the CS error growth related to ARs as shown in the red lines. It shows that the melting effect of ARs is enhanced in past several decades. If we exclude the contribution from the ARs, the CS growth as shown in blue lines could be much faster. So the key conclusion in this study is that the Arctic AR increase slowed down the thinner ice recovery in the winter, contributing to the CS decline in wintertime. Finally, we simply check the mechanisms behind the Arctic AR changes by separating the total trend into the contributions from dynamical and the thermodynamical effects. It's very clear that the dynamical contribution is play a less important role or even a negative role, while the thermodynamic effect is dominated the AR increase in the Arctic. This suggests that the Arctic warming allows more ARs penetrating into the Arctic. This is distinct to the South Hemisphere high latitude, where the AR increase is induced by the jet shift. Okay, here is the conclusion remarks. In this study, we investigated the melting effect of the ARs on the Arctic sea ice in early winter, and we found a robust increased trend in the ARs in the Arctic. More frequent ARs slow down the seasonal sea ice recovery, and therefore contributing to the sea ice decline. The mechanism is dominated by the thermodynamic effect. Thank you for your attention. It's a pity that I cannot attend the online meeting due to family medical emergency. Please feel free to send me an email if you have any questions or comments. Thank you.
All right, so yeah, unfortunately no questions for Pengfei here, but if you have any, please get in touch with him. And so now we move on to the final talk of this session, which is Hoi Li, who's going to talk about impacts of tropical cyclone wind forcing on the global climate.
sorry, I'm gonna share again. Does this work?
Yep, looks good.
Oh, excellent. I forgot to unmute myself just now. Yeah, hi everyone. My name is Hui Li, and I'm a project scientist at NCAR CGD and CCR. So today I want to talk about some findings from a modeling study which investigates the impact of tropical cyclone wind forcing on the global climate in a fully coupled climate model. So I want to first acknowledge my colleagues Aisha Hu, Jerry Mill, Nan Rosenblum, and Gary Strand for their contributions to this work. So there's a two-way relationship between the tropical cyclones and the upper ocean. The ocean can provide heat energy to TCs through enthalpy fluxes, and the TCs, on the other hand, can provide mechanical energy to the ocean by surface forcing. And it is this impact of TC's wind on the ocean that we're going to focus today. So specifically, when the TCs move over the ocean surface, it causes a vigorous vertical mixing, which homogenizes the upper ocean, causing this temperature anomaly dipole, which features a cold temperature anomaly at the near surface and a warm temperature anomaly underneath. And then after this mixing process, the near surface cold temperature anomaly would be gradually restored to climatological condition through the surface heat flux exchange. But the warm temperature anomalies that enters the ocean thermocline, which is shielded from the surface impact, can survive the surface impact for a longer time. So it can persist for beyond the seasonal time scale. And so the result of this TC ocean interaction is actually a net heat gain in the ocean. And it is through this process that TCs can actively contribute to the ocean heat uptake and subsequently the climate. So through these processes, previous studies have found that TCs have the potential to alter the ocean heat content and heat transport. And in the context of global warming, understanding this TC's contributions to the climate system may help us constrain uncertainties in climate simulations and projections. However, this has been a challenging topic because the processes involved span across a wide range of temporal and spatial scales. And previous studies have used some sparse observation-based studies or ocean-only modeling studies or regionally coupled model. But in order to understand the impact of TCs within the coupled climate system, where the ocean's response to TCs can also feed back to the atmosphere and subsequently affect the climate mean state and variability, we will need to have a fully coupled global experiment. So that's why our goal here is to investigate the ocean's response to TC forcing and its feedback to the atmosphere in a fully coupled global climate model. So in order to do that, we're going to prescribe TC winds into a fully coupled model. We're going to utilize two different configurations of the CSM version 1.3. The first one is a high resolution model. It has a 1/4 degree atmosphere coupled to 1 degree ocean. We're going to use this model to provide TC surface forcing. And then we also have a low resolution model with a 1 degree atmosphere coupled to 1 degree ocean, which carries the main experiments. So this high resolution model with a 1/4 degree atmosphere can simulate its own tropical cyclones. So here this figure shows 30 years of TC tracks in the observations at the top and in the model at the bottom. We can see that the model is able to capture the spatial distributions, annual frequency, as well as the range of TC intensity, generally consistent with the observations. So now we're going to find all these TCs in the model, extract their surface winds, and put them into the low-res coupled model. So at every 6-hourly interval, we are gonna find all these TCs happening at the time, and then take a snapshot of the surface winds surrounding the TC center of each TC. And then these snapshots are used to create a TC surface wind forcing inventory. Then we start running this low resolution fully coupled model and add this TC wind snapshots on the fly as the model integrates. This simulation is run for 100 years, and we're calling it a low-res TC run. So this animation shows that the TC surface winds are successfully added to the model. And here the TC's wind, the wind stress can be seen from the model output. So we do it in a way that the added TC snapshots still preserve their original timing and locations as in the high-res model. so that the ocean component of the low-res model sees the same TC surface forcing as the ocean component in high-res model, so that the TC winds can freely interact with the ocean and atmosphere, and their impact can be registered in the fully coupled low-resolution model. So we also have another low-res control round, which is the same with low-res TC, except that we didn't add TC surface wind forcing. And this is also 100 years long. And then our goal is to compare the low-res control in the low-res TC round to diagnose the impact of TC wind forcing within the coupled climate system. And then moving on to the results, which I will present according to this outline. We'll first look at the composite response in the ocean and atmosphere in order to have a process level understanding of their interactions. And then we will move on to look at the impact of TC winds on the large scale climate mean state as well as variability. So starting from the composite analysis, here we're looking at the ocean temperature response. The top two panels are showing the composite time series of the SST response following TCs. The left is for all the storms, on the right is for intense storms only, which is beyond category 3. So we can see that this coupled model with added TC can simulate TC-induced cold wake, a temperature reduction following the TCs, and the maximum cooling occurs around day 3 after the storm passage. And then the average maximum cooling for this intense TC is about 1 degree, which is similar to the observations. And the bottom left here shows the depth distance cross-section of the ocean temperature structure under the TCs at the time of maximum cooling. So we see that there is a cold temperature column right under the TC center, and there's also peripheral warming at the depth of around 50 meter depth, around the depth of mixed layer depth. And then if we take an aerial integral of this figure and plot the temporal evolution, we arrive at the bottom right figure. So we can see that after the TC passage, there's warm temperature anomaly below the ocean mixed layer, which is denoted by this black line here. And this warming signal can persist beyond the 30 days that we plotted here. So that was the composite response on the ocean. Then we also look at the composite response at the air-sea interface, especially the surface heat fluxes. So if we just focus on the black curve here, which shows the total surface heat flux, and positive means there's a heat flux going into the ocean. So we can see that in general, there is a positive heat flux going into the ocean. And this pattern, the evolution of the surface heat flux is very similar to the cold wake, but with the opposite sign. And then we also take a look at the different components of the total surface heat flux, including short wave, long wave, latent heat, and sensible heat flux. And we see that this evolution of the total heat flux is dominated by the reduction of surface latent heat flux release, which is a result from the SST cooling. And also there is also increased income shortwave radiative heating following the TCs, which also contributes to the total heat flux intake. And we also look at some responses in the atmosphere. Now here we're showing the low cloud amount. So we can see that on the day of TCs, there is some increase of low cloud amount, which is probably due to some forced updraft by the TC winds. And then afterwards, the low cloud amount also decreases with time, which also related to the reduction of SST. And it's also may partly contribute to the increase of the shortwave incoming solar heating. So that was the composite analysis. And next, we're going to look at the impact on the global climate. We'll first look at the ocean heat content changes, the SST, and surface heat flux, and precipitation. So first of all, this figure shows the ocean heat content time series. It's the anomaly, the difference between low-res TC and the low-res control. And this red curve here shows the ocean heat content anomaly integrated from ocean surface to 1,000 meter depth. So we can see that during the 100 years of simulation, the ocean heat content steadily increased, and with the average heat uptake of 1 to the power of 21 joules per year, which is equivalent to an annual heating rate of 0.03 petawatts. And this estimate is actually much smaller than the previous estimates from the ocean-only modeling studies, highlighting the importance of using the fully coupled model to capture the air-sea interactions. And also plotted is the blue line here. It shows the integrated surface heat flux, which is almost identical to the upper ocean heat content anomaly, confirming that the OHC increase is primarily coming from the surface heat uptake. And also we found that in this surface heat uptake, the dominant part is the radiative heating, and the latent heat flux is actually a major counteractive term, which I didn't really show here. And on the right, we're looking at the spatial patterns of this ocean heat content anomalies. And this is at the end of the 100-year simulation, about the last 20 years, actually. So we can see that the increase of ocean heat content is mostly in the subtropics, in the Pacific Ocean, as well as in the Eastern Equatorial Pacific. And overlaying on top is actually the TC power dissipation index, which is used to represent the TC wind power. So we see that the maximum increase of ocean heat content is a little forward than the major band of TC wind power. And next, we take a look at the climatological mean, annual mean SST pattern. So on the bottom here, we're seeing that the SST anomalies is generally consistent with the ocean heat content increase. So there is an increase of SST in the subtropical Pacific, as well as the Eastern Equatorial Pacific. And there is also some cooling of SST over the Aleutian Low area, as well as across the North Atlantic Ocean. And here is the annual mean total surface heat flux anomalies, which closely follows the SST. Here the positive values means the heat flux going into the ocean. So we can see that there is a release of surface heat from the ocean to the atmosphere in the subtropics, especially along the corrosion current. And this is corresponding to the higher SST in this area. As well, you can still see also this Eastern Equatorial warming that increases the heat flux from the sea surface to the atmosphere. And on the contrary, there is increase of surface heat flux into the ocean at the Indo-Pacific warm pole, corresponding to the cooling of SST. And we're also looking at the annual mean precipitation changes. Again, there's a slight increase of precipitation in the subtropical Pacific and some decrease of precipitation in the Indo-Pacific warm pool, and also decrease of precipitation in the North Atlantic Ocean. So that was about the large scale mean climate change. And next we're going to look at
12 minutes.
12 minutes, all right. So next we're going to look at the ocean temperature responses. So here the top panel shows the depth and longitude cross-section of the equatorial Pacific ocean temperature anomalies. So we can see that, first of all, there is a warm temperature anomaly stretching across the ocean mean thermocline, and the maximum warming is in the Eastern Equatorial Pacific. And this tells us that these TCs can contribute to this temperature pattern, which is conducive to an El Nino mean state. And I have a little text box here. And the bottom is showing the depth and latitude cross-section of the zonal mean temperature. Again, we can see that there is an increase of ocean temperature in the subtropics, all the way to the depth of about 6 meters depth. And also there is an increase of ocean temperature in the equatorial Pacific. And our analysis find that the heat anomalies actually can enter the ocean permanent thermocline and be transported equatorward through the subtropical cells. And lastly, this is the changes in the ocean circulation patterns. So here are the anomalies of global mean meridional overturning circulation stream function. On the right is the Atlantic meridional overturning circulation, AMOC. So we can see here in the TC experiment, there is actually general weakening of the AMOC, except for a slight increase of this wind-driven subtropical cell in the Atlantic. And on the global mean, there is actually an obvious increase of ocean overturning circulation, especially in the subtropical cells. So what we found is that the TC winds and actually strengthen the subtropical cell energetics. And the weakening of the AMOC, what we found is that it's due to the increased heat and freshwater fluxes in the subpolar North Atlantic. On the right, I'm looking at the meridional ocean heat transport. in the control in blue, and the differences between low-res TC and low-res control. So basically, we see that the added TC winds can increase the poleward heat transport at the latitudes of the maximum heat transport, and also there is a convergence of heat in the equatorial ocean. So that's quite interesting. I think I'm running out of time, but just one short mention of the El Nino. What we found is that the TCs can actually cause more extreme Enso events, and there's a positive relationship between Enso magnitude and TC power dissipation index. And we do see that the magnitude of El Nino and La Nina are enhanced in this TC run. And here's the summary. Basically, we designed an experiment where we put TC winds in a fully coupled model to investigate the wind effect. And we found that TC winds can increase ocean heat content and affect the SST pattern and changes in surface heat fluxes and precipitation. It also strengthened the subtropical cells and meridional overturning circulation and heat transport. And also it can increase the magnitude of El Nino events. That's pretty much all I have. Thank you.
Thank you. Any questions? I guess I have a question. I was wondering if you have tried to relate any of the things you found to biases that are in the low resolution model, and kind of would they be in the right sense to alleviate biases?
That's a good question. Well, I think that the idea is to compare, the model with added TC winds and the model without. So our hope is that any bias introduced by the model itself would be subtracted in this process. But I don't know, it may not be the most clean, way.
I didn't mean it as a criticism of the method. I was meaning more just kind of if you, in the low resolution model, if we're not capturing these winds associated with TCs, is the kind of the signal you see related to any biases that we see in the low res model?
Yeah, I think definitely yes. And I think it's even more so in the high resolution model, because in the high res model, you can actually resolve this high wind TC events. If these TCs are going to have an impact on the climate, it's also already included in your climate mean state. So I think it's definitely something to think about in terms of climate simulations.
Okay. Anne, did you have a question? I see you put your hand down.
Okay. Very impressive assimilation, but my question is, in your experiments, you only overrode the wind, and you didn't take the consideration of the precipitation and heat flux associated with tropical cyclones. And so will those other fields or heat flux precipitation cancel some of the wind effect or strengthen the wind effect?
Yeah, I think that's a great question. Absolutely. Yeah, we didn't include any impact from precipitation, or if that winds are added to the model, so it didn't really require the deep convective processes. So if you look at the time series of the surface heat flux, there's actually no heat extraction from the surface on the day of TC. So that's kind of different from what will really happen in the reality. So this is kind of an idealized model simulation that only looking at the effect of TC winds without looking at the full impact of other, TC characteristics. But I think including those will definitely have a different impact.
Okay, thanks. Well, if there's any further questions, you can put them in the chat, and we'll take our coffee break now for 25 minutes and come back at 2:30. We have some talks on extremes and then the update from the working group. Thanks. Thanks to all the speakers. unmuted. We'll give it one more minute. All right, thanks for joining again. So we have 3 more talks about extremes, and then we'll have the CVC WG update. And so for the speakers, just a reminder that I'll jump in at 12 minutes, which will be your reminder to wrap up at that point. So we're going to start this session with Danielle Tuma, who's going to talk about changes in the co-occurrence of extreme dry and wet events in the Western United States. I think you're muted. Are you?
Sorry about that. I think I'm good now.
Yep.
All right. So thanks for having me here. This has been a great workshop. So today I'll be talking about our research, kind of 2 research projects looking at the co-occurrence of extremely dry and wet events in the Western US. It's important to understand how extreme wet and dry events co-occur. In some cases, they can lead to devastating impacts. So this is one example of debris flows that occurred after a fire in Southern California in Montecito. So after the Thomas fire, Montecito received a rainstorm 1 month later, which led to this really devastating debris flow, leading to deaths, as well as many people losing their homes. In other cases, having an extreme wet event co-occur during a dry period or after a dry event can provide some relief. So this is a very recent and close by example of the snowstorm that occurred after the Marshall Fire this past December, and having this snowfall occur helped impede any further fire spread and enabled some relief to the community. And so we have reason to believe that these types of wet events co-occurring with dry events will increase in the future. This paper by Daniel Swain et al. Showed that the frequency of going from a very dry to a very wet year is expected to increase in California throughout the 21st century. So this is what he referred to as climate whiplash for both Southern and Northern California. And another study showed that the same year, burnt area and precipitation intensity is expected to increase in many parts of California. So that's the red regions here are expected to have more, have years where you have higher burned areas, larger burned areas, as well as higher precipitation intensities within the same year throughout the 21st century, or by the end of the 21st century. So today I'll talk to you a little bit about my recent paper that looked at how climate change impacts the risk of extreme rainfall following wildfire in the Western US. These are studying events that could possibly lead to things like the Montecito mudslides. And these are the awesome co-authors that I worked with on this study. And I'll also be talking about more recent preliminary work that I've been doing here at NCAR as a postdoc, looking at how extreme precipitation can kind of relieve or impede dry conditions, both in historic and future climates. So in the first part of the talk, so we found in this paper that there are increases in extreme fire weather events being followed by extreme precipitation events. So here I'm using the CESM1 large ensemble. We also looked at the Canadian large ensemble, but I'll just be showing results from the CESM1 large ensemble, and the results are quite robust across both. So what I'm showing here is a map of the frequency of extreme fire weather events being followed by extreme precipitation events for the Western US. So places where that are gray means that across the ensemble, there weren't enough of these compound events occurring to really show here. And where it's stippled means that the difference between the period we're currently in and the historic period, which we took as 1980 to 2005, was not significant. So you can see that there are these events occurring. So these are extreme fire weather events occurring, extreme fire weather events being followed by extreme precipitation events within 6 months. So you can see that there are some events there. Going into the future, we see increases in these number of events, especially over the Pacific Northwest, but you can also see significant increases in California, parts of Colorado, and really across all of the Western US. We see similar changes if we look at extreme fire weather events being followed by extreme precipitation events within 1 year. You can see much larger increases, especially in the Pacific Northwest, parts of California. And what this really equates to by the end of the 21st century for California, sorry, for the Pacific Northwest, this equates to more than 85% of all extreme fire weather events being followed by, are going to be followed by at least one extreme rainfall event. And in California, around 2/3 of all extreme fire weather events will be followed by at least one extreme rainfall event. So this is really striking findings of these types of compound events. And we do see that these type of compound events are these increases are being driven by the individual components of these events. So we're seeing here, I'm just showing California, but for all the Western US, we're seeing increases in extreme rainfall events, which I'm showing here on the y-axis, as well as extreme increases in extreme fire weather events, which I'm showing on the x-axis throughout the future period. And you can see that by mid 21st century and by the end of the 21st century, this increase is quite robust and outside of the natural variability, which I've shaded here in gray. Oops, wrong way. And if we dive into this a little bit more closely and look at the seasonal changes in these two types of events, we see that for California, that there are going to be increases in extreme fire weather events during the fire season or summer season, as well as increases in extreme rainfall events during the wet season, moving into the future. And we also see that the distance or the kind of the separation between these two types of events are shrinking, leading to more extreme fire weather events being followed by extreme rainfall events occurring in the fall and the spring. So here, what this is showing is the number of extreme fire weather events followed by extreme rainfall events in the three periods. So you can see in the dark teal and the middle teal that there are increases in 3-month and 6-month events going into the future. So all of these results point to a future with more of these post-fire hydrologic risks or events that can potentially lead to debris flow, flash floods, and other just compounding impacts in general. So here are some quick takeaways for this study. So we see that there are large increases in extreme fire weather and extreme rainfall events. And these lead to increases in this frequency of this compound event of extreme fire weather events being followed by extreme rainfall events by really large amounts across the Western US. And the most striking finding is that by 2100, more than 90% of extreme fire weather events will be followed by extreme rainfall events within 1 year. And in the Pacific Northwest, around 7 extreme rainfall events will occur after an extreme fire weather event. So to kind of flip it around now, I wanted to understand how and when extreme precipitation events alleviated dry conditions. So this is kind of an example. This is the example of the snowstorm that occurred after the Marshall Fire and helped impede fire growth. So the main questions I'm asking are, what are the characteristics of extreme precipitation events that lead to the ends of droughts or fire seasons? How do the characteristics and impacts of extreme precipitation events change? And what drives changes between the historic and future periods and the co-occurrence of these events? So the way I'm tackling this is by tracking extreme precipitation events in space and time. So here I'm showing an example of this in the CESM2 large ensemble, which is what I'm using in this part of the study. So we find grid points that exceed the 99th percentile of the historic distribution of precipitation. And we track them in space and time. So here you can see this event moving over California. It's probably an atmospheric river making landfall and kind of continuing on its way. At the same time, I calculate the change in the soil moisture over their footprint. So here I'm showing the change in the soil moisture anomaly as the event passes over the area. So you can see for this event, there's a wetting in the soil moisture as it makes its way inland. So I track events, extreme precipitation events, and 40 ensemble members. These are the ones that currently have daily soil moisture for the historic and full 21st century periods in the CESM2 large ensemble. And so just to give you kind of a number, for each ensemble member, we have around 3,000 extreme precipitation events for the Western US. And I've divided my analysis into 3 regions because they have slightly different characteristics in their extremes as well as in their dry seasons. So these are really new results. Still trying to, understand what they're telling me. But what we find are that longer and more intense extreme precipitation events lead to larger local and daily soil moisture increases. So what I'm showing here is the average intensity of an extreme precipitation event throughout its lifetime on the x-axis, and then the change in soil moisture of that event on the y-axis. And I'm showing it for 2 different time periods. In orange is the future period, the end of the 21st century, and in gray is the historic period. And so these are the marginal distributions for each of these events. So you can see there's a bit of the tail lengthening in the future period to more extreme values for both the intensity of extreme precipitation events and changes in soil moisture during these events. You can see that generally increases when you have higher intensities of extreme precipitation, we have also larger changes in soil moisture. You can see that this kind of relationship kind of stays the same throughout the future period, but you can see that it is spreading more into the tails. Well, I also find that the duration of extreme precipitation events matters for how much soil moisture change we get. So for both the historic and future period, when we have a shorter event, so 1 day or 2 day event, these generally lead to smaller changes in soil moisture than longer events. Though I'm still trying to really understand this relationship in general. There seems to be a bit of a plateau here at the end. I also wanted to look at more regional and seasonal scale conditions.
So you're at 12 minutes.
Okay, this is my last slide. And So I wanted to understand how kind of regional and seasonal conditions are impacted by extreme precipitation events. So now I'm showing on the x-axis the average intensity of extreme precipitation events. And each bar here shows, each box here is for different seasonal soil conditions. So in reds are very dry seasons, and in these dark teals are very wet seasons. So you can see that the average intensity of these events don't really make a difference in how dry or wet a season is, which I thought was interesting. On the other hand, the number of extreme precipitation events in a season seems to have a bigger influence on how dry or wet a season is. So wetter seasons have more events. And this is something that's kind of been found before, where the total amount of precipitation is usually driven by the number of extreme precipitation events versus how much precipitation you get per event. So this is kind of consistent with that. And if we look to the future, we see that this relationship kind of stays the same. We do have more events in the future, but the relationship in terms of the amount and number of extreme events stays the same, and how wet a season is stays the same. So overall, we found that I found that kind of the impacts of extreme precipitation events are spatial and temporal scale dependent. It makes a difference whether you're looking at local scale differences or regional differences. We found that more intense extreme precipitation and larger increases lead to and there are also larger increases in soil moisture in the future. And what drives these changes between historic and future periods is still to be determined. Kind of their what drives their changes in their co-occurrence is still to be determined. So I'll stop there and take any questions if there's time.
Thanks. Any questions for Danielle? Yeah, Maria.
Hi, Danielle. Great talk. That was really interesting. I have a quick question about some of the first earlier slides that you were sharing had discussion about compound events. And so I don't know if this is a silly question, but I was curious about like the spatial extent and how far apart in time these events can be to be considered compounds.
Sorry.
No, go ahead.
So for things like post-fire debris flow and post-fire landslides and flash floods, there's studies that have shown that having fires lead to conditions conducive to these types of debris flow and flash floods for up to 8 years after a fire in some cases. So there's been some observational studies that have measured kind of debris flows and flash floods after fires over old fire areas or burn areas. And they found that these impacts can occur for up to 8 years in some cases. But the riskiest time is really between, just right after a fire to around 3 or 4 years.
Great, thank you, Danielle. That was much longer than I thought. Thanks.
Yeah, it's really, yeah.
And Sanjeev, if it's a quick one, and maybe Jerry, you could bring up your slides while.
Oh, let me stop sharing that.
This was very interesting talk. I was wondering, the soil will have the limited capacity to store. So how much your future projection is kind of biased by the limited capacity of the soil? Like in the 10 centimeter, you can maximum store 10 centimeter of the water. That's a maximum. So is some of the future result is biased by is it more drier before it rains and then it gets more increase?
Yeah, I did look at that kind of do you mean the antecedent conditions? Yeah, so I did look at, so I have only looked at the 10 centimeter soil moisture so far, but I'm definitely planning on looking at more of the total depth or deeper levels of soil moisture. And I did look at how the antecedent conditions of the 10 centimeter soil moisture impact the change in the soil moisture. And I did see that initially drier soils do lead to larger changes in soil moisture after an extreme precipitation event has passed through. So that's something that I will look at more at different depths as well, moving forward.
Thank you.
Thank you.
Okay, thanks. So we'll move on to the next speaker, Jerry Meal, who's going to tell us about the Dust Bowl.
Thanks, Isla. So I want to acknowledge co-authors Haiyan Teng and Guy Walton in this work. So the Dust Bowl drought of the 1930s, and it's usually nominally said to span 1932 to 1939, was one of the worst natural disasters of the 20th century, and it generated some amazing imagery. These are just some examples here, these giant dust storms rolling across the Great Plains, the Dorothea Lange photos of kind of refugees from the Dust Bowl. And she had a whole series of very famous photos taken of those people who were driven off the land. And these people living there dealing with basically what's just bare dirt and hundreds of square miles of bare dirt, basically. So there's been a lot of work done trying to understand this phenomenon in the 2000s, and it's now thought to have been caused by a combination of negative IPO in the tropical Pacific and positive AMO in the Atlantic. This forced an anomalous frost-free wave train over North America to produce naturally occurring drought, along with associated heat extremes, but it actually was made much worse by disastrous land use practices. Basically, the Great Plains were plowed up starting in World War I, when there was a big push to produce more wheat. And then when the drought started in the 30s, the crops died and you were just left with bare dirt, and that produced these tremendous dust storms. And the dryness and dust were thought to have intensified the drought as well as the heat extremes. But it wasn't just the Great Plains that were hot during the 30s. So if you look at this GISS temp reconstruction of temperatures, you can see that it was really hot here over the central part of North America, but the heat extended over pretty much over the entire US and all the way up into Canada, areas of Northeastern Asia, areas of Northeastern Europe. And so keep these areas in mind, these areas of Northeastern Europe and Northeastern Asia, because we're going to be talking about those in a second. So I'm going to talk about these heat extremes in terms of daily temperature records. And so if you watch any TV broadcasts or Weather Channel or anything else, a lot of times for a given day, they'll have, and this is from 9 News, which is one of the local Denver TV stations. This is a really cold day, but they usually say today's high was 17, the low was 1. The average high for this date was 46, the average low was 18, and the record high for this date was 69, set in 1885, and the record low minimum was -3, set in 1873. So there's kind of a lot of awareness among people about kind of how you're experiencing the weather on a given day in relation to the records. And of course, record heat versus record cold is something that we're interested in. If you had actually a stationary climate and you took the ratio of record high maxima temperatures being set to record low minima at a given location, it'd roughly be 1. So there'd be equal chances of setting a daily record high maximum or daily record low minimum, and averaged over enough locations and over enough time, there'd be about, the ratio would be about 1. But if there's warming or if there's anomalous warmth, this ratio will actually increase, because you'll have a better chance of setting a record high maximum temperature compared to a record low minimum temperature. And over the US right now, we're up to about a ratio of about 2 to 1. So we're now twice as likely to set a record high maximum at a given location than a record low minimum. And we kind of looked at this in this paper that's was actually published in 2009. And there's also, we looked at this again in a paper in 2016, where we related the warm anomalies, temperature anomalies, to the magnitude of the record ratio. So as you get to warmer anomalies here, you get higher records ratios. And it stands to reason that as the average temperature warms up, you're going to get more extreme heat, less extreme cold. And so that is actually a relationship that we've seen over the observations over the US and elsewhere. And if you look at this in a climate model into the future, you can imagine that as the average temperatures continue to warm, the records ratio continues to rise. You get even more and more record high, record heat and less record cold. Now, the Dust Bowl in the 1930s was pretty unusual for the US. And this is just a plot of a subset of stations over the US showing the average temperature over the continental US, showing that the 30s here was about as warm as it's been in the 2010s. In fact, from this compilation, the 2010s aren't even quite as warm as the 30s. So when you show a plot like this to an audience, they immediately say, well, what the heck's going on? We thought that the warming has been due to increasing greenhouse gases, but it was actually as warm in the 1930s as it was now. And so this is kind of an interesting question to ask as to what was producing that record heat in the 30s when the greenhouse gas forcing wasn't near as high as it is now. And of course, this warmth of the 30s is reflected by the ratio of record highs to record lows. And this depiction here shows the departure from a 1-to-1 ratio. So these red bars are values where you have a ratio greater than 1, and the blue bars are a ratio less than 1. And we average these by decade over the United States. And the source of this is the NCEI records database. And you can see the 30s stand out, as you can expect. When the 30s were really warmer in the US, we had a records ratio. The actual ratio is 1.7 or 0.7 above 1. And it's taken us up until the turn of the century here, up till we've gotten to records ratios that were approaching what we saw in the 1930s. And it wasn't just the US. So when we were looking at that GIST temp reconstruction of observed temperature anomalies for the 30s, I noted that other areas of North America, like Canada, were actually anomalously warm. And sure enough, when you look at the records ratio for Canada, you can see that the 1930s had a ratio of about 1.6. I was talking about northeastern Europe, northern and northeastern Europe. And if you look at the data from Sweden, you can see the 30s stand out here, a records ratio of 2.7, which is still higher than what's even been experienced in Sweden since the turn of the century. You look at the UK, a very high records ratio of 2. And again, that's comparable to what we've seen currently. And even in Russia here, which is a much bigger area, but probably the northern part of Russia is contributing to this, you see the 30s stand out compared to other decades up until more recently. So these heat extremes were actually occurring in other areas of the Northern Hemisphere when it was anomalously warm in these other areas of the Northern Hemisphere. So it's kind of accepted that even though the tropical Pacific and Atlantic sea surface temperatures caused the drought and the disastrous land use that produced these dust aerosols intensified it, the question we were going to ask here, could the resulting extreme land surface conditions themselves be a contributor and affect total US mean temperature and heat extremes? And then could the drought itself have affected mean warming and dry conditions and heat extremes over other areas of the Northern Hemisphere? So to look at these questions, we're going to analyze a model sensitivity experiment where we set soil moisture over the Great Plains to 0. And this is in an atmosphere-only version of CAM5. The land surface is fully coupled outside the Great Plains, and we have climatological SSTs specified elsewhere. We run 100 ensemble members May through August, and compared to a long control run. And I'm going to show averages for this warm season, May, June, July, August. And the initial results from these experiments were described in a paper by Haiyan, Tang, and co-authors in 2019 in Journal of Climate. So what ends up happening in this sensitivity experiment? Well, as you can imagine, over this box here where we've set the soil moisture to 0, it gets really hot. And this heat spreads out over other areas, pretty much over the rest of the US and up into Canada. It also spreads to areas of Northeastern Asia and Northeastern Europe. And the reason this is happening, as Haiyan and co-authors showed, is that the heat that's produced from these dry soils heats the lower troposphere, and the lower tropospheric heating drives this anomalous wave 5 teleconnection. So this is a summertime teleconnection being driven solely from heating over the land surface over the central part of North America. And as you can imagine, where you get these anomalous high centers, that tends to be associated with these warm areas of the surface. And just to show you how hot it got in other areas, of course, it got very hot over the Great Plains box, over 4 degrees centigrade, but over the rest of the US outside the box, it was about 0.4 degrees C. Over the whole Northern Hemisphere, warmed up 0.15 C. Over the Northern Hemisphere land on average, 0.31 centigrade. Globally averaged almost 1/10 of a degree warming, which is almost what you get from a volcanic eruption in terms of cooling. Global land temperatures warmed up at 0.2 of a degree. So the sensitivity from this response over just this one area of North America really can extend globally. You look at the records ratios, which is kind of what we're looking at for heat extremes. Of course, you get these big increases of records ratios. In other words, you get much more extreme heat over areas, not just over this box where we drive out the soil, but over the rest of the US and other parts of Canada. And this color bar here, areas above or ratios above 1 are kind of these lighter blue colors. And you can see that in areas of Northeast Asia and Northeastern Europe, you're seeing records ratios approaching 2. And if you actually look at some of these area averages, these are some of the records ratios over some of these areas. Continental US, we get a records ratio on average of about 8. So 8 record highs to every 1 record low. The Great Plains, where we dried out the soil, 9 record ratio. Outside the Great Plains, it's about 6. Over Europe, it's about 2, and Northern Asia is about 2. And I highlighted the 2 here because that's roughly where we're getting to now in the observations in terms of what the records ratio is more recently. So what's producing this? As we saw, when we heat up or when we dry out the soil, we get this really hot patch here over the Great Plains that produces lower tropospheric warming, and that produces a teleconnection pattern that High-End documented. It's an almost wave 5 teleconnection pattern, but what's actually spreading this out over the actual rest of the hemisphere? If you look at vertical velocity, omega at 500 hectopascals, the blue colors are anomalous upward motion, red colors are downward motion. So where you're heating up the box here, you're getting warm air rises, you're getting a strong upward motion, we're getting strong subsidence all around this box here. So that's producing, and this teleconnection pattern is producing some substance in these areas of Northeastern Asia, Northeastern Europe, and Northeastern Asia. And where you get substance, you get decreases of clouds. So these blue colors are decreases of clouds in other areas of Northern Hemisphere and North America and Northeastern Europe. And that means when you have less clouds, you have more incoming solar, and the net surface heat flux increases over these areas. So you can spread this influence of a regional drying of the soil hemispherically through this teleconnection pattern and these physical processes that produce these changes. So just to summarize, the 30s Dust Bowl drought over the Great Plains was likely initiated by atmospheric teleconnections from the tropical Pacific and Atlantic, and it was intensified by dust aerosols from these bare soils, from these ridiculous land use practices that were happening during that time period, which were unique in the history of North America, I believe, thank goodness. A climate model sensitivity experiment indicates that the Dust Bowl, those conditions could themselves then produce this lower tropospheric heating and this anomalous wave 5 teleconnection pattern at 200 hectopascals that spreads the influence hemisphere wide through these teleconnections. And so the drought itself can produce heat extremes, and indicated by those large amplitude ratios of the record high maximum and daily record low minima over the Great Plains themselves, as you'd expect, but then that spreads the influence out through these teleconnections, so you get heat extremes over most of North America and other regions of the Northern Hemisphere, including these regions of Northeastern Europe and Northeastern Asia. So that's all I had. Thanks.
Thank you. Clara?
Yes. Hi, Jerry. Thank you. That was really interesting.
Thanks,
to
Clara.
think about these teleconnections. I just wondered, since the soil didn't completely dry out during the Dust Bowl, or maybe it did, but if you scaled that result, by, really what the soil moisture depletion was, how big of an impact would that have relative to AMV and tropical Pacific influence?
Yeah, well, that's kind of a good question. It's also kind of hard to know exactly what the land conditions were like during the 1930s. We can look at reanalysis of land conditions from some of the reanalysis project products, and I think we may end up doing that. obviously, this is a big kick to the system. It's a sensitivity experiment to actually see what happens if you can actually pick up these signals, and it looks like you can. So I think the next step in this is to actually maybe look at a more realistic, or at least figure out what more realistic would be. And of course, then there's papers written about the dust aerosols enhancing it and intensifying it. So it's a kind of a combination of things that really made that drought so intense. The other thing we want to look at are the pacemaker experiments that I was talking about during your talk, where we put idealized AMV and PDV patterns and run pacemakers from those areas just to see kind of how those regions respond over not only North America, but elsewhere. The previous work on this has been mostly done with kind of AMIP style experiments where SST anomalies that were observed were put in these different regions. But I think the pacemakers would be kind of interesting to see kind of what was coming from the Atlantic and from the Pacific as well.
Thanks.
Yep. Flavio, a quick one.
Oh, a quick one. Yeah, thanks, Jerry. I agree with Clara. That was really interesting. I guess I only had a question on effectively the error bars, or in other words, like how probable is it that this mechanism actually led to the pattern that we observed? Because we only observed the one pattern in reality. Obviously, the sensitivity experiment is like pretty convincing, but it is like it's a much larger sample size. So like, would the straightforward idea be to look at composites of droughts in a long, fully coupled control and see how, look for droughts in that region and see in a fully coupled system how often you actually get that pattern. Yeah, so I don't know, just curious about that sort of robustness part.
Yeah, that'd be one thing to try. But again, the intensity of this, and when experiments have run in the past where they just put in AMIP anomalies for Atlantic and Pacific, they can't get the intensity. And there's these experiments where they had the dust aerosols added. That's where you really get the intensity of the drought. So it's a combination of things. So you wouldn't quite get that, I don't think, in a long control run. I mean, we could look at the types of droughts and maybe look at what they were like in the model to see if you get anything that looks like that pattern. The other catch with these things, as you can imagine, is when you look at these different reanalysis products, and you're trying to see what the actual observed patterns were in the 30s. There's differences among the products, right? So that's another kind of caveat with this is the thing we liked about the GIST temp is it seemed to really correspond well to those big records ratios that we saw in Northern and Northeastern Europe. So that probably was real in terms of what was happening there. And that is something we see as a teleconnection from the dry soils. But of course, everything's happening at the same time. So I think this drying out of this summertime teleconnection pattern from the Great Plains would be something that would add to the effects that were being also driven simultaneously by the anomalous SSTs in the Pacific and Atlantic.
Okay, thanks. If there's any more questions for Jerry, you can put them in the chat. And so last but not least is Flavio, who's going to tell us about multiple feedbacks in the extreme 2020 anomaly over Siberia.
Great, thanks. Yeah, thanks for hanging around until the very last talk. I'll try to go quickly. In part because somebody recently said they saw a recorded talk of mine, probably aged you, and they played it at twice the speed. And they said I sound Irish if they do that. Yeah, I'll leave that judgment for you, but I guess it means that I could talk faster if people go in and watch my recorded talks at twice the speed. So we'll see if I can get close to do that today. So this is work, that by now like a long list of collaborators, Ayla, Clara are on it, and others. And it's in a way part 2 of a talk I gave last summer already at the Climate Variability and Change Working Group on this persistent temperature anomaly over Siberia in 2020. And I'll sort of briefly run through the first part, which is very similar to what I've shown last summer, and then a few new bits around that. So this is the temperature anomaly of the entire year 2020 relative to 1950, 1998 from the Berkeley Earth temperature. And the main point is it was very warm, not just in the early part of the year, which caught a lot of headlines, but also throughout the year, leading to this like large anomaly over the region. The interesting part was actually, or the part that I was most interested in, was not so much the individual temperature records that were broken for a given month, season, or day, but sort of the persistence of the event. And you can sort of see that by the daily temperature anomalies over the course of the year over this box, that it's really very persistently warm. Really only in December, it was sort of below normal temperatures. And again, this is the time series now for annual temperature over this box from different observational and reanalysis data sets, where you see that the year 2020 stands quite a bit above the rest of the century. And so the first part of the talk and the research was really just to try to understand perhaps what could have led to this exceptional persistence. So again, here you see the temperature time series in annual means, and also a mean of a large ensemble, a collection of large ensembles to give you sort of an estimate of our understanding of the forced component of this. You know, if you average all the models, we get an estimate of the forced response in green. But then more importantly, sort of for the remainder of the next couple of slides, is this breakdown into monthly temperatures over here. So on the x-axis, we have calendar month, and then on the y-axis, we have temperature anomaly. And all these gray lines are individual years from 1850 to 2019. But the main point is the year 2020 in solid black, which again showed like these strong temperature anomalies throughout the year, really, other than perhaps July and December, they were quite exceptional. You see in the dashed lines in the back, the 3, 2, and 1 standard deviations for these individual months. So in a way, like maybe not any individual month was like sort of record shattering. This new term we've learned last year, thanks to the Pacific Northwest heat wave. But the persistence, so like this, the fact that almost every month was at least one standard deviation above normal, really led to an exceptional year overall. I know now we try to break this down with like a familiar method or two at least. Dynamical adjustments, so trying to understand how much of these temperature anomalies were due to atmospheric circulation anomalies, and then we have the residual, which we sort of tend to interpret as more thermodynamically driven. And this is just an example for January-March mean. So this is the temperature anomaly in the shading for that period, and sea level pressure anomalies in the contours. And then the dynamical adjustment comes up with an estimate of the temperature anomaly that occurs typically when we have this kind of circulation anomaly. So this is can be done with two different methods. The paper are over here. They tend to, as you'll see in a second, they tend to provide quite similar results. And then if you subtract this dynamical contribution from the total, you're left with this residual. And so you can then start to ask questions whether this might represent something not related to atmospheric circulation, but maybe more thermodynamic feedbacks. If we do this for the entire observational data set and we look at the residual time series or the time series that result, we get this blue series as the dynamical temperature contribution, which we see was like very large in the year 2020. And if we look at the breakdown in months, we see that it was particularly large in the early part of the year, kind of, consistent with what we see in these maps for January to March. But then it was actually not that significant for the rest of the year. And so the residual is then sort of filling in these gaps, and we see that actually, especially the second half of the year, was more dominated by this residual. And so the question is like, what processes could have led to this large residual contribution and maybe more thermodynamically driven contribution? And this is again sort of like similar to what I showed last summer. There is, if you go into the literature, there's like a whole list of recipes that can lead to sort of a recipe for temperature persistence. Some of the papers are specific to this region, others are more general. And so like, just to run through some of them, like especially for this region, a strong polar vortex can lead to a positive Arctic oscillation. The Scandinavian pattern can also lead to month persistent in temperature anomalies. These patterns themselves can sort of be reinforced and prolonged by North Atlantic SSTs. And then I'm sort of calling this maybe more of the dynamic contributions. And then as we turn to the land surface and maybe more feedbacks, you can think of interactions with snow cover, soil moisture, and sea ice anomalies. And obviously there's also interactions between those that are possible. And so to tease that out, we looked at all of these potential drivers of temperature persistence. And without going into too much detail, a lot of them were in quite an anomalous state. So this is a measure of the polar vortex strength, Arctic oscillation, Scandinavian pattern. So all of them were really lined up, especially in the first half of the year, to really produce this strong temperature anomaly that we've seen. This is just, sorry, I'm going to skip over this, but this is confirming that these mechanisms do correlate with, with the respective variable that we care about. So polar vortex can lead to positive AO. AO can drive temperature variability, the same for Scandinavia. But then I want to spend a little more time talking about these maybe more thermodynamic drivers, the snow cover, the soil moisture, and the sea ice sort of along the Siberian shelf. And all of them had like relatively low values, some of them record breaking during the year 2020. And again, if you combine that with the knowledge that those are correlated with those driver variables are correlated with temperature, then you can start to draw a picture of what might have driven the thermodynamic component. And now these correlations down here are broken up actually in correlation with the total temperature in black, but then also these more thermodynamic residual and the dynamic residuals from the dynamical adjustment. And so from this, we can see that, yeah, indeed, these tend to correlate much more closely with what we think is the thermodynamic driver. So again, like sort of like a consistent story here. And then we can use these three drivers, snow cover, soil moisture, and sea ice, to try to reconstruct the residual that we've seen in the overall plot. So this is, again, the total temperature anomaly over the years. And then the red one is the residual, and the orange one is a construction through multiple regression with these three predictors: snow cover, soil moisture, and sea ice. And we can recover a lot of the month-to-month variability from those. So that seems to be general sort of a consistent story. And now the second part, I'll see how far I get this time, is really trying to see if models are able to reproduce some of these mechanisms that can lead to persistence from month to month, and also how those might change over time. For this, we look at multiple large ensembles. I'm probably just going to show the example of one. Yeah, you've seen a couple of collections of large ensemble simulations out there. This is just for illustration, the annual mean temperature over Siberia from a range of those models. So what we're doing here now is actually not care too much about the forced response per se, because we see that all of them are warming under RCP 8.5. So we'll expect these kind of events to become more frequent. That's pretty straightforward. What we're asking here is more like, is the character changing, or the influencing drivers changing over time? And for that, we detrend our simulations with the ensemble mean. So we have effectively detrended time series to work with. And then we go in and look at whether the probabilities of these consecutive anomalies and this persistence changes over time. So we're looking for the probability of consecutive anomalies over one standard deviation. Again, from these detrended time series now. And more specifically, for reasons that will hopefully become clear, we're actually looking at the odds, which is just the probability of such a consecutive anomaly, such consecutive anomalies divided by 1 minus that probability. So if you look at that for the CSM2 temperature over Siberia, we come up with this kind of curve. For now, ignore the colors and just look at the general pattern. So what this tells you is that, like, in spring, we have a higher chance to see these persistent temperature anomalies. So for a temperature anomaly of 1 standard deviation to actually survive to the next month. And kind of the same story, oops, I think my mouse just went. Kind of the same story in fall, where we have more persistence. But then I do want to draw your attention to the colors, which each line is based on 50 years of data and expressing the survival odd for a particular 50-year period. And so the color bar for those periods, the center year is given on the right-hand side of the slide. And so what this allows you to do, if you then run through your large ensemble, again, all detrended, you can look at changes in the survival odds as a function of time. And so, like in this particular case, there's generally lots to look at, but what we see for CSM2 for temperature survival odds is that For example, they tend to increase in spring in the future and decrease in early spring and in fall in particular. And so there's lots of reasons that could lead to this. In this part, we're mostly focusing on these thermodynamic drivers to ask like whether they had anything to do with that. And for that, we're looking at odds ratios. So before we were looking for the probability of consecutive anomalies and the odds of that. And now we're looking for those same kind of events, but we're adding an additional criteria. And we're asking whether we've seen consecutive anomalies when in the first of the 2 months, we've also seen an anomaly in one of these driver variables, like snow, soil moisture, or sea ice. So sort of a conditional probability, well, before we had an unconditional probability. We can again calculate the odds of that, and then the odds ratio, so just the odds, the unconditional odds, or sort of the conditional odds divided by the unconditional odds will start to tell us whether the odds are changing because there is a change in one of the driver variables. And so if you look at one example, this is now snow cover. So now we're looking at odds ratios. So basically when we have values over 1, then it is more probable to have a temperature anomaly survive from 1 month to the next if in the first months there is also a snow cover anomaly present. And so on the one hand, we see that like it's kind of a mixed bag. There's certain months where snow cover does influence the temperature survival probability. That's kind of consistent with what we've seen. But then we also see that this is changing. We have a couple of months of the year where this influence of snow cover on survival probability goes up. In other months, it goes down. And then we can do the same thing for soil moisture and sea ice and see if they start to tell a coherent story in terms of the overall temperature survival odds. And depending on where I'm at with time, I can talk longer or less long about this. But
13 minutes.
Okay, great.
But yeah, I mean, you're the last one, so it's okay.
Perfect. I think the gist is that it's not straightforward to interpret some of these results. I think some of the more consistent things are that we think that sea ice, for example, we know well in the future will disappear. And so its influence on temperature survival probability, especially in fall, where currently we sometimes have sea ice, we sometimes don't, that'll sort of go away. And that's kind of what we see in the rightmost panel in the fall, where we see these lines as they go towards yellow, they really go towards 1 or even below 1. In other seasons, this kind of melting of sea ice might start to bring a stronger influence of survival probability because we're shifting into a regime that can sometimes have ice, sometimes not. And so we see these relatively complex changes in probabilities. Some of them you can sort of interpret reasonably well, and others are honestly not super straightforward to me. The thing that was most confusing to me, and I'll just briefly show this, is that it's not very consistent across models. I'm showing here the CSM1, CSM2 large ensemble, and the MPI large ensemble for these kind of same questions. So if you just look at the survival odds per se, the leftmost column, they tend to sort of agree on the story, but then the influence of the individual thermodynamic driver on that story is a little more muddled. Right, and I think I'll leave it at that with these conclusions. I think, yeah, it's a nice application of large ensembles to detrend them and start to dig into the more nuanced questions of probabilities and how they change under warming. Yeah, that's like sort of a little bit work in progress, how to interpret those. Thanks.
Thank you. Any questions for Flavio? Yeah, Danielle? You're muted. Right.
All right. Thanks for the talk. It was really interesting. I was wondering about fire-related aerosols in that region, and if you think that had an effect in driving or reducing the persistence or level of temperature anomalies during 2020. And is that something we would be able to see in these large ensembles as well going into the future?
Yeah, that's a good question, especially following sort of from Cherry's talk. It might be worth looking at, yeah. I mean, to the degree that aerosol emissions from fires, yeah, as long as sort of the chain of processes is like reasonably well represented in the model, right? So In reality, we did have fires, and you could argue that the Siberian fires were certainly benefited from the dry and warm conditions. And so I think that might be worth looking into. I think like one of the points I've made here in the conclusion slide is, that I feel like this framework should be, can be easily expanded to include actual impacts like the fires. Another one was sort of the permafrost thawing that seems to sort of depend a little bit non-linearly on persistent anomalies. So like if you actually have multiple months of above normal temperature, it can actually do more damage than individual months if you sum them up. So yeah, I think that'd be a nice question to look at next.
Cool, thanks.
And Clara?
Flavio, thank you for your great talk. I'm a little confused about the relative roles of just this anomalous circulation in the early part of 2020 that then seemed to trigger these thermodynamic feedbacks versus just the background force response. So yeah, I think this figure, maybe you can just speak to that for a moment. So you're talking about these feedbacks from this underlying surface that were not triggered by the circulation, because that would be part of the dynamical adjustment, but they are externally forced. Or do I have that completely wrong?
Yeah, that's you're right that I kind of did not spend time on that important nuance question. So to briefly step back, like what all you see here, including the regression results on the right-hand side, so the orange line on top of the red one, are based on data that's not detrended. Although I do have made all of these plots also with detrended data. So like, yeah, before doing any of these calculations and regressions, I try to remove a force trend, especially in the temperature component. Generally, you're able to recover a lot of the sort of the anomalies that you see in the red line on the top right as well. But you overall explain a little bit less of the variance of your time series. So like a part of this, both of the variability and sort of the magnitude of the red line is actually coming from the forced response. So the mere fact that this region is warming, and it's perhaps warming unevenly in different seasons. But the general influence of these individual drivers on causing anomalies, let's say more in the second half of the year, that kind of story is consistent even if you detrend it. So that's like just sort of to answer that part. And then the other one is a little more difficult to answer. You could easily imagine that, a circulation anomaly has an influence on snow cover, but then we're using snow cover to talk about more thermodynamic drivers. So I don't think I can perfectly separate that here. We do have interaction terms now in the regression model that are significant, I think, in particular for snow cover. So that kind of speaks to that, but I'm not quite sure how to cleanly separate that. So I think, again, it comes back to the fact that these are empirical methods to make the dynamical adjustment. And so it's an estimate of the predominantly dynamical contribution, and the residual is like hopefully predominantly thermodynamic. But I think we're still at the same place in terms of what we can truly attribute those to. They're all always caveated a little bit.
Thank you.
Okay, thank you. So thanks to all the speakers for all the great talks today. So we're done with the presentations, but now we have the update of the CVC WG. And so Flavio, I don't know if you could.
Yeah, sorry. I think the battery of my mouse just ended, so I gotta find the trackpad on my.
Okay, maybe I can make
and then I'll stop share. Yeah, there we go. I think.
Okay, great.
Sorry about that.
So yeah, I hope you will stick around for this, and we'll just have a sort of 10 or 15-minute summary of things that have happened over the last while and going, and then I hope we can have some discussion of a couple of different things, in particular, any simulations that you'd like to see us propose in our next allocation. That doesn't happen till August, but really it's now, and then the summer meeting are the chances to discuss this. So let me just Okay, so I'll kick this off on behalf of my fellow co-chairs, Sarah Larson and Aisha Hu, who they'll chime in at certain points here. So this is what we're going to go through, and I don't think it'll take as long to go through as it looks. So just an update on the new simulations that are available or are about to be available, and what we're going to be doing over the next few months. And then also just a kind of reminder, and for people who are new, about some resources that are of relevance to the working group. And then we'll finish up with the discussion in particular on these two topics here. So we'll start with an update on what's new, what's become available. So for the GOGA extensions, so these are simulations that are run with prescribed time varying sea surface temperatures taken from observations. And we've been extending these as we can because there's this ongoing drought in the US Southwest and people have been interested in looking at that. And so these simulations currently go to April 2021, and we'll probably extend them out to the end of 2021 when the SSTs become available. And you can find information on where to get the data from these simulations on the website there. If you just Google the working group as well, you'll get to that. So this is another new set of simulations, which is one of the things we had proposed to do in our last allocation. And this is kind of a preliminary pre-industrial control that is being run with the new, or kind of the new grid that will be used in CAM7. So in case you're not familiar with this, there's a plan to move toward higher vertical resolution in the next version of the model. And what you're seeing here is kind of the vertical resolution. So the x-axis is the grid spacing. So low numbers means high vertical resolution. And then the y-axis is the height within the model. And so in CSM2 generation, we have CAM, which has the black dots here. And we have WACM, which is the high vertical resolution model, which actually goes a lot higher than what you see on this figure. And so the plan is that we'll have this new red grid, which will be kind of the workhorse version of the model, which has a model top at about 80 kilometers. So it's kind of between CAM and WACM, but it also will have a lot higher resolution in the troposphere and lower stratosphere. And it will also have an increased resolution in the boundary layer. And the blue one is kind of cheaper version of that is not 80 kilometers, which will be used for anyone who doesn't care about what the stratosphere is doing and for tuning and things. And so as a working group, since we're interested in kind of climate variability and change, we wanted to get a sense of what is the impact of having this change in the representation of the stratosphere on the model. And so we proposed to run this new grid, but without the boundary layer changes. Once you change the boundary layer, you have to start retuning the physics. And so we wanted kind of a cleaner comparison than that. And this is using all of the current CAM6 things. So it's using the finite volume dynamical core and no changes to the physics other than some tuning of gravity waves. And so that's to really kind of be able to do more of a clean comparison with our low top pre-industrial control. So we have run a simulation that's 100 years long, fully coupled with this vertical grid. And so one of the things that we get with this new vertical grid is the quasi-biennial oscillation. So here you're seeing the time series of tropical average, zonal mean, zonal wind, and this is in the reanalysis. Our current CAM obviously does not represent the QBO, and even our current WACM doesn't have that good of a QBO. It doesn't come down into the lower stratosphere, which is where you might expect it to have impacts. And this is what the QBO looks like in this new grid. And so it's better in terms of the amplitude in the lower stratosphere. So QBO and having just a better representation of the polar vortex might impact on our representation of variability and change. And so I'm saying this is preliminary here because there are some confusions that are kind of ongoing at the moment. One is that this is run with specified chemistry WACM, and there are some differences in how forcings are prescribed in specified chemistry WACM compared to CAM6. So it's just something to bear in mind. I don't think it's a huge deal. There are also some differences in the representation of sea ice, which might be related to those differences, which is something to just bear in mind. The model does have a big bias in stratospheric water vapor, which probably doesn't matter too much for most purposes. And this is not something that is going to be fixed for this particular version of the model. So just a few things to bear in mind if you're looking at this, but probably still it is useful to, if you want to start looking at things like QBO impacts or teleconnections, once you have a good well-resolved stratosphere, please feel free to go and take a look at this data. This is the location here. We have not put it on the website yet because we haven't really looked at it ourselves and it's not fully vetted at this point. But definitely feel free to go and have a look. And if you come across anything weird, please let us know. And we are looking into running now a comparable simulation with CAM6 instead of specified chemistry WACM, just to try and minimize those differences that I talked about. And one of the reasons that we are running this configuration is that it's going to be kind of a baseline check on this version of the model that's going to be used by a group at Scripps to run a seasonal prediction ensemble. And they're going to be running 20 ensemble members of 1 year long hindmass from 1970 to now. And they've already run it with the 32 level model. And this is very comparable to the SMILE project that Steve Yeager has been leading, that you would hear about at the Earth System Prediction Working Group. But they're also going to run with this configuration and to try to have kind of a clean comparison of how does it change the predictability on this kind of 1 year long timescale if you improve the representation of the QBO and the stratospheric vortex. Another big project that's underway is the single forcing large ensemble, and this should become available later this spring. This has really been down to the work of Nan Rosenblum. And so the format of this ensemble is going to be 15 members for each forcing, running from 1850 to 2050 at this point. We may extend them if we have computing time. And they're using the SSP 370 scenario, and they're using a smoothed version of the biomass burning. And so overall, that makes these members comparable to the second 50 members of the CSM2 large ensemble, if you want to compare with the all forcing experiments. So the way we set this up is actually kind of the inverse of the CSM1 single forcing large ensemble that many people talked about today. The forcing that is of interest is evolving in time, and the other forcings are held fixed. So we have an ensemble of greenhouse gas simulations, an ensemble of industrial aerosol simulations, an ensemble of biomass burning aerosol simulations, and then we have an ensemble of everything else where we put all of the other things in together. And the idea of doing it this way was that we should be able to add these 4 up to the total. And so they're almost done, just the everything else's are still running at this point. So one of the interesting things that has come out of this is this additivity issue. And so what you see here on the left is CSM1. The black is all forcing simulation. And then the purple is what you get if you sum up the influence of the greenhouse gases and the industrial aerosols. And so remember, CSM1, it was everything but that forcing evolving. So to get the greenhouse gases, it's the large ensemble minus the run without greenhouse gases. And so in CSM1, you can see that they add up, those 2 contributions add up pretty nicely to the total. In CSM2, that is not the case. We see this nonlinearity, and it's not explained by the other forcings either. And so digging in a bit more deeply, if we just look at the impact of the aerosols, this is what you see. And so the blue is the impact of the aerosols in CSM2, and the red is the impact of the aerosols in CESM1. And so you can see that in CSM2, the aerosols are giving much more cooling than they were in CSM1. And the green line here is some additional experiments that we've done to try and understand the origins of this difference. And the green line is running CSM2 in the way we ran CSM1. So determining the aerosol influence by taking the large ensemble minus a 3-member ensemble in which we let everything evolve in time except for the aerosols. And you can see that that looks much closer to CESM1. So it's not the whole story, but definitely much of this story is the difference in the method that's being used. And so we're running complementary experiments now with CSM1 to kind of complete the story, to see what happens if you run with only aerosols with CSM1. And we'll document this in the description paper and probably provide some advice on what the best way to use this large ensemble is, given that the way we've done it now, they don't all add up to the total. Okay, I'll hand it over to Aishu to talk about this.
Okay, this is we call it the AMAC map simulation. And this is a project led by Laura Jackson from UK. Right now, there's about 6 modeling groups participating in this project. Basically, for this project, what we want to do is we want to test the stability of the AMAC after a hosting experiment. And what the figure I showed here is the result from CSM2. For CSM2, the black line is the control run, and the blue line is the freshwater hosting run, which we add 0.3 through freshwater into the North Atlantic, north of 50 degrees north, all the way to the Arctic, and stopped at the Bering Strait. What we see here is that during the first 50 years, the AMAC is dramatically weakened. And then from this simulation, we branch to other simulation. We stop the hosting at year 20, 520, or stop it at year 550. We can say is for the first one, the AMAC recovers within about 50, 60 years. And in the second place, when we stop the hosting at year 50 years into the hosting, the AMAC would not recover, at least during this 150 or almost 200 year simulation. Our result represent some similar result also reached by some other model, but also the other group of model shows the AMAC does not recover even we stop the hosting at year 20. So there's some differences of these different models. And right now, Laura Jackson, she's preparing a manuscript to document these differences and try to figure out what caused this different response of the AMAC. And this simulation right now for CSM and also other model group basically are done. And if you are interested to analyze this result, you can send an email to me. And I think all the modeling groups, they are willing to share the data with other people. That's it.
Okay, thanks. All right, okay, so now we'll talk about the forthcoming simulations. I guess 2 of them are being done under the working group resources, and then this one that Sarah is leading, she is doing that with a university allocation, but I think these simulations will be of interest to the working group more generally. So the first one is kind of the big project that we've been saying we're going to do for a while, and we are actually going to start doing it soon. And this is going to be a regionally refined North Atlantic AMIP simulation where we're going to run with this grid that refines down to 1/8 degree resolution in the North Atlantic. And so we're going to run from 1950 to the present day. We're going to prescribe observation-based sea surface temperatures that'll have 1/10 degree resolution that will come from a forced ocean simulation. That's really the only way to get that kind of resolution in the SSTs. And so I think this will be kind of one of the longest high resolution simulations we'll have, going to like this 1/8 degree. And the main motivation here is to see whether there's really any big changes in the representation of ocean atmosphere coupling or ocean influences on the atmosphere and on low frequency variability in the jet stream. And the data from this will be made available, but please let us know if there's anything in particular you'd like to look at to make sure we get the output right. And I think Sarah's put a link to a Google Doc in the chat where you can either write it down or we can discuss it at the end. Another thing that's been underway for a while, and this has been led by Young-Oh, and if he's still on the line, he can probably answer questions about this, is this pencil model. So this is kind of in between the slab ocean and a full 3D ocean in that it will have kind of has the representation of the mixed layer of physics at each location. And so we heard a talk today about how that might matter. And so they have been working on this pretty hard. I think there's been some issues. So they've run 2 100-year-long control simulations, but found there to be this drift that kind of made it unusable for really long climate simulations. And ideally, we want to have a long pre-industrial control with this configuration. And it turned out that that was due to an inconsistency between when they were initializing the run that they used to derive this flux correction term that needs to kind of represent the large scale circulation, I believe, and the climatology that was being restored to for that. So it sounds like there's a path forward for this. And if they're running tests now, and if this doesn't produce the drift, then they should be ready to be running a longer pre-industrial control. So hopefully if this works, then by the next meeting, we'll be able to let you know that has become available. I will hand it over to Sarah now for the mechanically decoupled.
Thanks, Isla. Yeah, so this is being done through a university allocation. I did my postdoc, Kate McMonigal, has done the lion's share of the work, but Dave Bailey and Nan Rosenblum have been really instrumental in getting all this off the ground. So kind of the science goals behind these simulations were, the first one was to determine how anomalous wind stress forcing is impacting the ocean and climate. And so for this, we ran a pre-industrial version of this framework, and sort of the technical details are that the wind stress forcing on POP, the ocean model, is fixed to the 6-hour climatology from the fully coupled run. So the ocean can't feel anomalous wind stress variability. So you can kind of figure out what's buoyancy driven versus what's not. And so we branched this from year 1051 of the fully coupled run from the CMIP6 database on Casper. And we've got about 600 years spun up. So there's a lot of data to look at. And so we're pretty much done with this run. We're trying to push the diagnostics paper out of the door probably within the next couple of months. So if anyone wants to start looking at this particular run, we can send the path. But until we get some of the initial diagnostics, we're kind of hesitant to make it publicly available just now. So the other run we're doing is a historical ensemble. And this has also just been completed. So the science goal of this was to determine how anthropogenic trends in the wind stress are impacting future climate and the related ocean trends. So essentially, we're taking the pre-industrial run and we're branching 20 members from that. And we're leaving the wind stress on the ocean fixed to the 6-hour climatology from the fully coupled. So any climate change induced trends in the winds, the ocean won't feel that. So we'll get a better sense of what trends that we've observed over the historical period, and we are going to push this into future scenarios as well. So what trends were due to changes in the atmospheric circulation, impacting the ocean circulation versus trends due to changes in air sea heat fluxes. And we've had a lot of interest in this simulation, so we can go ahead and go to the next slide. Just to show, all we've really done is run the large ensemble diagnostics package over this so far. So we don't really know too much, but we have a few things that I figure we might as well just show. So I don't know if you can see my screen, probably not because I'm not sharing. So the top right is the top left is the mechanically decoupled ensemble. We've got 20 members, and this is the SST trends over the historical period. And then the bottom panel is the fully coupled. And so for our runs, we used the smooth biomass burning version. So we're only comparing those to those 50 members from the fully coupled that have the same forcing. And I think you could kind of just see a few differences. Some, I guess, characteristics that others have pointed out to us. Then it looks like the mechanically decoupled doesn't warm quite as much. And Kay's been digging into that, and it looks like that this version of the runs, the deep ocean is storing more heat than in the fully coupled run. We don't quite understand why that is yet, but that's one of the analyses that we're thinking about doing. Another characteristic that was pointed out to us is that the interhemispheric asymmetry in the warming looks less pronounced in the mechanically decoupled run. So that's another thing that we're kind of curious to figure out, and we're definitely welcoming suggestions from the community on things to look at. And then the right panel is just the globally averaged SST trends. And the main thing to point out is that the fully coupled warms more over this time period than the mechanically decoupled. Again, we think the decoupled run is storing more heat in the deep ocean. But it is diverging kind of at that same period that Isla mentioned in some of the other runs, right around 1970 into 1990. That's about when the experiments start to diverge. Exactly why, we're still trying to figure out. So lots of interesting questions, but eventually, yeah, we'll be able to make these runs available once we at least figure out the basics of what's going on before we hand it all out.
Great, thanks. Okay, so then just one last quick thing in case anyone's new or not aware, just a couple of resources that might be of interest. No, sorry, the labeling got messed up here, but so Adam Phillips and Clara have produced this new version of the CVDP that is geared towards large ensembles, and there's lots of information here, but you can go to the website, and this is the kind of thing that you can get from this new package. This is comparing indices of or pattern correlations with observations of the PDV, and then RMS difference from observations. So you can look at all of large ensembles and compare them and look at intermodal spread. And so this package will calculate these kind of indices for you. And then this is from Dave Schneider. So he's really the person to contact about this. Yeah, if you're interested to hear about the various data sets, the climate data guide kind of summarizes the pros and cons of different observation-based data sets. And so there's been a few things happened in the last while. Dave is working on redeveloping the website, so you can see that it's looking more modern. And there's also been this board of advisors that have got together who are advising on kind of what are the important things to include here. And so I think they've had productive meetings over the last while. But yeah, contact Dave if you have any suggestions or questions about this. So that's all we have in terms of an update. So we'll move on for the last 10 minutes or so to just an open discussion, and obviously feel free to discuss anything. But I guess the two main things we would like to hear about are anything you'd like to look at in this new regionally refined North Atlantic simulation, and then what kind of simulations you'd like to propose for the next allocation. And we'll be writing this proposal in the summer. So I think you have the Google Doc links, and I see that people are already writing some things in here. And so feel free to just continue to write there, but also we can start with an open discussion now if anyone would like to say anything. So I'll stop sharing. Okay, I think did I miss anything in the chat here? Okay, so there were some questions about the variable resolution from Clara. So does the forced IHASP simulation use, so so the forced ocean simulation, I mean, this is open for discussion. If we don't think this is the right thing to do, we don't have to do it. But I think this is a suggestion from Steve at our last meeting, is that this is an ocean and sea ice only simulation that's being forced by observed surface fluxes. So it will have the advantage of having, it's kind of similar to what was used for initializing the decadal prediction large ensemble. So it'll have low frequency variability that's kind of realistic, but what we can get from this that we can't get from the observations is kind of some representation of like 1/10 degree features in the ocean. But yeah, if people think it would be preferable to use like the HAD IST quarter degree actual observed SSTs, we could do that instead. Oh, I guess Steve, sorry, has already answered. Does that answer your question, Clara?
Yeah, thank you very much. You just hadn't specified where the SSTs come from. So I thought we should make sure everybody knew about that.
Okay, yeah, it's not, I mean, it's the SSTs come from the forced ocean simulation, but they're
which is forced by
yeah. Okay, so Jerry's asking about the science questions. So I guess my main motivation for this regionally refined North Atlantic is really to look at whether the low frequency variability in the jet stream changes if we go to very high resolution. And it's related to, I guess, the signal to noise paradox and the fact that we don't have low frequency variability in the jet stream. That looks like what happens in observations. And I think there's a high chance that it won't work, but that's the hypothesis that the Met Office has put forward, that really things change a lot when you go to high resolution, because you have different interactions between the storm systems and the SST variability. But I'm hoping there'll be other things. I think Christine is interested in looking at atmospheric rivers. There was a student who was interested in looking at polar lows. But yeah, anything else that anyone wants to do would be welcome.
Okay, thanks. So yeah, I've heard this discussed for a while. I was just kind of curious because it's going to be basically looking at features in the atmosphere, right? So you're going to look at atmospheric dynamics mainly when it's really high res.
Yeah.
Yeah.
Yep.
I mean, for what it's worth, years ago we did a set of runs, with Youngo and Claude and Mike Alexander, where we try to put in a realistic kind of KOE SST anomaly with the CAM5, and we did 1 degree and quarter degree runs. And in that case, we found a very different response to the SST. So the 1 degree was a classic Hoskins and Caroli kind of response, low to the east of the warming, subsidence over the warming, no remote response. And at a quarter degree, we got a change in the storm track. So the heat balance was different. You basically got a change in the moist static energy transport by the storms. So you didn't get you didn't get any surface circulation anomaly to speak of. You didn't get subsidence over the SST. And as a result, there was a real pronounced downstream response. And yeah, I mean, I think that kind of experiment is still worth doing. I mean, I know Youngo would probably as well, although he doesn't do that so much, but I'd still love to see that in the Pacific again at a kind of a more thorough calculation as well.
Yeah, it's definitely.
Same thing for the Atlantic. I mean, I think it would be interesting.
Yeah.
There.
I think it might, maybe seeing how this one goes, maybe a Pacific version would be something to propose for the next allocation. And I guess what you described is, I guess, what we're exactly hoping to see, although you don't see it at a quarter degree, any difference in the jet stream variability at this point. But yeah, we'll see what happens with 1/8 degree.
Yeah, I mean, one possibility there was that it had a lot to do with the fact that a lot of the precipitation in the KOE region is convective precipitation too. So that it was never clear to me how much that was driving some of these effects. But.
Okay. Steve, did you have something you wanted to say, or I see you've lowered your hand?
Yeah, just a minor point in your slide. You said this experiment will go from 1950, but the IHESP simulation starts in 1958. So
okay.
I think you can get SSTs from 1958 through probably 2018 for this experiment.
Okay. I didn't realize that. Okay, that's probably, I guess we could weigh up the pros and cons. I guess if we use the quarter degree HADIS, we could start at 1950, I think, but it might be better to start in 1958. Yeah, thanks. All right. Does anyone have any other things you'd like to suggest that we consider for the next allocation?
I put it in the Word doc. The idea, I think Yaning showed this morning, I couldn't join the presentation, but the simulations that we did, yeah, Adam Phillips basically did them, but lots of people chipped in. Matt Newman gave the SSTs. So they're like using limb-generated SSTs to run AMIP simulations or TOGA simulations to be more precise. And so to explore different historical SSTs other than the ones we've observed. And so those, we have like two ensembles with two contrasting SST trajectories from 1960 to today. And so we want to find a way to make those available to the community. But if they're of interest and we realize there's other SST cases that might be interesting, sort of synthetic ones, then that could be another idea. But I feel already quite fortunate that we were able to do those. I don't want to push them too much, but it's definitely an idea that could potentially be of interest.
Yeah. Yeah, Clara?
Yeah, I just wanted to comment on, I think these single forcing runs, we heard several talks this morning making use of the CSM1 single forcing, and I think they're just becoming more and more valuable, to the entire community. There's a whole, as you know, WCRP Lighthouse activity now on detection and attribution, hoping for these somewhat large ensembles of single forcing runs. And I think that, what you've stumbled on as, maybe the protocol is, could change at least some aspects of the answer. I think we should see, maybe in time for the summer meeting of the working group, where your analysis is at and whether, then one wants to propose the companion all but single forcing simulations with CSM2, or at least some subset of those. So I think we should keep sort of a bit of an open mind and open, slot for possibly, really comprehensively comparing the protocols, just because it's going to feed in, to other modeling groups and this whole Lighthouse activity. And I think we might be in a really good position to inform what approach is, maybe is more valid. And then that could be the basis for, other modeling groups to adopt that same approach. So I just wanted to just keep that in our minds so that, we can revisit that maybe in the June meeting.
Yeah, I think that's a good idea. Especially at least for the aerosol one. I mean, I feel like the other forcings are kind of the same, and I think we could probably, well, we need to test it first, but probably just calculate the aerosol effect as a residual of all the others. But it would be good to show that is the same as what you'd get if you just did it the CSM1 way. There's a question from Who in the chat about how with this high resolution run, if we use both the high res SSTs and the atmosphere, it might be difficult to know what has caused the change. And I agree, but I feel like it's probably the best to just start with giving it everything and seeing if you get anything different. And then once you do, start to pull it apart. That was kind of the motivation for using both high resolution SSTs and the high resolution atmosphere. And so I guess if we do this run first, then we can kind of see what it looks like and decide what might be needed to propose in the next round to understand influences further.
I mean, would there be a time scale issue there where you might not want the finest scale SST? Because the finer the scale of SST, the more you'd have to worry it's coupled to the atmosphere in reality, and you're putting it in now as a forcing. I mean, that's the mid-latitude SST problem in a nutshell. That was why when we did our experiments, we were really constrained about just putting it in the KOE region so that we were putting in SST in a place where you could make a pretty good argument that the ocean was doing a lot of the driving.
Right. Yeah, that's a good point. Yeah, I guess it depends though, because I mean, you do have people arguing that these fine scale ocean eddies are driving change, and that's we're not seeing it in models because we're not resolving them. But yeah, I don't know. Yeah, any thoughts of what's preferable? They're definitely welcome.
Yeah, I mean, I guess it depends upon what you're testing. I mean, obviously, from my perspective, I would argue the issue is the atmospheric model resolution isn't high enough, and that boosting the resolution, if our results can be believed, is the important component. We did do some, we didn't do enough, but we started doing a second ensemble where we use the high resolution atmosphere, but use the 1 degree SST. And we seem to be getting about the same result. So it looked like it was more of an atmospheric thing, but like you say, then there are people who argue the opposite. But
yeah,
for what it's worth, in those cases, they're coupled models. So I guess the question is if you do an uncoupled, if you do an AMIP experiment, how do you want to best design that?
Yeah.
And I would say you might want to consider the possibility of not even putting in SSTs, observed SSTs everywhere. Sort of for the same reason that we had, that, you know, you do run, there's a paper, you know, there's the Brotherton and Battisti paper from years ago where they kind of illustrated why this can be an issue. But, you know, you can just think of it in a hand wavy sense. If you have a system where X is forcing Y, and so Y has a certain response, and now you remodel it where you use the observed Y to force X. I mean, yeah, it might appear to reproduce a little bit of X, but it won't be quite right. And then how do you interpret that?
Yeah. Yeah, and I guess it's there with the same issues there with our low resolution. And so maybe, but yeah, to really compare those two would be a first stab at seeing what difference does resolution make, and then start to worry about, does it make any sense?
Yeah.
Yeah. Any other thoughts? I know we're past the time, so obviously feel free to leave if you had enough Zoom for the day.
I had a quick question about pacemaker experiments. I don't know if you're still planning on doing them. I was curious, particularly, I know the tropical Pacific pacemaker for the CSM2 is different than for the CSM1. And I was wondering if you had done any with the CSM2 that had the same configuration so that you could do more of a like-to-like comparison. You know, as Kara knows, I'm real big on that Aerosol connection, and I think that the CSM1 pacemaker experiment kind of produced that. So I'm curious if that's also in the CSM2 or if it acts differently.
Well, so sorry, I did not mention all of the things that have been done. I only mentioned kind of just things that have been done recently, but yeah, there are the tropical Pacific pacemakers, the CSM2, that have a different nudging region that tapers off further to the west. We have not run, at least I'm not aware that anyone has run CSM2 with the same setup as CSM1. And yeah, so, but they are there if you want to look at those, but with a slightly different nudging region.
Right, but the nudging, so what I liked about the way the CSM1 ended up working, maybe it wasn't intentional, was that because it cut off at 170, you have the same Enso error in the Western tropical Pacific, but you have the kind of correct, SSTs from 170 to the east. So that difference plot that you have in the appendix, kind of buried in your paper, it's the best figure in the paper, I think. I like to call the error teleconnection, and you can see it coming out of the Western tropical Pacific. It's kind of this error. What is the error that you get? What is this westward shift in Enso, which we see in every model that's ever been made, without exception? What does that shift do? And so you had a kind of a nice set of experiments, and yeah, we are interested in looking at those. We're ping you about that, but I'm kind of curious if you get that kind of error, what happens in a different model, let's say the CSM2? Do you see the same sort of thing, or something different because the model has other different characteristics?
I think you designed some AMIP experiments to answer that, Matt, where you could take I think it's, the model's biased mean state that is the culprit for that, those errors. And I'm not sure you have to have a pacemaker to really assess that.
Yeah, but it's just, I wonder how true that is. That's everybody's assumption, I know.
Yeah.
But that was why that was kind of an interesting experiment, because you had you had both in the same run. You had the right SSTs up to 170 and then the wrong further west.
Right.
You'd have to, you could do an AMIP experiment with CAM6 where you use the SSTs that you got in the CSM1 pacemaker, obviously.
Exactly. Yeah. I think that would be a faster way to get at that.
Yeah.
Yeah, and I guess our motivation was we didn't want that error in the pacemakers, which is why we did it that way, right? For other purposes.
Yeah.
Okay, any other thoughts? But yeah, for the pacemakers and everything, like if you just go onto the working group website, there's information about how to get to all those simulations. All right, well, I guess if there's nothing more, we'll finish up, and please put your thoughts into those Google Docs if you have any about other simulations, and we'll discuss it again in the summer before we write the proposal. And thanks to all the speakers for great talks. And I guess we'll see you in June.
And thanks to the co-chairs for organizing a really interesting session.
Yeah, thank you very much.
Thanks.
Very well done.
Bye.
Bye, Isla.